Hello there, and welcome to Life Beyond Seen, where curiosity gets comfortable and science takes the scenic route toward understanding the mysteries that cradle our planet. Tonight, we're turning our attention not to the stars above or the passing of time, but to a realm far closer to us and yet far more alien. A place that lies just beneath the surface of our own world, stretching into darkness so deep that sunlight itself cannot follow. It's a realm that covers more than 2/3 of Earth, and still we know more about distant planets, more about the surfaces of moons billions of kilometers away, than we do about what lies beneath the waves on our very own planet. So, let me ask you something before we dive in. Where are you listening from tonight? And how close is the ocean to where you are right now? Maybe you're within earshot of its tides, or maybe you've only seen it in pictures and documentaries. Either way, what waits beneath that shifting blue surface is more mysterious than most people realise. And if you find this quiet exploration soothing, if it's the kind of slow and thoughtful journey that helps your mind unwind after a long day, I'd be deeply grateful if you gave this video a like, maybe even subscribed, so others searching for a gentle corner of wonder might find it too. Because tonight, we're not chasing stars or pondering seconds. We're sinking, slowly and deliberately, into the last great frontier of Earth. Somewhere between sunlight and silence, pressure and possibility, lies the story of the deep sea and why, even now, it remains the least known place on the planet we call home. For most of us, the ocean is a surface. It's waves curling along a beach on a summer day. It's the rhythmic crash of water against a rocky shore. It's ships crossing blue horizons and perhaps a memory of salt spray on your skin. But beneath that familiar face is a world that has nothing in common with the one we live in. The ocean is vast. It covers more than 70% of Earth's surface, and yet more than 80% of it remains unexplored. Think about that for a moment. More than 4/5 of the largest living space on our planet is still, for all practical purposes, a blank map. We've mapped Mars and the Moon in greater detail than we've mapped our own sea floor. And it isn't because we're lazy or indifferent. It's because the deep ocean is unlike any other environment on Earth. It's not just big. It's hostile, immense, and profoundly difficult to reach. The deeper you go, the stranger everything becomes. Light disappears, pressure mounts, temperature drops. The rules of life twist into unfamiliar shapes. Down there, our everyday assumptions fall apart, and that is part of why it remains so hidden. Our story begins just below the surface, where sunlight still dances in ripples of gold and blue. This uppermost layer of the ocean, the epipelagic zone, extends roughly 200 meters down. Here, photosynthesis thrives, fish dart and feed, and human divers can still function without special equipment. But even here, at the shallowest edge of the sea, the scale is daunting. The Pacific alone spans more than 60 million square miles, larger than all the continents combined. Imagine trying to explore a mountain range that covers most of the planet, except instead of walking across its slopes, you have to travel through a dense, heavy fluid that resists every movement and crushes anything that descends too deep. That's the challenge oceanographers face every day. Even with satellites, ships, and robotic probes, the sheer size of the ocean makes full exploration nearly impossible. Go deeper, and the sunlight begins to fade until somewhere around 1,000 meters down, it disappears completely. This is the midnight zone, and it's as foreign to us as the surface of an alien planet. Down here, the water is pitch black, and the pressure is immense. For every 10 meters you descend, the pressure increases by about 1 atmosphere, the equivalent of the air pressing down on you at sea level. By the time you reach the deep ocean floor, pressure can exceed 1,000 times what you experience on land. It's enough to crush steel, enough to make even the most sophisticated machines creak and groan. This alone explains part of the mystery. The deep sea doesn't hide its secrets because we aren't curious. It hides them because it can. It is a place that resists us by its very nature. It's also vast in ways that are hard to imagine. More than 90% of the ocean's volume lies below 200 meters. Most of that space is completely dark, relentlessly cold, and under crushing pressure. It's the largest habitat on Earth, home to countless species, many of which we've never seen. And yet, despite that immensity, we've explored only a fraction of it. Human missions to the deepest parts of the ocean are so rare you could count them on one hand. Even robotic vehicles, our best tools for probing the abyss, have mapped only a small portion of the seafloor in high detail. To this day, enormous stretches of the ocean floor remain as featureless on our maps as unexplored continents once were. The challenges aren't just physical, they're technological and financial too. Sending equipment into the deep sea isn't like launching a drone into the sky. Machines must withstand crushing pressure, operate in total darkness, and function without direct communication. Every meter deeper means more engineering complexity and more cost. The ocean, unlike space, isn't empty. It's dense and dynamic. Water currents tug and twist at submersibles. Sediments cloud instruments. Salt corrodes. Every expedition is a battle not just against depth but against the environment itself. And even when we succeed in sending our instruments down, retrieving them is another story. A probe that fails or a cable that snaps in the abyss is usually lost forever. It's a high-stakes game with expensive pieces. It's tempting to ask why we devote so many resources to exploring space when so much of our own planet remains unknown. After all, the nearest deep-sea trench is just a few kilometers below us, while Mars is millions of kilometers away. But the answer isn't as simple as priorities. Space, for all its challenges, offers some advantages. It's predictable. It's open. Once a spacecraft leaves Earth, it travels through a vacuum, free of resistance, and instruments can beam data back across vast distances with relative ease. The ocean is the opposite. It's chaotic, constantly moving, filled with pressure, salt, and darkness. Sending signals through seawater is difficult. Maintaining power at depth is harder still. A probe orbiting Mars can send back a live feed of images. A submersible in the deep sea often operates almost blindly, returning only limited data after it surfaces. And yet, despite these obstacles, we have ventured into this alien world. From the early bathyspheres of the 1930s, steel spheres lowered on cables to depths never before reached, to today's remotely operated vehicles and autonomous submersibles, each expedition has peeled back another layer of the unknown. What we've found has been extraordinary. Life thrives where we once thought it impossible. Entire ecosystems exist around hydrothermal vents, feeding not on sunlight but on chemical energy from Earth's interior. Giant squid, once the stuff of sailors' myths, glide silently through the dark. Strange gelatinous creatures drift like living ghosts. Some animals glow with their own light, producing bioluminescence that paints the darkness in blues and greens. These are not just curiosities. They are reminders that the deep sea is not barren. It is vibrant, dynamic, and teeming with life, much of it utterly unlike anything we know. But if the deep sea is so rich and fascinating, why is it still so unknown? Part of the reason is that we're only beginning to grasp its complexity. The ocean isn't a single environment. It's a layered, shifting system of currents, temperatures, salinities, and pressures. Each layer supports different forms of life. Each region behaves differently. Exploring one part doesn't tell us much about another. The deep Pacific is not the same as the deep Atlantic. A trench ecosystem is nothing like a seamount community. To understand the deep sea fully, we would need to sample it across countless points and times, a task that would take generations. There's also the question of visibility. Light is our most powerful tool for observing the world, but in the deep ocean, light simply doesn't exist. Our eyes are useless there, and even the most advanced cameras require powerful artificial illumination. But bringing light into the deep sea isn't straightforward. Bright lights can disturb delicate ecosystems, scare away creatures, or alter behaviours. Even the act of observation changes what we're observing. It's a paradox that marine scientists wrestle with constantly: how to study a world without altering it. Another subtle barrier is time. deep-sea exploration is slow work. A descent to the abyssal plain can take hours. Mapping even a small patch of seafloor in detail can require weeks. Weather on the surface can delay or cancel missions. Equipment failures can set back research by months. In contrast, a telescope can observe vast regions of space in minutes, gathering terabytes of data overnight. Oceanography moves at the pace of the ocean itself, deliberate, unpredictable, and often frustratingly slow. And then there's the simple matter of human perception. We're a species that looks up, not down. The sky has always captured our imagination. Stars have guided our journeys and shaped our myths. The ocean, by contrast, is opaque and forbidding. We see only its surface, and what lies beneath has long been the realm of fear and fantasy. For centuries, the deep sea was imagined as a place of monsters and mysteries, a realm too hostile for humans to ever know. Even today, despite all our technology, some of that ancient awe remains. We still talk about the ocean's depths with a mixture of wonder and dread, and yet for all its resistance, the deep sea is crucial to life on Earth. It regulates the planet's climate, absorbing vast amounts of heat and carbon dioxide. It drives global circulation patterns that influence weather and seasons. It's home to ecosystems that support fisheries and biodiversity. It stores geological records that tell the story of Earth's past. And it may even hold resources, from minerals to medicines, that could shape our future. To ignore it is to ignore a fundamental part of the planet's system. Still, ignorance is precisely what defines our relationship with the deep. We know it exists, we know it matters, but we barely know what it contains. It is a frontier not because it is distant, but because it is difficult. It is a mystery not because it hides, but because we have yet to learn how to see. And that, more than anything, is why it remains the least known place on Earth. It's worth pausing here to think about just how extraordinary that is. We live in an age when satellites can read license plates from orbit, when spacecraft send selfies from the edge of the solar system, when genetic code can be sequenced in a matter of hours, and yet vast portions of our own planet remain blank. Mountains taller than Everest rise unseen beneath the waves. Trenches deeper than the height of Mount Kilimanjaro plunge into darkness. Rivers flow across the seafloor, carving valleys and deltas that no human has walked. Entire continents of life drift and feed and reproduce beyond the reach of sunlight. It's not that these things are unknowable, it's that they are hard to know. And that difficulty is precisely what makes them worth knowing. When we speak of the deep sea as unexplored, we don't mean it in the sense of total ignorance. We've taken glimpses, snapshots, moments of contact. But those glimpses are scattered and incomplete. Imagine trying to understand a city by visiting one building. Imagine trying to map a continent by standing in one field. That's roughly the state of deep-sea science today. We know pieces, but the whole remains elusive. This is why, despite centuries of effort, the deep sea still holds more questions than answers. How many species live down there? We don't know. How do they interact? We're still learning. What role do they play in global processes? Only hints and hypotheses. Even the basic geography of the seafloor remains uncertain in many places. Vast swathes of ocean are mapped only in the roughest detail, with features measured not by direct observation, but by inference from satellite data. It's as if we were trying to draw a detailed map of a forest by looking at its reflection in a lake. And yet every expedition brings surprises. Every probe that descends into the dark returns with something unexpected. A new species, a new geological formation, a new behaviour that challenges our assumptions. The deep sea rewards curiosity with revelation, and each revelation deepens the mystery. It is a reminder that even on our own planet, perhaps especially on our own planet, the unknown is vast. So as we prepare to descend further into this story, keep that image in mind. A planet mostly water, mostly dark, mostly unexplored. A world beneath our world that is larger, older and stranger than anything we have yet imagined. And know that this is only the beginning. Because if the surface of the sea is the doorway, and the twilight zone the threshold, what waits beyond them is a realm that defies our senses and rewrites our definitions of life, pressure, and possibility. The deep ocean is not just a place we have yet to explore. It is a place that challenges the very way we think about exploration itself. When we think of our planet, we tend to picture its continents first. We trace the outlines of countries and coastlines on a globe, memorize the shapes of mountains and deserts, and think of Earth as a mostly solid world, with oceans scattered between its land masses. But that image is profoundly misleading. The truth is the opposite. Earth is not a planet with oceans. It is an oceanic planet with some land scattered across its surface. Water doesn't just fringe our continents, it dominates them. It doesn't just fill basins, it shapes the very contours of the planet. And nowhere is this more evident than in the deep sea, a realm so enormous that it defies not only exploration but imagination itself. To begin to grasp the scale of what lies beneath, it helps to start with some numbers. More than 70% of Earth's surface is covered by ocean, and more than 97% of all the water on the planet is contained within those oceans. They hold about 1.35 billion cubic kilometres of water, a number so vast it's almost meaningless without comparison. If all the land on Earth were levelled flat and the oceans allowed to spread evenly across the surface, the entire planet would be covered by a layer of water nearly 3 kilometres deep. Even Mount Everest, the tallest peak above sea level, would lie submerged beneath 700 metres of water. The oceans aren't just a feature of Earth's geography, they are its defining characteristic, and yet we rarely think of them that way. Part of the reason is that we live on the thin, dry crust that pokes above the waterline. To us, the oceans seem like boundaries, vast, wet gaps between the continents we inhabit. But the oceans are not interruptions. They are the main event. They connect rather than divide. They cover far more of the planet's surface than land ever could. And beneath their waves is not emptiness, but an entire world of landscapes and ecosystems, of mountains and valleys, of trenches deeper than anything above sea level. The largest continuous mountain range on Earth, the mid-ocean ridge, winds through the oceans for more than 60,000 kilometres, stretching farther than the circumference of the planet itself. The deepest trench, the Mariana, plunges nearly 11 kilometres below the surface, far deeper than Everest is tall. If Mount Everest were dropped into the Challenger Deep, its peak would still lie more than 2 kilometres beneath the surface. The scale becomes even more staggering when we compare the deep ocean to the spaces we've explored beyond our planet. Humans have sent probes to the edges of the solar system, mapped the surfaces of planets and moons, and peered into the farthest reaches of the cosmos. We have radar maps of Venus, topographic models of Mars, and even detailed surveys of asteroids millions of kilometres away. And yet we have better maps of the surface of Pluto, a world over 5 billion kilometres distant, than we do of our own sea floor. Only about 25% of the ocean floor has been mapped in high resolution. The rest remains vague outlines and estimations, sketched by indirect satellite measurements rather than direct observation. Why does this matter? Because the size of the ocean is not just a statistic, it is a clue to why it remains unknown. Its vastness isn't simply horizontal, spreading across most of the globe, but vertical as well, plunging into depths that dwarf the tallest mountains and create more three-dimensional space than all the continents combined. The volume of the deep sea is so immense that if you could scoop all the land on Earth into it, the sea would swallow it whole and still have room to spare. This immensity means that even with our most advanced technology, even with fleets of research vessels and decades of effort, our attempts to explore the deep sea are like trying to understand a rainforest by examining a single leaf. The vastness of the ocean also challenges how we think about ecosystems. On land, ecosystems are bound by geography. Mountains and rivers define where one environment ends and another begins. But in the ocean, boundaries are fluid. Water masses shift and mix, creating gradients of temperature, salinity, and nutrients that stretch for thousands of kilometers. Entire ecosystems drift with currents, forming invisible highways of life that connect distant regions. A whale that feeds in the nutrient-rich waters of Antarctica might later give birth in the warm tropics. Microscopic plankton born near the equator might drift for months and die in the Arctic. The deep sea adds another layer to this complexity. Its vast plains and trenches, its seamounts and ridges, form habitats that are not only remote but also dynamic, shaped by geological forces and biological processes that operate on timescales far longer than a human lifetime. This vastness also means that the deep ocean is not uniform. It contains multitudes. The abyssal plains, which make up much of the seafloor, are vast, flat expanses of sediment stretching for thousands of kilometers, often appearing featureless but hiding intricate ecosystems within their mud. Rising from these plains are seamounts, underwater mountains formed by volcanic activity, that create islands of biodiversity in the deep. Hydrothermal vents spew superheated, mineral-rich water from the Earth's crust, supporting entire communities of life that thrive without sunlight. Submarine canyons, some deeper and longer than the Grand Canyon, cut into the continental slopes, channeling nutrients from shallow waters into the abyss. And then there are the trenches, narrow, deep scars where tectonic plates collide and one slides beneath the other, plunging into darkness beyond darkness. Each of these environments is its own world, governed by its own rules. Each harbours life adapted to conditions we can barely imagine, and each remains, for the most part, unexplored. The sheer size of the deep ocean means that even our most ambitious expeditions can study only tiny fragments. A remotely operated vehicle might spend weeks exploring a single seamount, gathering data from an area no larger than a few football fields. A research cruise might map a section of seafloor the size of a small city, a pinprick on the map of the global ocean. It's like trying to write a biography of Earth by reading a few scattered pages. Even the way we measure the deep sea reflects its enormity. On land, we speak of distances in kilometres or miles, of heights in metres or feet. In the deep sea, we speak of pressure, of atmospheres, of tons per square inch. At the bottom of the Mariana Trench, the pressure exceeds 1,286 bars, more than 1,000 times the atmospheric pressure at sea level. That's equivalent to the weight of 50 jumbo jets pressing down on a single square metre. Every 10 metres deeper adds another atmosphere of pressure. The ocean is a relentless, crushing presence, and yet, despite this, life thrives. Fish, crustaceans, and microbes survive, even flourish, under pressures that would obliterate a human-made submarine. Their existence is a testament to life's adaptability and a reminder of how much we still have to learn. This vastness also complicates the logistics of exploration. On land, scientists can drive, hike, or fly to their study sites. In space, we can launch telescopes that stare unblinking into the void for years. But in the deep sea, every expedition is an operation. Ships must be outfitted, equipment tested and calibrated, weather windows planned. Once at sea, research vessels often spend days just reaching their destination. Deploying instruments can take hours. Recovering them can take longer. The deeper the dive, the longer the descent and ascent. Each mission is costly, complex, and limited in scope. The result is that the deep ocean is explored not continuously, but in brief, scattered glimpses. A few days here, a few dives there. Weeks or months of planning for hours of data. It's easy to underestimate how much this vastness matters. We think of the deep sea as a single place. Down there, beneath the waves. But it's not a place. It's billions of places, connected but distinct, each shaped by local conditions, each telling a different story. Imagine trying to study Earth's deserts, rainforests, mountains and plains all at once, with only a handful of tools and a few days at a time. That's what deep-sea scientists face. They are not exploring a single world, but a universe of environments, each demanding its own approach. The vastness of the ocean also hides its complexity from our senses. On land, we see landscapes in a glance. Mountains rise on the horizon. Forests stretch across valleys. Deserts sprawl beneath the sun. In the ocean, we see none of that. The surface hides everything. Even from space, satellites can reveal little beyond broad patterns of temperature or colour. The deep sea is invisible, its vastness masked by the thin shimmer of the surface. This invisibility affects how we think about it. It's hard to care about what we cannot see. It's harder still to explore what we cannot even imagine. And yet, we know enough to know that this vastness matters. The deep ocean plays a critical role in Earth's climate. It stores enormous amounts of carbon, helping regulate the planet's temperature. It circulates heat and nutrients through global currents that influence weather and ecosystems far above the waves. It shapes geology, recycling Earth's crust at subduction zones and forming new crust at mid-ocean ridges. It supports fisheries that feed billions of people and provides habitats for organisms that could hold the keys to new medicines and materials. It is not a remote or irrelevant place. It is the beating heart of the planet. The vastness also holds potential and peril. As technology improves, interest in deep-sea mining has grown. The abyssal plains are rich in polymetallic nodules, lumps of manganese, nickel, cobalt, and other metals essential for modern electronics. Hydrothermal vents contain valuable minerals deposited by superheated fluids, but extracting these resources poses risks we barely understand. The ecosystems of the deep sea are slow to recover. Some species live for centuries, some may take millennia to return if disturbed. The vastness that makes exploration difficult also makes damage irreversible. A single mining operation could disrupt an ecosystem the size of a small country, and once damaged, the deep sea does not heal quickly. All of this underscores a simple truth. The deep ocean's vastness is not just a barrier to knowledge, it is a fundamental part of its nature. Its size is why it remains unknown. Its scale is why we must approach it with patience and humility. And its immensity is why every discovery feels like a revelation, a glimpse into a world too large to ever fully grasp. Yet, even this vastness is only part of the story. It explains why the deep sea is hard to explore, but not why it captivates us. For that, we must look beyond size and depth and consider the qualities that make the deep ocean unlike any other place on Earth. Among those, one of the most important is darkness, not just the absence of light, but the presence of a kind of perpetual night that shapes everything that lives and happens below. Because while the ocean's sheer size sets the stage for mystery, it is the darkness that truly defines it, cloaking life and landscapes in a veil that only the most determined exploration can pierce. And so, as we continue our descent into this unknown world, the next layer of the story waits in the shadows, where light fades and the secrets of the deep sea begin to emerge in ways that challenge everything we thought we knew about life on Earth. If the ocean's vastness explains why it remains hidden, then darkness is the force that keeps its secrets safe. It is easy to forget, standing under a bright sky, how rare light actually is. On land, we take it for granted. It spills over mountains, reflects from city windows, glows from lamps and screens and even the faintest stars. Life on the surface is built around light. Plants stretch toward it. Animals depend on it to hunt or hide, and our own bodies set their rhythms by its rising and falling each day. But the ocean is a realm where light is a stranger, and the deeper you go, the quicker it vanishes. Sunlight, the same force that drives weather, feeds ecosystems and shapes the patterns of life on land is swallowed by water with ruthless efficiency. And that single fact, that light cannot travel far beneath the waves, changes everything about how the deep sea works and why it remains unknown. The story of darkness in the ocean begins just meters below the surface. As sunlight enters the water, it is scattered and absorbed. The brighter, warmer colours, red, orange, yellow, disappear first. Even by 10 meters down, red light is gone. By 50, orange and yellow have faded. Only the shorter, bluer wavelengths penetrate deeper, and even they surrender by the time you reach 200 meters. That is the lower boundary of what scientists call the sunlit zone, the thin skin of ocean where photosynthesis can occur and where most familiar marine life thrives. It might seem deep to us, far deeper than any pool or lake, but in the context of the ocean, it is barely a scratch on the surface. More than 90% of the ocean's volume lies below this layer, in darkness so complete that even a powerful spotlight fades into black just a few meters from its source. Below the reach of sunlight, the ocean changes. The water grows colder, the pressure mounts, the landscape becomes more alien with every meter. Between 200 and 1,000 meters lies the twilight zone, a realm of dim, ghostly light that never changes into day or night. Here, what little sunlight remains is so weak it cannot support photosynthesis. Plants disappear, and animals adapt in strange ways. Some develop enormous eyes to catch every photon. Others become transparent or silvery, blending into the faint shifting glow above. Predators lurk in near darkness, relying on bioluminescence, like they generate themselves, to find prey or lure it closer. This is the last place where the sun has any influence, and even here it is more memory than presence. Below 1,000 meters, darkness becomes absolute. This is the midnight zone, a place where sunlight has never touched the seafloor. It is a darkness so complete that our senses fail to describe it. On land, even the darkest night is punctuated by starlight, by the faint glow of the atmosphere, by the reflection of distant cities. In the deep sea, there is none of that. The darkness is total. It is constant. It is unbroken. This is the world in which most of Earth's living space exists, and it is the reason so much of that space remains unknown. The absence of light is more than a visual problem. It reshapes the entire nature of exploration. On land and in space, light is our primary tool. We map, measure and observe with cameras, telescopes and lasers. We rely on reflected light to show us shapes, distances and details. But in the deep ocean, that tool is useless. Cameras see nothing without artificial illumination. Lasers scatter and fade in water. Even sonar, which uses sound rather than light, struggles to provide the kind of resolution that visual instruments can achieve. Every observation in the deep sea is hard won, and every image represents hours of work, careful planning, and often luck. This is one reason why our understanding of the deep sea lags so far behind our understanding of space. A telescope can scan thousands of stars at once, collecting light that has travelled for millions of years. A deep-sea camera can illuminate only a small cone of water a few meters across. The scale is different. The speed is different. The difficulty is incomparable. And every time we turn on those lights, we face another problem. We change what we are observing. Light is rare in the deep sea, and most creatures are exquisitely sensitive to it. A bright spotlight can blind or stun them. It can scare them away before we can study them. In some cases, it can even harm them. This means that much of our observation must be done carefully, indirectly, or with minimal disturbance. A slow and painstaking process that reveals the deep sea, one small detail at a time. Darkness also makes navigation and mapping difficult. On land, light reflects off surfaces, allowing us to build maps with cameras, drones, and satellites. In the deep sea, the only way to see is with sonar, which sends out sound waves and measures their echoes. Sonar is powerful and useful, but it has limits. It cannot easily distinguish fine details. It struggles with soft sediments or complex structures. It is also slow. Mapping the ocean floor with sonar is like painting a wall with a toothbrush. Possible, but painfully time-consuming. This is why, even with decades of effort, we have mapped only a fraction of the seafloor at high resolution. The darkness slows everything down. The absence of light shapes life itself in ways that are difficult to imagine from the surface. Most deep-sea animals have never seen sunlight. Their eyes, if they have them, are adapted to detect the faintest glimmers. Some have enormous pupils or specialized retinas. Others have lost their eyes entirely, relying on touch, vibration, or chemical signals to navigate. Many deep-sea creatures create their own light through bioluminescence, a chemical reaction that produces a cold, steady glow. Some use it to attract mates, others to lure prey. Some flash it as a warning to predators, while others use it to blend into the faint light above, disappearing from view. Bioluminescence is so widespread in the deep ocean that scientists estimate the majority of deep-sea animals can produce light in some form. It is a language of survival in a world where the sun is silent. This darkness also affects how energy flows through deep-sea ecosystems. On land and in shallow water, sunlight fuels photosynthesis, which forms the base of the food web. Plants convert light into energy. Herbivores eat the plants, predators eat the herbivores, and so on. In the deep sea, where sunlight never reaches, that entire system collapses. Most deep-sea life relies on a rain of organic material, dead plankton, fish, and other debris, falling from the surface. Scientists call it marine snow, and it drifts down slowly, sometimes taking weeks to reach the seafloor. It is a thin and uneven supply of energy, and deep-sea creatures have evolved to make the most of it. Many are slow-growing and long-lived, conserving energy in a world where food is scarce. Some wait motionless for weeks between meals. Others roam vast distances in search of sustenance. In certain places, however, life has found another solution. Around hydrothermal vents and cold seeps, places where chemical-rich fluids flow from the seafloor, entire ecosystems thrive without sunlight. Instead of photosynthesis, they rely on chemosynthesis, a process in which bacteria convert chemical energy into food. These bacteria form the base of a unique food web, supporting worms, clams, crabs, and fish that have never known light. It is one of the most remarkable discoveries of modern science. Life not just surviving, but flourishing in a world utterly cut off from the sun. And it is a reminder that the deep sea, though dark, is anything but dead. For scientists, the darkness of the deep sea is both obstacle and opportunity. It makes exploration difficult, but it also offers the chance to discover forms of life and systems of energy that challenge our understanding of biology. Studying how creatures live without light may help us understand how life could exist elsewhere in the universe, on the icy moons of Jupiter and Saturn, for example, where oceans may lie hidden beneath thick crusts of ice. It may also teach us new ways to harness energy or inspire new materials and technologies. Bioluminescent proteins, for instance, are now widely used in medical research as markers in genetic studies. Enzymes from deep-sea microbes help develop industrial processes. The darkness that hides the deep-sea's secrets also shelters discoveries that could change our lives in unexpected ways. But that same darkness is also why so many of those secrets remain hidden. It limits not only what we can see, but how we think about what we see. Human beings are creatures of light. Our eyes evolved in sunlight. Our technologies rely on it. Our very sense of time and space is tied to the rising and setting of the sun. The deep sea operates outside all of that. It is timeless and unlit, a place where our familiar ways of perceiving and measuring fail us. When we look into space, even across billions of light years, we're still using light to understand what we see. In the deep ocean, we have no such luxury. We are forced to rely on indirect methods, sound, chemistry, touch, and these give us only fragments of the picture. Darkness also hides motion. On land, movement is visible. We can see animals migrate, watch storms form, track changes in forests and deserts. In the deep sea, much of this is invisible. Currents shift and swirl silently, unseen. Sediments move across the seafloor in slow avalanches. Animals migrate vertically, rising at night to feed near the surface and sinking back into darkness by day. The largest daily migration on Earth, happening every 24 hours and yet almost entirely hidden from view. Even major geological events, like volcanic eruptions or earthquakes along mid-ocean ridges, can pass unnoticed unless instruments happen to be nearby. The deep ocean is dynamic, but darkness keeps its movements secret. Even sound, which travels far better in water than light does, presents its own challenges. Sonar can map the sea floor and detect large objects, but it struggles to reveal detail. Passive listening devices can hear the calls of whales or the rumble of undersea quakes, but they cannot easily pinpoint their sources. The ocean is a noisy place, filled with natural sounds from waves, wind, rain, and ice, as well as human noise from ships and submarines. Distinguishing one sound from another requires sophisticated equipment and careful analysis. Even then, much remains unknown. New and mysterious sounds, long, low rumbles, sharp clicks, haunting moans, are still being recorded, their sources unidentified. Darkness hides not only shapes but stories. This secrecy has consequences. Because we cannot easily see what is happening in the deep sea, we're often unaware of changes that could affect the entire planet. Deep ocean currents, for example, play a crucial role in regulating Earth's climate. They transport heat and nutrients around the globe, linking surface conditions to the abyss. Yet, because these currents flow far below the reach of sunlight, we know little about their exact pathways, speeds, or how they might change as the climate warms. Similarly, deep-sea ecosystems may be sensitive to shifts in temperature, oxygen, or chemistry, but their remoteness and darkness make them hard to monitor. By the time we notice changes at the surface, in fisheries, weather patterns, or atmospheric composition, the deep ocean processes driving them may have been shifting for decades. Darkness also shapes how we think about ownership and stewardship. The deep ocean lies mostly beyond national borders, in international waters that belong to no single country. Because it is out of sight, it is often out of mind. Its remoteness makes it easy to ignore, and its darkness makes it easy to exploit without oversight. Deep-sea mining, for example, is advancing faster than our understanding of its potential impacts. Companies are preparing to harvest minerals from the seafloor, even as scientists warn that we know too little about these ecosystems to predict how they will respond. Pollution too reaches the deep sea. Plastics, chemicals, and heavy metals sink from the surface, accumulating in sediments and organisms in places where no light ever shines. Yet the darkness that hides the damage also hides the urgency. And still, despite these challenges, we return again and again to the deep sea, driven by curiosity and necessity. We send submersibles into its blackness. We lower sensors and cameras, build maps with sonar, and listen for echoes in the dark. Each time we uncover a little more, a new species, a new landscape, a new piece of the puzzle. And each time the darkness reminds us how much we have yet to learn. It is both barrier and invitation, a curtain drawn across the stage of the largest, least-known place on Earth. What makes this darkness particularly humbling is how close it is. The deep sea is not on another planet. It's not hidden behind a distant star or locked in a faraway galaxy. It is beneath us, pressing against the continents we inhabit, shaping the climate we depend on, influencing the life we see every day. And yet, it remains more mysterious than worlds billions of kilometers away. We have seen the rings of Saturn in exquisite detail. We have mapped the frozen plains of Pluto, but we have not truly seen most of our own planet. Darkness has kept it hidden. not out of malice or intention, but simply because that is its nature. And so, we come to understand that the deep ocean is not unknown by accident, it is unknown by design. Its vastness defies easy exploration, its darkness resists our instruments, its pressure crushes our machines. It is a place where our usual tools and assumptions fail, and that is why, even in the 21st century, even with all our technology and knowledge, the deep sea remains Earth's final frontier. Yet darkness, for all its power, is not the only challenge. Even if we could light up the deep ocean like a city street, even if we could banish the blackness with some new technology, we would still face obstacles that go beyond what our eyes can see. The ocean's crushing pressure, its cold, its remoteness, and the sheer hostility of its environment all conspire to keep it hidden. And so, to understand why the deep sea remains the least known place on Earth, we must descend deeper still into a realm where pressure rises to unimaginable levels, and where even the strongest machines strain against the weight of the water above. Darkness may guard the secrets of the deep sea, but pressure enforces them. If light is stripped away gently, fading with depth until it is gone, pressure builds relentlessly, rising without mercy with every meter you descend. It is not sudden or dramatic. It increases steadily, predictably, and yet with such immense force that it transforms everything it touches. It changes the physics of water, the chemistry of life, the engineering of machines, and even the way we think about exploration. It is the invisible wall that separates the world we know from the world we do not, and it is one of the most profound reasons the deep sea remains beyond our reach. Pressure in the ocean follows a simple rule. For every 10 meters you descend, the pressure increases by 1 atmosphere. At the surface, we live under the weight of 1 atmosphere. The pressure of the air above us, about 14.7 pounds per square inch. It's easy to forget that this pressure exists because we've evolved to live within it. Our bodies, our bones, our lungs and our blood are all built to operate comfortably under that load. But water is dense, about 800 times denser than air, and it does not compress easily. As you descend into the ocean, the weight of the water above you adds quickly. At 10 meters, the pressure is twice what it is at the surface. At 100 meters, it is 11 times greater. At 1,000 meters, the pressure reaches about 100 atmospheres, equivalent to the weight of a small car balanced on every square inch of your body. By the time you reach the deepest trenches, more than 11,000 meters below the surface, the pressure exceeds 1,100 atmospheres. That is more than 16,000 pounds pressing down on every square inch, enough to crush a human submarine like an empty can. It is difficult to imagine these numbers in a meaningful way because they are so far removed from our everyday experience. We live in a world where air pressure is constant and gentle, where we can climb mountains or descend into valleys without feeling much change. Even when we dive into a swimming pool, the extra pressure at the bottom is barely noticeable. But the ocean is different. It is vast and heavy, and its weight grows quickly. Imagine the Empire State Building, a structure of steel and concrete weighing hundreds of thousands of tons. Now imagine that weight pressing on a single square meter. That is roughly the pressure at the bottom of the Mariana Trench. It is a force so great that ordinary materials cannot withstand it. Steel buckles, glass shatters, human lungs collapse long before reaching such depths. This relentless increase in pressure is one of the fundamental challenges of deep-sea exploration. On land, we build machines to resist gravity, bridges, buildings, airplanes. But gravity pulls in one direction and at a constant rate. In the ocean, pressure pushes from all sides and increases with every meter. Every vessel, probe and instrument that ventures into the deep must be designed to withstand it. A small flaw, a weak weld, a microscopic crack can spell disaster. In 1960, when the bathyscaphe Trieste made its historic descent into the Challenger Deep, the deepest known point in the ocean, its thick steel sphere groaned under the pressure. At nearly 11,000 meters, The windows cracked as water pressed against them with unimaginable force. The two men inside, Jacques Picard and Don Walsh, described hearing a loud bang, the sound of the sphere flexing under pressure. They stayed only 20 minutes before beginning their slow ascent, knowing that even the smallest failure could be fatal. Since then, only a handful of human missions have reached such depths. James Cameron's solo descent in 2012 aboard the Deep-Sea Challenger was a triumph of engineering, but it also underscored the difficulty. The vessel's pilot sphere was barely large enough to sit in, its walls made of special materials designed to withstand the crushing weight. It took years to design and build, and even then the mission lasted only a few hours. Most of our deep-sea exploration is done not by humans, but by remotely operated vehicles, ROVs, and autonomous underwater vehicles, AUVs, which can go deeper, stay longer, and risk more. Yet even these machines face enormous challenges. The deeper they go, the more pressure squeezes their frames, cracks their seals, and threatens their electronics. Cables must be reinforced, cameras must be encased in thick housings, sensors must be designed to function under loads that would destroy ordinary equipment. Pressure also affects how we collect samples from the deep sea. A fish or crustacean that lives comfortably under hundreds of atmospheres of pressure can die within moments if brought to the surface too quickly. Its cells can rupture, its proteins can denature, and gases dissolved in its body can expand violently. Scientists have developed special pressurized containers to bring deep-sea organisms up intact, but these are expensive, complex, and limited in capacity. As a result, much of what we know about deep-sea life comes from incomplete or damaged specimens. Clues to a puzzle that remains largely unsolved. Even the water itself behaves differently under pressure. Its density increases, its freezing point changes, the way sound travels shifts, currents behave differently, chemical reactions slow or accelerate in unexpected ways. These changes ripple through the entire deep-sea ecosystem, shaping the biology of the organisms that live there and the geology of the seafloor beneath them. Creatures that thrive in the deep ocean are adapted not just to darkness, but to pressure itself. Their cell membranes are more flexible. Their enzymes are structured to function under intense compression. Their bodies are often soft and gelatinous, allowing them to deform without breaking. Some species have no gas-filled cavities at all, no swim bladders, no lungs, because such spaces would collapse under pressure. Others use special molecules called piezoletes to protect their proteins and cell structures from the crushing force around them. One striking example is the snailfish, a small translucent creature that lives in the Hadal zone, depths below 6,000 meters. Its body is soft and flexible, with no scales and minimal bone. Its enzymes are adapted to function under extreme pressure, and its cells are filled with protective compounds that prevent them from collapsing. It is perfectly at home in an environment that would destroy almost any other fish. But it also cannot survive at the surface. Remove it from the pressure of the deep, and its body fails. It is a reminder that life is not merely enduring the deep ocean's pressure, it is built by it. Pressure doesn't just shape biology, it shapes geology too. Deep-sea trenches exist where tectonic plates collide, and the immense weight of the water above adds to the forces driving these geological processes. Subduction zones, where one plate dives beneath another, are influenced by the pressure of the overlying ocean. Volcanic eruptions on the seafloor behave differently than those on land, as gases dissolve in magma under the weight of the water, altering how eruptions occur. Hydrothermal vents, where superheated water rich in minerals burst from the seafloor, exist because pressure allows water to remain liquid at temperatures far above its normal boiling point. At 2,500 meters, water boils not at 100 dig but at around 250 den. Without the weight of the ocean above, these vents, and the unique ecosystems they support, could not exist. Pressure also creates engineering challenges that go beyond simply building strong materials. Electronics behave differently under compression. Buoyancy calculations change. Even time itself is affected. The oscillators and clocks, for example, can shift slightly under high pressure, altering measurements. Every system that operates in the deep sea must account for these changes. It's not just about surviving the pressure, it's about functioning within it. That is why deep-sea exploration is not simply a matter of scaling up existing technologies. It requires designing entirely new ones. Humans, too, face fundamental limits imposed by pressure. The deepest scuba dives ever recorded reach around 300 meters, far shallower than the depths where most of the ocean's secrets lie. Beyond that, the risks grow exponentially. Gases dissolve into the bloodstream under pressure, and if a diver ascends too quickly, they can come out of solution, forming bubbles that block blood flow. A dangerous condition known as decompression sickness. Breathing ordinary air becomes impossible because oxygen and nitrogen become toxic under pressure. Divers use special gas mixtures to mitigate these effects, but even then, the limits remain strict. To reach greater depths, we must retreat into machines, submarines, spheres, and robots that isolate us from the crushing weight outside. This reliance on technology introduces another layer of difficulty. Machines capable of withstanding high pressure are expensive and heavy. They require powerful support chips, complex logistics, and meticulous planning. Each dive must be carefully coordinated, and each mission carries risks. Even small leaks or structural weaknesses can become catastrophic under the immense pressure of the deep sea. That is why deep-sea exploration is often measured in hours rather than days, and why each expedition is a rare and costly event. The psychological dimension of pressure is harder to quantify, but no less real. The knowledge that thousands of meters of water press above you, that a failure in the hull could mean instant death, weighs heavily on those who venture into the deep. Astronauts often describe space as silent and empty, but aquanauts describe the deep sea as crushing and omnipresent. It is not a void, but a substance, dense, heavy, and always pressing in. That awareness shapes how missions are planned and executed, how crews are trained, and how long they are willing to remain at depth. Pressure also affects how signals travel, complicating communication between deep-sea vehicles and the surface. Radio waves, which carry data through air and space, do not penetrate water well. Sound waves travel farther but more slowly, and they distort over distance. This means that real-time control of deep-sea robots is difficult, and commands often take seconds or even minutes to transmit. Feedback is delayed, and precise movements become challenging. The deeper the mission, the more pronounced these delays become, limiting what can be done remotely. All of this contributes to a simple but profound reality. The deep sea is not just far away, it is fundamentally different. It is not a place we can visit casually, not an environment we can enter without transformation. To reach it, we must shield ourselves from pressure, rethink our tools, and accept risks that few other scientific fields demand. It is exploration in the truest sense, slow, deliberate, dangerous, and deeply humbling. Yet the deep sea is not empty. Life thrives under pressures that would crush our strongest machines. It has evolved solutions to problems we struggle even to define. Some organisms produce proteins that remain stable where ours would fail. Some build shells and skeletons under pressures that would dissolve most minerals. Some live not just in the deep, but in the sediments below the seafloor under pressures and temperatures that push the known limits of biology. These creatures are not merely surviving, they are thriving, suggesting that pressure is not just a barrier, but a force that shapes life in profound ways. This realization carries implications beyond Earth. If life can exist under such extreme conditions here, perhaps it can exist beneath the icy crusts of Europa or Enceladus, moons thought to hide deep oceans beneath their surfaces. Perhaps it can survive beneath the thick atmospheres of exoplanets, where pressure is far greater than anything on Earth. The study of how organisms adapt to pressure, a field known as piezobiology, may one day help us recognize life elsewhere in the universe. Pressure even influences how ecosystems form and evolve. Species found at one depth may differ completely from those found just a few hundred meters deeper. Subtle changes in pressure can create invisible boundaries that separate habitats and limit migration. This layering means that the deep sea is not a single environment, but a series of stacked worlds, each shaped by the pressure that defines it. It also means that our understanding of one layer tells us little about the ones above or below it. Each must be studied on its own terms with its own tools and techniques. The effects of pressure extend beyond biology and geology. They influence how water circulates, how nutrients move, and how the ocean interacts with the atmosphere above. Deep sea currents, driven in part by differences in density and pressure, transport heat and carbon around the globe, affecting weather patterns and climate. They mix water masses from different regions, distributing oxygen and nutrients, and sustaining life even in the darkest depths. Without these pressure-driven currents, Earth's climate would be radically different, and life as we know it might not exist. Despite all this, pressure remains one of the least understood aspects of the deep sea. We know how it increases with depth, and we can calculate its effects in broad terms, but the details, how it shapes specific chemical reactions, how it influences the evolution of particular species, how it interacts with other environmental factors, are still emerging. Each expedition adds new data, but the picture remains incomplete. It is another reminder that the deep sea is not merely unknown because it is far away or hard to reach. It is unknown because it is governed by forces that we are still learning to understand. And yet, even with all these challenges, we continue to push deeper. New materials, new designs, and new technologies are allowing us to build vehicles that can survive greater pressures for longer periods. Advances in robotics and automation are expanding our reach. Autonomous vehicles can now map the seafloor without human control, and pressure-resistant sensors can record data for months or years before surfacing. These tools are slowly peeling back the layers of mystery, revealing glimpses of a world that was once beyond our imagination. Still, pressure ensures that progress remains slow. Every new depth reached reveals new obstacles. Every discovery opens new questions. And that is part of what makes the deep sea so compelling. It resists us. It humbles us. It reminds us that even here, on our own planet, there are places where the laws of physics themselves become barriers. Pressure is the great equalizer of the deep ocean. It shapes everything, from the smallest microbe to the tallest undersea mountain, from the structure of proteins to the flow of tectonic plates. It is the reason most of the ocean remains unseen, and it is the force that keeps much of its life beyond our reach. But pressure is not the only challenge. Even if we could build vessels strong enough to withstand it, even if we could send machines to any depth and bring them back unscathed, we would still face another obstacle: the sheer lack of structure and infrastructure in the deep sea. Unlike the land, which is crisscrossed by roads and dotted with settlements, the deep ocean offers no easy paths. It is a wilderness without roads, without markers, without places to stop and rest. And to explore it, we must learn how to navigate that emptiness. Even if we could banish the darkness with perfect light, and even if our machines could shrug off the immense pressure of the deep, we would still be faced with a problem that is subtler but no less daunting. The deep sea is a wilderness without roads. It is an environment with no natural pathways, no landmarks that remain visible, no places to pause or resupply, and no simple way to retrace one's steps. On land, exploration has always relied on pathways, whether natural or man-made. Rivers, valleys, and mountain passes guided early travellers. Roads, railways, and flight paths now link distant points across continents. Even in space, we chart trajectories with mathematical precision, plotting courses that allow spacecraft to slingshot from one gravitational well to another. The deep sea offers none of that. It is a place where direction is difficult, movement is costly, and the very act of exploration must be reinvented from the ground up. Consider for a moment how exploration works on land. If you want to study a rainforest, you can cut a path through the trees, build a camp and return to it again and again. If you want to map a desert, you can travel by vehicle guided by the horizon, by stars, by GPS. Even remote regions can be reached by aircraft or satellite imagery, which allow scientists to see and plan before they arrive. None of this is possible in the deep ocean. There is no horizon to navigate by. There are no fixed points visible from afar. Satellites cannot see through water, and light itself barely penetrates the upper layers. Even the seafloor, which lies just a few kilometers below us, is hidden behind a veil of darkness and density that our eyes cannot pierce. Every journey begins with uncertainty, and every mission must carry everything it needs from start to finish. Movement itself is a challenge. Water is not air, and the deeper you go, the more resistance it offers. On land, a vehicle can roll for hundreds of kilometers without refueling. In the air, an aircraft can cross oceans in hours. In the deep sea, a remotely operated vehicle may move only a few kilometers in an entire day. It must fight against currents, drag, and turbulence, all while tethered to a support ship far above. Even autonomous vehicles which roam freely without cables must conserve power, limiting how far and how long they can travel before returning to the surface. And because communication signals struggle to penetrate water, these vehicles must often operate without real-time control, navigating with pre-programmed instructions and limited feedback. This means that exploration is not just slow, it is uncertain. A vehicle may miss its target by hundreds of meters, arrive in a region that looks nothing like what was expected, or become lost altogether. Even when a vehicle reaches its destination, the challenges continue. On land, scientists can set up permanent field stations. They can leave instruments in place, return months or years later, and pick up where they left off. In the deep sea, every piece of equipment must be designed to withstand crushing pressure, corrosive salt water, and the relentless forces of currents and sediment. Moorings must be anchored securely to the seafloor, yet light enough to be retrieved. Instruments must function autonomously for months or years without maintenance, and even then, there is no guarantee they will still be there when scientists return. A single powerful current can dislodge equipment. Sediment can bury sensors. Marine life can interfere with instruments. Recovery missions sometimes find nothing but silence where a device once was. The absence of roads also complicates mapping and navigation. On land, we can triangulate positions using landmarks, satellites or radio signals. In the ocean, there are no landmarks, and GPS signals do not penetrate water. Instead, underwater vehicles rely on a combination of inertial navigation, sonar, and acoustic beacons. Inertial systems measure movement from a starting point, but even tiny errors accumulate over time, causing significant drift. Acoustic systems can correct these errors, but they require carefully placed beacons or transponders, which must be deployed ahead of time and recovered afterward. Each step adds complexity, cost, and potential failure points. And even when navigation is successful, the resulting maps are often incomplete or imprecise. Sonar can reveal the broad contours of the seafloor, but fine details, the ridges, canyons, and vents that shape deep-sea ecosystems, require close-up surveys that take time and effort. This lack of infrastructure means that every expedition into the deep sea is a standalone endeavour. On land, explorers can build on the work of those who came before. Roads and railways built centuries ago still guide modern travel. Spacecraft can use data from earlier missions to refine their trajectories. But in the deep sea, each mission must begin almost from scratch. A research vessel might spend weeks just reaching the study area and deploying equipment. Once there, scientists may have only a few days to gather data before weather, logistics, or funding forces them to leave. The next mission may not return for years, and when it does, currents may have shifted, landscapes may have changed, and previous markers may be gone. Continuity is rare, and cumulative progress is slow. This isolation extends to communication as well. On land, explorers can relay information instantly. Data flows in real time from remote sensors, drones, and satellites. In space, spacecraft transmit signals across millions of kilometers, allowing scientists to receive updates almost as they happen. In the deep sea, communication is far more limited. Radio waves are absorbed within centimeters of water. Optical signals, which rely on light, are scattered and absorbed within meters. Acoustic signals can travel farther, but they carry only limited data and are easily distorted. This means that deep-sea exploration is often a one-way conversation. Vehicles collect data silently and return it only after surfacing. By the time scientists see the results, the mission is already over. The absence of infrastructure also affects safety and recovery. On land, explorers in trouble can call for help, and rescue teams can arrive by road, air, or sea. In the deep ocean, help is far away. A vehicle that becomes stuck or disabled may be impossible to retrieve. A malfunction in a pressure hull or a leak in a submersible can become fatal within seconds. Even a minor mechanical failure can mean the loss of millions of dollars in equipment and years of work. And because every mission is remote and isolated, there is often little margin for error. Each decision must be made carefully, each risk weighed against potential reward. Funding is another challenge amplified by this lack of roads. Building infrastructure is expensive, but once it exists, it reduces the cost of future exploration. A road built once can be used by generations. A satellite launch today can support missions for decades. The deep sea has no such infrastructure. Every expedition requires a ship, a crew, specialized equipment, and extensive preparation. Costs are measured in millions of dollars, and because missions are rare and expensive, they must compete with other priorities. Space exploration, for example, benefits from global attention and funding, while deep-sea exploration often struggles for support. As a result, progress is incremental, and many questions remain unanswered simply because no one has been able to fund the journey to ask them. The deep sea's lack of roads also means that discoveries often cannot be revisited easily. A hydrothermal vent field discovered by one expedition may go unobserved for years, even decades, before another mission can return. In the meantime, the vent may change dramatically, or even cease activity altogether. Species observed once may never be seen again. Geological features may shift, collapse, or be buried. Each expedition is a snapshot, a moment in time rather than part of a continuous record. This makes it difficult to study long-term processes or understand how ecosystems evolve over time. This isolation also affects collaboration. On land, scientists from around the world can converge on a site, share equipment, and coordinate research. In space, agencies share data and resources to support missions. In the deep sea, collaboration is harder. Missions are tied to specific ships and schedules, and opportunities for joint work are limited. Even sharing data can be challenging, as the sheer volume of information collected, from sonar maps to video footage to biological samples, requires specialized infrastructure to store, process, and distribute. Without roads, both literal and metaphorical, the flow of knowledge is slower and more fragmented. It is important to remember that this is not simply a matter of technology. The deep sea's physical nature resists the very concept of roads. Water is fluid. It moves constantly, reshaping the environment in subtle ways. Sediment drifts and settles. Currents shift. Even if we could build permanent structures on the seafloor, they would face enormous challenges. Pressure would crush many materials. Corrosion would eat away at metals. Biological growth would coat and clog surfaces. And unlike land, where roads and buildings exist above the ground they serve, anything built in the deep sea must exist within the medium itself, exposed to all its forces at once. The result is that permanent infrastructure is rare and fragile, and most exploration remains transient by necessity. The absence of roads also shapes how we think about the deep sea. On land, maps and pathways allow us to conceptualize space. We can imagine where places are, how they connect, and how to move between them. In the deep sea, this mental map is harder to build. Features are vast and distant, separated by expanses of darkness and water. A trench here, a seamount there, a vent field somewhere in between. But the spaces between them are largely unknown. Our understanding is patchwork, and connecting the pieces into a coherent whole is one of the great challenges of oceanography. There have been attempts to overcome this. Networks of deep-sea observatories now dot parts of the ocean floor, connected by cables that provide power and communication. These stations collect data on temperature, currents, seismic activity, and biological processes, offering a continuous record that was once impossible. Autonomous vehicles roam vast areas, mapping terrain and recording data without direct human control. Swarms of smaller robots are being developed to work together, covering larger areas and sharing information. These innovations represent the first steps toward building something like infrastructure in the deep sea, but they are still rare, expensive, and limited in scope. The deep ocean remains overwhelmingly pathless. This pathlessness has scientific consequences beyond logistics. It influences the kinds of questions we can ask and the kinds of answers we can find. On land, infrastructure allows us to conduct large-scale experiments, monitor changes over time, and respond quickly to new discoveries. In the deep sea, our work is constrained by opportunity. We study what we can reach, when we can reach it, and often without the ability to return. This shapes our understanding in subtle ways. It biases our data toward the accessible and the visible. It leaves gaps that we may not even know exist. The deep sea's wilderness also shapes how life evolves. On land, roads and pathways can act as conduits for species, allowing them to spread and interact. In the deep ocean, isolation is the rule. Seamounts and vent fields are often separated by vast distances, creating pockets of habitat that may remain cut off from one another for millennia. This isolation drives evolution in unique directions, producing species found nowhere else on Earth. It also makes ecosystems fragile. A disturbance in one location may not be repopulated from another. Recovery can take centuries, if it happens at all. It is tempting to imagine that as technology advances, this wilderness will shrink. That roads, literal or metaphorical, will eventually crisscross the deep sea. And in some ways this may happen. Autonomous vehicles will grow more capable. Networks of sensors may become more widespread. Our maps will improve. But the deep sea will never become easy. Its size, its darkness, its pressure, and its dynamic nature ensure that it will always resist simplification. And perhaps that is as it should be. Wilderness is not merely an absence of roads, it is a presence of complexity, of unpredictability, of the unknown. The deep sea is a wilderness not because we have failed to tame it, but because it is, by its nature, untamable. And so the absence of roads is not just a barrier, it is part of what makes the deep sea what it is. It is why exploration remains difficult and slow. It is why discoveries still surprise us, and why questions still outnumber answers. It is why, even in the 21st century, the deep ocean remains one of the last great frontiers on Earth. But this wilderness also points to another challenge, one that is as much about our own limitations as it is about the oceans. Because even if we could navigate this pathless expanse with ease, even if we could map every trench and seamount, we would still face a problem closer to home. The tools we have built to explore the deep sea are still far from equal to the task. Even if we could somehow navigate the pathless wilderness of the deep sea with perfect ease, there remains an obstacle that is perhaps more revealing of our limitations than any physical barrier. Our tools are still not ready for this world. Human technology has carried us to the moon, landed rovers on Mars, sent probes beyond the solar system, and mapped the structure of the universe itself. Yet when it comes to the deep sea, a realm just a few kilometers below our feet, our machines falter. They creak under pressure, stumble in darkness, lose their way in shifting currents, and break down in conditions they were never built to endure. This is not because scientists are careless or engineers unimaginative. It is because the deep ocean is a fundamentally different environment from anything else we explore, and our tools, even the best we've built, are still designed with other worlds in mind. To understand the nature of this technological gap, it helps to start with the basics. Water, as a medium, is far more difficult to work in than air or vacuum. It is dense and heavy. It resists movement. It absorbs and scatters light. It blocks radio waves. It corrodes metals. It exerts pressure that increases steadily and dramatically with depth. Every property that makes the deep sea what it is also makes it hostile to our machines. Even something as simple as communication becomes a major engineering challenge. On land, we send data instantly through radio signals. In space, those signals travel across billions of kilometers, but water absorbs them within centimeters. This means that most deep-sea vehicles cannot communicate directly with the surface in real time. Instead, they must rely on acoustic signals, which travel far better in water but are much slower and carry far less data. A radio signal moves at the speed of light and can transmit gigabytes per second. A sound wave moves at about 1,500 meters per second and carries only a fraction of that information. This drastically limits what a deep-sea vehicle can send or receive while it's operating, making remote control, imprecise and detailed data collection challenging. Power is another fundamental problem. Most deep-sea vehicles rely on batteries, but energy storage is heavy and limited. The deeper a vehicle goes, the more energy it needs to fight pressure, resist currents, and power lights, cameras and instruments. Recharging batteries underwater is complex and often impossible, which means vehicles must return to the surface frequently, wasting time and reducing the amount of data they can collect. Some experimental systems use tethered power cables, drawing electricity from the ship above, but these cables are bulky, fragile, and limit how far the vehicle can travel. Nuclear power, which fuels some spacecraft for decades, is rarely used in the ocean due to safety concerns and regulatory restrictions. As a result, most deep-sea missions are constrained by energy budgets that would seem absurd in space exploration. A Mars rover can operate for years. A deep-sea robot might last only a few hours before it has to ascend and recharge. Materials science presents another major hurdle. At the surface, pressure is about 1 atmosphere. At 1,000 meters, it's around 100 atmospheres. At the deepest known point, more than 11,000 meters down, pressure exceeds 100 atmospheres, more than 16,000 pounds per square inch. Few materials can withstand such forces without deforming, cracking, or collapsing. Traditional engineering approaches, thicker walls, stronger metals, quickly reach their limits. Doubling the strength of a pressure vessel often means doubling its weight, and in water, weight is a critical constraint. Heavier vehicles require more buoyancy, more power, and more support from the ships above. Each solution creates new problems, and the deeper we go, the more complex those problems become. Even when materials survive the pressure, they must also resist corrosion. Salt water is an aggressive solvent. It corrodes metals, degrades seals, and infiltrates electronics. Protective coatings can slow the process, but over long missions, corrosion remains a serious risk. And because deep-sea missions are often expensive and infrequent, equipment may sit unused for months or years between deployments, giving salt and moisture time to do their work. Maintenance becomes a constant battle, and even small leaks or cracks can compromise an entire mission. Sensors and instruments too face unique challenges. Measuring temperature, salinity, pressure, and chemical composition is straightforward in shallow water. In the deep sea, instruments must function under immense pressure and extreme cold, often near freezing. Delicate components must be protected without losing sensitivity. Optical instruments must operate in total darkness. Acoustic sensors must filter out noise from currents, marine life, and even the ship above. Cameras must provide clear images despite sediment, darkness, and distance. And because every bit of equipment adds weight, size, and power demand, engineers must balance precision against practicality. The result is that many deep-sea instruments are compromises, good enough to function, but far from ideal. Navigation is another fundamental problem that exposes the technology gap. GPS signals, which make navigation trivial on land and in the air, cannot penetrate water. Instead, deep-sea vehicles must rely on inertial navigation, acoustic positioning, or dead reckoning, all of which are less accurate and more prone to drift over time. Even small errors can accumulate into significant deviations. A vehicle travelling just a few kilometres might miss its target by hundreds of metres. Scientists compensate by deploying acoustic transponders on the seafloor, which create a kind of underwater GPS. But these systems require careful setup, add cost, and work only in limited areas. For wide-ranging missions, navigation remains a major challenge. Even something as seemingly simple as data storage and retrieval becomes difficult in the deep sea. High-resolution sonar maps, video footage, and sensor readings generate vast amounts of data, but transmitting that data through water is slow and unreliable. Most vehicles must store their data on board and upload it only after surfacing. This means scientists cannot analyze information in real time or adjust their missions based on what they learn. If a vehicle misses something important, a vent field, a rare animal, a geological feature, there may be no way to go back and investigate before the mission ends. In space, we can send new commands to a probe on Mars in minutes. In the deep sea, we often must wait hours or days for a vehicle to return before we know what it has found. Cost amplifies all of these challenges. Building and operating deep-sea vehicles is expensive. Research vessels cost tens of thousands of dollars per day to operate. Submersibles and remotely operated vehicles cost millions to build and maintain. Every dive requires a skilled crew, specialized equipment, and careful planning. Weather delays, equipment failures, and unforeseen complications can add days or weeks to a mission. And because funding for ocean exploration is often limited, many missions are one-time efforts. Once they're over, the equipment may sit idle for years before it's used again, if it's used at all. This financial reality creates a feedback loop that slows progress. Because missions are expensive, there are fewer of them. Because there are fewer missions, there is less data. Because there is less data, it's harder to justify the cost of building better technology. And because better technology is rare, missions remain expensive. Breaking this cycle requires sustained investment and collaboration, but such support is often hard to secure. Space exploration captures the public imagination and political will. Deep-sea exploration, by contrast, happens largely out of sight and out of mind. Its discoveries, while scientifically profound, rarely make headlines. As a result, funding often lags far behind the need. Yet for all these challenges, progress is being made. Advances in material science are producing lighter, stronger pressure vessels. New battery technologies promise longer missions and greater range. Improvements in acoustic communication are increasing data transmission speeds. Autonomous vehicles are becoming smarter, able to make decisions on their own and adapt to changing conditions. Swarms of small robots are being developed to work together, covering larger areas and sharing information. These innovations are slowly expanding our reach into the deep, but they remain limited compared to what we might one day achieve. One promising development is the use of fiber optic tethers, which can transmit vast amounts of data quickly and reliably between a deep-sea vehicle and a surface ship. These tethers allow for real-time control and high-resolution video streaming, enabling scientists to react immediately to what they see. However, Fibre optic cables are delicate and expensive, and deploying them thousands of meters below the surface is a complex and risky task. A single snag on the seafloor can end a mission. As a result, fibre optic tethers are used sparingly, and usually only on large, well-funded expeditions. Another area of innovation is artificial intelligence. Deep-sea vehicles equipped with AI can analyze data as they collect it, adjusting their missions without waiting for human input. They can recognize patterns, identify interesting features, and prioritize tasks in ways that were once impossible. This not only improves efficiency, but also allows vehicles to operate longer and cover more ground. Still, AI is not a cure-all. It requires powerful processors which consume energy and generate heat, both of which are scarce resources in the deep sea. And while AI can make decisions, it still depends on sensors and instruments that are subject to the same physical limitations as before. Even with these advances, the gap between what we can do and what we need to do remains wide. Consider the scale of the challenge. The average depth of the ocean is about 3,700 meters. The deepest point is over 11,000 meters. The total volume of water is about 1.35 billion cubic kilometers. Mapping all of that at high resolution would require millions of missions and centuries of work with current technology. Even mapping just the seafloor in detail, a relatively modest goal, would require thousands of ship years and billions of dollars. By comparison, we have mapped the surface of Mars, a planet tens of millions of kilometers away, in greater detail and in far less time. The reasons for this disparity go beyond physics and engineering. They also reflect our priorities. Space exploration benefits from decades of sustained investment, driven by geopolitical competition, scientific ambition, and public fascination. Deep-sea exploration has rarely enjoyed the same level of attention. Its missions are often smaller, shorter, and less frequent. Its discoveries, though scientifically important, rarely inspire the same wonder as images of distant planets. And because it lacks the infrastructure that space exploration enjoys, from launch facilities to satellite networks, each mission must build much of its support from scratch. Still, there are reasons for optimism. International collaborations are growing, bringing together resources and expertise from around the world. Commercial interest in deep-sea mining, though controversial, is driving investment in new technologies. Advances in robotics, sensors, and communication are opening possibilities that were unimaginable just a few decades ago. And a growing awareness of the deep ocean's importance to climate, biodiversity, and the health of the planet is beginning to shift public and political attention toward this hidden realm. Yet even as technology improves, it will never eliminate the challenges of the deep sea entirely. Water will always absorb light and block radio waves. Pressure will always rise with depth. Corrosion will always threaten metals. These are not problems to be solved, but realities to be managed. Our tools will get better, but they will always operate within the constraints of the environment. The deep sea will always demand more from our machines than space or land ever has, and it will always remind us that technology, no matter how advanced, has limits. And perhaps that is part of the deep sea's enduring mystery. It resists mastery. It humbles our tools and tests our ingenuity. It forces us to confront the fact that exploration is not simply about building better machines, but about understanding and adapting to the environments we enter. The deep sea is not waiting passively for us to arrive. It is actively shaping the way we must approach it, and in doing so, it teaches us new ways of thinking about exploration itself. Even with the best technology, however, there is still one more obstacle that must be faced. Because beyond the pressure, beyond the darkness, beyond the absence of roads and the limitations of our machines, there is a question of life itself. What survives in this place? How does it endure conditions so extreme that they defy our understanding of biology? And what can those forms of life teach us, not only about the deep sea but about life on Earth, and perhaps beyond it? Even with all our struggles against darkness, pressure, distance, and technological limits, the story of the deep sea would remain incomplete without considering the life that calls it home. For if anything truly defines this vast hidden world, it is the astonishing fact that life not only exists there but thrives in forms and ways so unfamiliar that they seem to belong to another planet. The Midnight Zone, that vast expanse below 1,000 meters, where sunlight has never reached, is not barren or empty. It is alive, it is crowded, it is vibrant in its own strange, muted way. It is home to some of the most bizarre and extraordinary creatures ever discovered, beings that have evolved in isolation from the surface world, shaped by pressures and conditions that would destroy most life forms we know, and the more we learn about them, the more they challenge everything we thought we understood about what life can be. To appreciate how remarkable this is, consider the conditions these creatures endure. Light is absent, so photosynthesis is impossible. Temperatures hover near freezing, usually between 2 and 4 degrees Celsius. Pressure is hundreds of times greater than at the surface. Food is scarce, often arriving only as tiny flakes of organic debris falling slowly from above, a constant drizzle of what scientists call marine snow. And yet, in this world that seems so inhospitable, life has found countless ways to adapt. It is as if evolution, faced with the most extreme constraints imaginable, responded not with surrender but with creativity. One of the most striking examples of adaptation is bioluminescence, the ability to produce light through chemical reactions. In the Midnight Zone, bioluminescence is everywhere. It is estimated that as much as 90% of the organisms here can produce light in some form. Some emit brief flashes to startle predators or attract mates. Others produce steady glows to lure prey or communicate with their kind. Still others use bioluminescence as camouflage, matching the faint light filtering down from above so they disappear from view when seen from below. This phenomenon, known as counter-illumination, is one of the most effective survival strategies in the deep. Tiny photophores, light-producing organs, dot the bodies of fish and squid, allowing them to control the brightness and even the colour of their light with remarkable precision. The anglerfish is perhaps the most iconic example of deep-sea bioluminescence. With its gaping mouth and needle-sharp teeth, it already looks otherworldly. But what truly sets it apart is the luminous lure that extends from its forehead, a modified fin spine tipped with a glowing bulb. This light is produced not by the fish itself, but by symbiotic bacteria that live inside the lure, fed by the fish in exchange for their glow. Prey, drawn to the mysterious light in the darkness, swim close, and are instantly engulfed by the anglerfish's enormous jaws. It is a strategy so effective that anglerfish rarely need to move. They simply hang motionless in the water, mouths open, waiting for dinner to come to them. Bioluminescence is not limited to predators. Some prey species use it as a defense, releasing glowing clouds to distract or confuse attackers. Others produce sudden flashes to startle predators, much like a camera flash in a dark room. Some squid can even eject bioluminescent mucus, creating glowing decoys that continue to pulse and drift as they escape. This biological light show is a fundamental part of life in the Midnight Zone. Not a rare feature, but a universal language. It replaces colour, which is meaningless in darkness, and serves as communication, camouflage, lure and alarm all at once. Physical adaptations are equally extraordinary. Pressure in the Midnight Zone is immense, yet animals here show no signs of stress. Their bodies are soft and flexible, lacking the gas-filled spaces that would collapse under pressure. Swim bladders, which help fish control buoyancy in shallower waters, are absent or replaced by oil-filled sacs. Bones are reduced or eliminated altogether. Many creatures have gelatinous bodies that compress easily without damage. Some are so delicate that they disintegrate when brought to the surface, their structures unable to withstand the sudden drop in pressure. One of the most remarkable of these adaptations is found in the snailfish, which inhabits trenches more than 8,000 meters deep. Its body is soft and scaleless, its bones reduced to cartilage. It has no swim bladder. Its enzymes and proteins are specially adapted to function under immense pressure, and its cells contain high levels of piezolites, molecules that protect cellular structures from compression. The snailfish is not merely surviving in these conditions, it is thriving. It is a top predator in its environment, feeding on crustaceans and other invertebrates that live in the sediment, yet it cannot survive at the surface. Remove it from its pressurized home and its body collapses. It is a creature truly of the deep, incapable of existing anywhere else. Other species have evolved sensory adaptations that seem almost magical. In the absence of light, vision becomes less important and other senses take over. Some deep-sea fish have highly developed lateral lines, sensory organs that detect vibrations and movement in the water. Others rely on chemoreception, sensing chemical cues to locate prey or mates. Some have retained and even enhanced their vision, evolving enormous eyes capable of detecting the faintest glimmers of light. The colossal squid, for example, has eyes the size of dinner plates, the largest of any known animal, allowing it to detect the faint bioluminescence of prey or predators hundreds of meters away. Other species, like the barrel-eye fish, have transparent heads and upward-facing eyes that can swivel within their sockets, scanning for silhouettes against the faint glow above. Morphologically, the creatures of the midnight zone often look so alien that early scientists who dredged them up were unsure whether they were even animals. Many are elongated and eel-like, maximizing their ability to sense vibrations and currents. Some have enormous mouths and distensible stomachs, allowing them to swallow prey nearly as large as themselves. A crucial advantage in an environment where meals are rare and unpredictable. The gulper eel, with its vast balloon-like mouth, is a prime example. Others, like the viperfish, have needle-like teeth so long they cannot close their mouths. These adaptations, though grotesque by surface standards, make perfect sense in the deep. They allow predators to seize and consume whatever prey they encounter, regardless of size. The scarcity of food in the midnight zone has driven some species to extraordinary lengths in their reproductive strategies as well. The anglerfish, for example, has one of the most bizarre mating systems known to science. Males are tiny compared to females, sometimes less than 1/10 their size. When a male encounters a female, he bites into her skin and fuses with her body, connecting to her bloodstream and becoming a permanent parasite. Over time, he loses his eyes, fins, and internal organs, existing only as a source of sperm when she needs to reproduce. This strategy ensures that when a female encounters a rare mate in the vastness of the deep sea, she never loses him. It is an extreme solution to the problem of distance and scarcity, and it illustrates how deeply life in the midnight zone is shaped by its environment. Other species rely on mass spawning, releasing enormous numbers of eggs and sperm into the water in the hope that some will meet and survive. Some brood their young internally, while others attach eggs to the seafloor or to their own bodies. Many deep-sea organisms have long lifespans and slow reproductive rates, reflecting the stability of their environment and the scarcity of resources. Some corals and sponges in the deep ocean are thousands of years old, growing millimetre by millimetre over centuries. Their age is a testament to the patience and persistence of life in a world where time moves differently. The base of the food web in the midnight zone is equally fascinating. Most life here depends on detritus falling from above, a slow rain of dead plankton, fecal pellets, and other organic matter that drifts down from the surface. This marine snow is the primary source of energy for countless deep-sea organisms, from tiny bacteria to massive scavengers like amphipods and sea cucumbers. Some species migrate upward at night to feed in more productive waters, then return to the depths during the day, a vertical journey that constitutes the largest daily migration on Earth. Others rely on carrion, the occasional carcass of a whale or large fish that sinks to the seafloor, providing a sudden, massive infusion of nutrients. A single whale fall can support an entire community of organisms for decades, as bacteria, scavengers, and predators move in to feed and reproduce. Yet not all life in the midnight zone depends on the surface. Around hydrothermal vents and cold seeps, places where chemical-rich fluids flow from the seafloor, entire ecosystems thrive in complete isolation from sunlight. Here, bacteria use chemosynthesis to convert chemicals like hydrogen sulfide and methane into energy, forming the base of a unique food web. These bacteria are eaten by worms, clams, and shrimp, which in turn support larger predators. Some species live in symbiosis with the bacteria, housing them within their bodies and relying on them for nourishment. The giant tube worm, for example, has no mouth or digestive system. Instead, it contains billions of symbiotic bacteria that convert the chemicals from the vent fluid into food. These ecosystems are among the most productive on Earth, rivaling rainforests in their biomass, and they exist in total darkness, fueled not by sunlight but by the heat and chemistry of the Earth itself. The discovery of these vent communities in the late 1970s revolutionized our understanding of life. Until then, scientists believed that all ecosystems ultimately depended on sunlight. The existence of thriving communities powered by chemical energy showed that life could exist entirely independent of the sun. This realization had profound implications, not only for biology, but for our search for life elsewhere in the universe. If life can flourish in the crushing darkness of the deep ocean, fed by chemical reactions rather than sunlight, then perhaps it can exist beneath the icy crust of Europa or Enceladus, moons thought to harbour subsurface oceans. Perhaps it can survive beneath the thick atmospheres of distant exoplanets. The deep sea is not just a hidden part of our own world. It is a window into what life might look like anywhere in the cosmos. Despite these revelations, our understanding of life in the midnight zone is still rudimentary. Most species remain undiscovered. Those we know are often known only from a single specimen, dredged from the depths and preserved in a jar. Their behaviours, life cycles, and interactions remain mysteries. Even the basic diversity of life in the deep ocean is unknown. Estimates suggest that as much as 2/3 of deep-sea species have yet to be described. Some scientists believe that the deep sea may harbour more biodiversity than all of Earth's rainforests combined. And yet, because exploration is so difficult, we have only begun to scratch the surface. This ignorance is not just a matter of curiosity. It has real consequences. Deep-sea organisms produce unique biochemical compounds that could have medical or industrial applications. Enzymes from deep-sea bacteria are used in biotechnology. Molecules from deep-sea sponges have shown promise as anti-cancer agents. Studying how deep-sea organisms cope with pressure, cold, and darkness could lead to new materials, new technologies, and new insights into the limits of life. But we cannot harness what we do not understand, and we cannot protect what we do not know exists. The deep sea is increasingly threatened by human activities, from deep-sea mining to pollution to climate change, and without a deeper understanding of its ecosystems, we risk destroying them before we ever comprehend their value. Even the basic relationships between species are poorly understood. On land, ecologists can study how predators and prey interact, how plants and animals shape each other's evolution, and how ecosystems respond to change. In the deep sea, these relationships are often invisible. We know that predators exist, but we rarely see them hunt. We know that scavengers feed on carcasses, but we rarely observe how they arrive or compete. We know that vent communities thrive, but we know little about how they form, how they disperse, or how they change over time. Each observation is a clue, but the full picture remains elusive. The creatures of the midnight zone also challenge our assumptions about beauty and value. Many are grotesque by human standards, all teeth and translucent flesh and gelatinous forms, yet they are perfectly suited to their world, their strange appearances the result of millions of years of adaptation. Some are elegant in their simplicity, drifting effortlessly through the water. Others are intricate in their complexity, bristling with sensors, lights, and appendages. Together, they represent the astonishing creativity of evolution, which finds solutions even in the harshest conditions. And perhaps most remarkable of all is how much of this world remains hidden from us. Every deep-sea expedition brings new discoveries, new species, new behaviours, new ecosystems. In some cases, scientists have recorded dozens of new species on a single dive. And yet, for every discovery made, countless others remain beyond our reach. The Midnight Zone is vast beyond comprehension, covering most of the planet and representing the majority of its living space. It is a realm we have barely begun to explore. The existence of such extraordinary life in such an extreme environment is a humbling reminder of how adaptable and resilient life can be. It shows us that life does not need sunlight, or warmth, or abundance. It needs only the right conditions and enough time to evolve solutions. And it suggests that Earth's biosphere is far larger and more complex than we once believed, not confined to the thin skin of land and atmosphere we inhabit, but extending deep into the planet's hidden realms. Yet even with all we have learned about the life that thrives in darkness and pressure, the deep sea continues to defy us, because beyond the biology lies something even more elusive, the sheer depth of our ignorance. For every mystery solved, another emerges. For every question answered, new ones appear. And nowhere is this truer than in the strange and shifting border between what we understand and what remains hidden. A place where science and mystery intertwine, and where the limits of our knowledge are laid bare. For all the astonishing life we have glimpsed in the deep, for all the ingenuity of the creatures that thrive in the Midnight Zone, what is perhaps most striking is how little of this world we actually understand. The deeper we go, the more we realise that the deep sea is not merely a physical frontier, it is an intellectual one, a place where the limits of our science become painfully clear, and where mystery is not an obstacle to knowledge, but a constant companion. We know enough now to understand just how vast our ignorance still is, and nowhere else on Earth is the gap between what we know and what we don't as wide as it is beneath the waves. It begins with the most basic of questions. How much life is down there? We do not know. Estimates vary wildly, but most scientists believe that the vast majority of Earth's species remain undiscovered, and many of them are likely to live in the deep sea. Every expedition uncovers new organisms, many of them so unlike anything known that they cannot easily be classified. Some exist only as a single specimen dredged from the depths. Others are known only from fragments, a few cells of DNA caught in a water sample, a strange trace left on the sea floor. These hints suggest that deep-sea biodiversity is not just high. It may exceed that of all terrestrial ecosystems combined. Yet without systematic exploration, these are only guesses. Our sampling is too sparse, our observations too brief, our coverage too incomplete. We are trying to count stars in the sky by looking through a pinhole. Even among the species we have discovered, our knowledge is often shallow. We know what they look like, but not how they live. We can describe their anatomy, but not their behaviour. We know where they were found, but not how far they roam. Consider the anglerfish, one of the most iconic deep-sea predators. We have studied its morphology, and even unravelled the genetic basis of its bizarre reproductive system. Yet we have never observed many of its behaviours in the wild. We do not know how it hunts in its natural habitat, how it chooses mates, or how it interacts with other species. Our understanding of its life is pieced together from specimens hauled to the surface and from rare glimpses caught by remotely operated vehicles. Fleeting, fragmentary moments that cannot capture the full complexity of its existence. This ignorance extends to the ecosystems of the deep sea as well. We know that hydrothermal vents support thriving communities, but we do not fully understand how those communities form, how they evolve, or how they spread from one vent field to another. The vents themselves are ephemeral, often active for only decades or centuries before shutting down. How do species migrate between them across the vast empty seafloor? How do they colonize new vents when they appear? What happens to the communities when the vents go cold? These are fundamental questions about the dynamics of deep-sea life, and yet they remain largely unanswered. We also know little about the role the deep sea plays in global processes. The ocean is Earth's largest carbon sink, absorbing and storing vast amounts of carbon dioxide from the atmosphere. Much of this carbon ends up in the deep sea, where it can remain for centuries or millennia. But how exactly does this process work? How does carbon move from the surface to the depths, and how is it transformed along the way? What role do deep-sea organisms play in sequestering or releasing carbon? How might climate change alter these processes? These are not trivial questions. They are central to our understanding of Earth's climate system and our ability to predict its future. Yet our data are sparse and our models incomplete. The deep ocean, which covers more than 2/3 of the planet, remains a black box in our climate calculations. The geology of the deep sea is no less mysterious. We know that mid-ocean ridges create new seafloor as tectonic plates pull apart, and that trenches consume old crust as plates collide and subduct. But the details of these processes are often hidden from us. Volcanic eruptions on the seafloor are frequent. Some estimates suggest they occur more often than eruptions on land. Yet we have witnessed only a handful of them. Most go undetected, their evidence discovered only long after the fact. Earthquakes rattle the deep ocean, triggering submarine landslides that reshape the seafloor and generate tsunamis. But we rarely record them in detail. Even the structure of the oceanic crust itself is poorly mapped. We know more about the surface of Mars than about the geology beneath our own seas. Sediments too hold secrets we have barely begun to explore. Layer upon layer of fine particles settle on the seafloor over millions of years, recording a history of Earth's climate, volcanic activity, and even biological evolution. These sediments are like pages in a book, each one holding clues to the past. But our sampling is limited. We have drilled cores from a few locations, but vast areas remain untouched. What stories might lie buried in those sediments? What ancient climates? What mass extinctions? What evolutionary transitions are recorded there? The answers remain hidden beneath kilometres of water and metres of mud. Even the physics of the deep ocean, the way water moves, mixes and circulates, is incompletely understood. Ocean currents transport heat, nutrients and carbon around the globe, shaping weather patterns and sustaining life. Some of these currents, like the Gulf Stream, are well studied. Others, especially those in the deep ocean, are not. We know they exist, but their pathways, speeds and variability remain uncertain. We do not fully understand how they respond to changes in temperature and salinity, or how they might shift as the climate warms. These deep currents are like the planet's circulatory system, and yet we are only beginning to trace their veins and arteries. The twilight between science and mystery is not just about what we do not know. It is also about what we think we know, but may be wrong about. For example, we once assumed that the deep sea was a stable environment, unchanging over long periods. It seemed reasonable, without sunlight, without seasons, without weather. What could change? But new research suggests that the deep ocean is far more dynamic than we believed. Currents shift, sediments move, hydrothermal vents flare and fade. Even the distribution of life changes over surprisingly short timescales. Some species migrate vertically by hundreds of meters each day, following food sources that rise and fall with the sun. Others move horizontally over vast distances, carried by currents or driven by subtle chemical cues. These discoveries challenge long-held assumptions and remind us that the deep sea is not a static repository of secrets, but a living, changing world. Another assumption under scrutiny is our understanding of how deep-sea ecosystems connect to one another. For decades, scientists believed that many deep-sea habitats were isolated, separated by vast distances of empty water and sediment. But new evidence suggests that connections may exist in ways we did not anticipate. Genetic studies reveal that populations separated by thousands of kilometers may still exchange genes, suggesting hidden pathways of dispersal. chemical signals may travel farther and more effectively than we imagined, guiding organisms across seemingly featureless expanses. Even physical structures like seamount chains may act as stepping stones for species migration. If these connections are real, they have profound implications for how deep-sea ecosystems function and how they might respond to change. Our ignorance extends even to fundamental definitions. What exactly is a species in the deep sea? Traditional definitions based on physical characteristics often fail here. Many deep-sea organisms are known from only a handful of specimens, making it difficult to determine whether differences are variations within a species or evidence of entirely new ones. Genetic studies have revealed hidden diversity, cryptic species that look identical but are genetically distinct. In some cases, what was once thought to be a single widespread species turns out to be dozens of separate lineages, each confined to a specific region or depth. This hidden diversity complicates everything from ecological studies to conservation planning, and it underscores how much we have yet to learn. The twilight zone of knowledge is not limited to biology, geology, or physics. It also encompasses the role of the deep sea in Earth's broader systems. The ocean stores more heat than the atmosphere and land combined, and much of that heat is absorbed and transported by deep currents. But how quickly does this heat move? How does it interact with other components of the climate system? How might changes in deep circulation affect surface temperatures, weather patterns, or sea level rise? These are critical questions in an era of rapid climate change, yet our understanding of them remains rudimentary. We are trying to predict the future with incomplete equations. Even the chemistry of the deep sea holds mysteries. We know that hydrothermal vents release metals and minerals that play a crucial role in ocean chemistry, but we do not fully understand how these materials disperse or how they influence marine life. We know that methane seeps can release vast quantities of greenhouse gases, but we do not know how stable these seeps are, or how they might change in a warming world. We know that the deep sea stores vast amounts of carbon, but we do not know how secure that storage is, or what might release it. Each of these unknowns carries potential consequences for the planet as a whole. And then there are the mysteries that we cannot even frame as questions yet. Every deep-sea expedition seems to uncover something unexpected. A new species, a new geological feature, a new chemical process. Some discoveries defy explanation entirely. Strange gelatinous blobs that do not fit into any known category. Mysterious sounds that echo through the water, their sources unknown. Sudden blooms of microbial life in places where none were expected. These are not just curiosities. They are reminders that the deep sea is not simply unexplored, but fundamentally underexplained. We do not yet know what we do not know. This twilight between science and mystery is not a failure of science. It is the nature of exploration. Science thrives on the unknown. It advances by probing the edges of ignorance, by asking questions we cannot yet answer. The deep sea is simply an environment where those edges are vast and close together. It is a place where every answer leads to more questions, where certainty is rare and temporary. And that is what makes it so exciting. The mysteries of the deep sea are not static gaps waiting to be filled. They are dynamic frontiers that expand as we approach them. But this also means that our relationship with the deep sea must remain one of humility. We cannot assume that we understand what we are seeing. We cannot assume that patterns observed in one place apply everywhere. We cannot assume that what seems insignificant today will remain so tomorrow. The deep sea has a way of overturning our assumptions, of revealing complexity where we expected simplicity, of showing us that the universe is more inventive than we are. It teaches us to question not only what we know, but how we know it. And this twilight between knowledge and mystery extends beyond science itself. It shapes how we think about exploration, about discovery, about our place on this planet. The deep sea is a reminder that Earth is not fully known, that mystery still exists not just in the distant cosmos, but here, beneath our feet. It reminds us that exploration is not something that belongs to the past, a story of ancient navigators and forgotten frontiers. It is a living, ongoing process, one that is happening right now in places we have yet to reach. Even our myths and imaginations have long reflected this sense of mystery. Long before scientists began probing the depths with sonar and submersibles, humans were telling stories about what lay beneath the waves. Stories of monsters and lost worlds, of gods and spirits, of realms beyond human reach. These myths were often born of ignorance, but they also reflected a deeper truth, that the ocean has always been a symbol of the unknown. And even now, with all our science and technology, that unknown remains. It has simply changed its shape, from sea serpents and krakens to microbial ecosystems and carbon cycles. The mystery persists. It is woven into the fabric of the deep, and perhaps that is the greatest lesson the deep sea offers. It shows us that mystery is not something to be feared or dismissed. It is something to be embraced, not as a sign of failure, but as a sign that there is more to learn, more to discover, more to understand. It reminds us that the world is not finished, that our knowledge is not complete, that there are still places where wonder and curiosity have work to do. The twilight between science and mystery is not a barrier. It is an invitation. But this invitation is not new. Humanity's fascination with the deep sea stretches back far beyond the age of sonar and satellites, beyond the first submersible dives, beyond even the earliest scientific expeditions. Long before we had the means to explore it, we imagined it. We filled it with gods and monsters, with cities and kingdoms, with stories that reflected our hopes and fears. And those ancient myths shaped how we think about the deep even today. To understand why the deep sea remains such a powerful symbol of mystery, and why it has resisted our attempts to know it, we must look back to those early imaginings and see how they continue to shape our relationship with the abyss. Long before sonar beams pulsed through seawater, before submersibles crawled down into black trenches, before scientists argued over biogeochemical cycles or deep-sea microbial mats, humanity had already filled the ocean with stories. The abyss has always lived in our imaginations, even when it was far beyond our reach. We feared it, revered it, personified it. We believed it was home to gods and monsters, that it contained the entrances to other worlds, that it was both cradle and grave. And although we now know that much of what those stories contained was fantasy, they still matter deeply because they reveal something fundamental about the way we relate to the unknown. They show that long before the deep sea was a scientific frontier, it was a psychological one, a canvas on which humans projected their deepest fears, desires, and questions. The earliest human encounters with the ocean were necessarily shallow. Fishermen and sailors of the ancient world knew the surface intimately, its winds and currents, its moods and seasons. They saw storms rise without warning and ships disappear without a trace. They watched whales breach and vanish again into the depths. They pulled fish and strange creatures from the water, some beautiful, some grotesque, all mysterious. But they could not see beneath the waves. The ocean's surface was a mirror that reflected only the sky, hiding everything below, and so, in the absence of knowledge, imagination stepped in. Nearly every culture on Earth developed myths about what lay beneath the sea, and though the details varied, certain themes repeated again and again. The ocean was often seen as primordial, the source from which the world emerged. In ancient Mesopotamian mythology, the goddess Tiamat embodied the chaotic waters that existed before creation. Her body was split by the god Marduk to form the heavens and the earth. In Greek mythology, the primordial deity Pontus personified the sea, and from him sprang many of the sea's divine inhabitants. The Bible speaks of the deep, the Tehom, as the dark, watery void from which God created the world. These stories reflect a deep intuition that the ocean, vast and inscrutable, is not just part of the world but its origin. At the same time, the sea was often associated with chaos and danger. a place where order breaks down and human power is meaningless. Ancient sailors feared sea monsters like Leviathan and Rahab in Hebrew tradition, Tiamat's monstrous offspring in Mesopotamian lore, or the Greek Ketos, slain by Perseus to save Andromeda. These creatures embodied the unknown and the uncontrollable. They were the living symbols of a realm that could swallow ships whole and erase them from memory. Even when people did not believe in literal monsters, they spoke of the sea itself as alive, a capricious being that could nurture or destroy depending on its mood. Other myths imagined the deep as a realm of death and the afterlife. In Japanese folklore, the sea goddess Watatsumi ruled a palace beneath the waves, a place where the souls of the drowned might dwell. The ancient Greeks believed that Oceanus, the great river that encircled the world, lay beyond the known lands and led to the realm of the dead. In Norse mythology, the serpent Jörmungandr coiled around the world beneath the sea, destined to rise and bring about Ragnarok, the end of all things. The deep was not just a physical place, it was a threshold between worlds, between life and death, order and chaos, the known and the unknown. These stories were not naive misunderstandings of the ocean. They were attempts to grapple with something that was, and still is, profoundly alien to human experience. The deep sea defies the senses. It is invisible, intangible, unknowable. It swallows light, sound, and even memory. To stand on a shore and gaze out at the horizon is to confront infinity, not the infinity of the stars, which we can at least see, but a more immediate, more intimate infinity that begins just beyond the breakers. Ancient myths gave shape to that infinity. They allowed people to name and narrate what they could not see. They transformed the ocean from an incomprehensible void into a realm populated by beings and stories, giving it meaning even as it remained mysterious. Over time, as seafaring technology improved and exploration expanded, myths evolved. The Greeks imagined Oceanus not just as a god, but as a vast river that flowed around the known world. Medieval Europeans placed sea serpents and monstrous fish on their maps, warning sailors of dangers that might lurk in uncharted waters. Polynesian navigators, who travelled thousands of miles across the Pacific, developed oral traditions that blended myth with practical knowledge, encoding navigation techniques and ecological observations in stories of gods and spirits. Even as people learned more about the ocean's surface, the deep remained beyond their reach, and so it remained the domain of myth. The Enlightenment began to change that. As science advanced, curiosity about the deep ocean grew. Naturalists and explorers began to ask whether the creatures of myth had any basis in reality. Expeditions dredged the seafloor, bringing up bizarre animals that seemed to confirm that the ocean did indeed harbour strange life. Some early scientists believed that no life could exist below a few hundred metres, where sunlight could not penetrate. The discovery of deep-sea organisms in the mid-19th century shattered that assumption, revealing that life persisted, and even thrived, in places once thought barren. Each new discovery replaced one kind of mystery with another, and myths gave way to questions that could be tested and explored. One of the pivotal moments in this shift came with the voyage of HMS Challenger from 1872 to 1876. This British expedition, often considered the birth of modern oceanography, travelled nearly 70,000 nautical miles, collecting samples, measuring depths, and cataloguing thousands of species. It revealed the existence of life in the deep ocean and mapped features like the Mid-Atlantic Ridge. It also dispelled many myths, showing that the deep was not a lifeless void, but a complex and dynamic environment. Yet even as it replaced myth with science, the Challenger expedition did not banish mystery, it deepened it. Every new discovery raised new questions, and the sheer vastness of the ocean became more apparent than ever. The 20th century brought new tools, sonar, submarines, deep-sea cameras, that allowed scientists to probe deeper and see farther. Submersibles like the Trieste descended into the Mariana Trench. Remotely operated vehicles revealed hydrothermal vent communities no one had imagined. With each advance, myths receded further, and science took their place. But the impulse behind those myths, the human urge to imagine what lies beyond our reach, did not disappear. It simply transformed. Where ancient sailors spoke of Leviathan and Oceanus, modern scientists speak of unknown species and unexplored ecosystems. Where myths spoke of gods and monsters, science speaks of chemical processes and evolutionary adaptations. The language has changed, but the sense of wonder remains. Even today, popular culture continues to fill the deep sea with creatures of imagination. Giant squids, once mythological, are now known to be real, yet they still loom large in literature and film. Stories of colossal deep-sea monsters persist, from Lovecraft's Cthulhu rising from the depths to cinematic leviathans that threaten humanity. These modern myths are not meant to be taken literally, but they serve the same purpose as the ancient ones. They give shape to the unknown. They allow us to imagine what might be down there, even when we cannot see it. They express our fascination and our fear, our curiosity and our awe. There is a deeper continuity here. Myths and science are often seen as opposites, but in truth, they are part of the same continuum. Both are ways of engaging with mystery. Myths imagine what we cannot know. Science investigates it. Myths fill the gaps in our understanding with stories. Science fills them with data. But the impulse behind both is the same, a desire to make sense of the unknown. The deep sea has always demanded that kind of engagement because it is by its nature unknowable. Not absolutely, but in practice. Its size, its darkness, its depth, and its inaccessibility mean that it will always outpace our knowledge. There will always be more to discover than we can grasp. And so, just as myths once did, science will continue to circle the unknown, expanding its reach without ever fully enclosing it. Modern curiosity about the deep is driven not only by wonder but by necessity. The deep ocean plays a crucial role in Earth's climate, chemistry and biology. It is home to vast reservoirs of carbon, essential minerals and genetic diversity. It influences weather patterns, supports fisheries, and shapes the evolution of life. Understanding it is not just a matter of satisfying curiosity, it is a matter of survival. Yet our exploration of the deep remains limited compared to our exploration of space. We have sent probes to the edges of the solar system, but we have barely begun to map the seafloor. We have catalogued the atmospheres of distant exoplanets, but we do not know the composition of many deep-sea ecosystems. This disparity speaks to the persistent influence of myth. Even in an age of science, space captures our imagination in part because it is visible. The deep sea, hidden and silent, resists our gaze. Still, curiosity persists. It drives scientists to develop new tools, new methods, new ways of seeing. It inspires nations and institutions to fund expeditions, even when budgets are tight. It pushes explorers to risk their lives in submersibles and divers to descend beyond safe limits. It fuels the slow, painstaking work of mapping, sampling and analysing. It is the same curiosity that once filled the ocean with gods and monsters, now turned toward understanding the processes that shape our planet. And it is a reminder that the deep sea is not just a physical space, but a conceptual one. A space where imagination and investigation meet. This interplay between myth and science also shapes how we communicate about the deep sea. Scientists often draw on mythic language to convey the wonder and strangeness of their discoveries. They speak of alien worlds and ancient creatures, of landscapes that resemble the surfaces of distant planets. This language is not accidental. It reflects the fact that the deep sea truly is as foreign and unexplored as any extraterrestrial world. It also reflects the continuity between the stories we told in the past and the stories we tell now. Myth may no longer explain the ocean, but it still frames how we think about it. The persistence of myth, also serves another purpose. It keeps us humble. It reminds us that the unknown will always be larger than the known, that our understanding is always provisional. Myths evolve as knowledge grows, but they never disappear entirely because there will always be gaps for them to fill. The deep sea ensures that those gaps will remain vast. It ensures that even as science advances, imagination will always have work to do. And perhaps that is fitting. The deep sea, after all, is not just a place. It is an idea, a symbol of the unknown, the unexplored, the unfathomable. It is a reminder that mystery still exists, that there are still frontiers left on Earth. It connects us to our ancestors, who stood on the same shores and stared out at the same horizon, wondering what lay beyond. It connects us to our future, to the discoveries yet to come. It connects myth to science, imagination to investigation, past to present. The transformation from myth to science did not happen overnight, nor is it complete. It is an ongoing process, one that continues with every expedition, every sample, every new piece of data. And it has brought us to a remarkable point in history. For the first time, we have the tools to reach the deepest parts of the ocean, to observe them directly, to begin unraveling their mysteries. We're no longer limited to speculation. We can test our ideas, challenge our assumptions, and replace myths with measurements. Yet even as we do, the deep sea resists us. It hides its secrets well, and as we push deeper, we encounter not only new questions, but new challenges. Challenges that no myth could have prepared us for. One of those challenges is the story of how we began to explore the deep in earnest. It is a story that blends myth and science, curiosity and courage, imagination and engineering. It is the story of how humans first descended into the abyss, how they built the machines that would carry them down, how they overcame the crushing pressure and the endless darkness, and how for the first time in history they looked upon a world that had existed unseen since the dawn of the planet. To understand why the deep sea remains unknown, we must understand how we first dared to know it at all. The ocean's depth remained for most of human history a place we could only imagine but never touch, a boundary defined by fear and ignorance as much as by physical limitation. People sailed across its surface for millennia, fought battles upon it, harvested food from its edges and built empires connected by its waves. But the world beneath the waves was beyond reach. No diver could descend more than a few dozen meters without risking death. No rope could reach the seafloor without breaking or becoming hopelessly tangled. No instrument could survive the pressure of the abyss. It was a world that seemed destined to remain hidden forever. And then, slowly, hesitantly, daringly, humanity began to descend. The earliest attempts to explore below the surface were crude but bold. Ancient sponge divers held their breath and plunged into the shallows, sometimes reaching depths of 30 or 40 meters. Extraordinary feats of endurance, but far from the midnight zone. In the Renaissance, inventors built diving bells, inverted chambers lowered into the water with air trapped inside, allowing divers to stay underwater longer. These bells extended human reach, but only slightly. They were heavy, cumbersome, and limited to shallow depths. They were windows, not doorways, into the deep. By the 19th century, new materials and industrial technology made deeper exploration possible. The invention of the hard hat diving suit in the 1830s allowed divers to remain underwater for extended periods, supplied with air through a hose from the surface. Salvage operations, underwater construction, and scientific sampling all benefited from this advance. Yet even these divers rarely went deeper than 100 meters. Beyond that, pressure crushed metal and bone alike. The abyss remained impenetrable. The first real breakthrough came not from a diver, but from a sphere of steel lowered into the sea on a cable. In the early 1930s, American naturalist William Beebe and engineer Otis Barton built a device they called the bathysphere. a hollow steel ball just over 4 feet in diameter with tiny quartz windows and enough room for 2 people to squeeze inside. Suspended from a ship by a steel cable, the bathysphere could be lowered far deeper than any diver could go. It was primitive by today's standards. It had no propulsion, no steering, no life support systems beyond compressed oxygen and chemical scrubbers. If anything went wrong, there was no rescue. And yet, with this crude vessel, Beebe and Barton descended to depths never before reached by humans. First 435 meters, then 923, then 1 to 6. Those dives were not just technical achievements, they were acts of extraordinary courage. The bathysphere was barely thicker than a man's arm, and the pressure outside could have crushed it like an eggshell. It was suspended by a single cable, and if that cable snapped, it would plunge uncontrollably into the abyss. The tiny windows distorted the view and offered little more than glimpses of the darkness outside. But through those windows, Beebe and Barton saw a world that no one had ever seen before. A world of strange, glowing creatures, of jellyfish and fish with lanterns in their heads, of shapes and movements that defied description. Beebe described them with the language of myth, dragons, ghosts and monsters, because there were no scientific words yet for what he saw. The bathysphere opened the door to the deep, and what lay beyond was stranger than anyone had imagined. The bathysphere proved that humans could descend into the deep, but it was a fragile and limited tool. It could not move horizontally. It could not stay down for long. It could only go as deep as its cable would allow. To explore farther, engineers needed a vessel that could move under its own power, that could carry people safely into the abyss and bring them back again. That vision began to take shape in the mid-20th century with the invention of the bathyscarf. The bathyscarf was an evolution of the bathysphere, but also a radical departure. Instead of hanging from a cable, it was freediving, using buoyancy and ballast to ascend and descend. A large float filled with gasoline provided lift, gasoline being less dense than water and incompressible under pressure, while heavy iron pellets served as ballast. The crew rode in a pressure sphere attached beneath the float, protected from the crushing depths by thick steel walls. When it was time to rise, the ballast was released, and the bathyscarf floated upward. The most famous of these early bathyscarfs was the Trieste, built by Swiss scientist Auguste Piccard, and later operated by the US Navy. In 1960, Piccard's son Jacques and US Navy Lieutenant Don Walsh boarded the Trieste and descended into the Mariana Trench, the deepest known part of the ocean. After nearly 5 hours of descent, they reached the Challenger Deep, 10,911 meters below the surface. The pressure outside was over 100 times that at sea level. The plexiglass window cracked under the stress, but the sphere held. They spent 20 minutes on the seafloor, observing sediment and what appeared to be a flat fish-like creature, before releasing ballast and ascending. It was a historic moment. For the first time, humans had reached the deepest part of the planet. The abyss was no longer theoretical, it had been touched. The Trieste was a technological marvel for its time, but like the bathysphere, it had limitations. It could descend and ascend, but it had little ability to maneuver horizontally. It carried no robotic arms, no scientific instruments beyond the most basic. Its windows were small, its lighting weak, its capacity limited. It was a proof of concept, a demonstration that humans could reach the ocean's greatest depths, but not yet a practical tool for exploration. As technology advanced, engineers built submersibles that were more capable, more maneuverable, and more useful for science. These new vessels were not just vehicles, they were laboratories. They carried cameras, sensors, manipulator arms, and sampling equipment. They could hover above the seafloor, collect specimens, drill into sediments, and deploy instruments. They could stay submerged for hours or even days. One of the most famous of these was Alvin, a US Navy and Woods Hole Oceanographic Institution submersible launched in 1964. Alvin could carry 3 people to depths of over 4,500 meters. It became one of the most important tools in deep-sea research, making discoveries that transformed our understanding of the ocean. In 1977, Alvin played a central role in one of the most significant discoveries in modern oceanography: hydrothermal vents. At a depth of 2,500 meters near the Galapagos Rift, scientists using Alvin found towering chimneys spewing mineral-rich water heated by magma below the seafloor. Around these vents thrived dense communities of life, giant tube worms, clams, crabs, and fish, unlike anything previously known. These organisms relied not on sunlight but on chemosynthesis, harnessing chemical energy from the vent fluids. The discovery overturned long-standing assumptions about the dependence of life on photosynthesis and revealed a new way for ecosystems to exist. It also hinted at the possibility of life elsewhere in the universe, on icy moons with subsurface oceans, for example, where sunlight never reaches. Alvin's work did not stop there. It explored undersea volcanoes, investigated deep-sea earthquakes, and helped locate the wreck of the RMS Titanic in 1985. It became a workhorse of deep-sea science, diving more than 5,000 times over its career. Its design inspired a new generation of submersibles around the world, vessels like Japan's Shinkai 6500, capable of reaching 6,500 meters, and France's Nautil, designed for deep-sea research and salvage. These submersibles extended human reach into the deep and allowed scientists to conduct systematic studies of ecosystems and geology far below the surface. Yet even as human-occupied submersibles grew more capable, they remained expensive and risky. Each dive required a ship, a crew, and careful planning. Each mission could last only a few hours, and each carried the inherent danger of sending people into an environment that would kill them instantly if the vessel failed. The limitations of human presence in the deep ocean spurred the development of another class of technology: remotely operated vehicles, or ROVs. ROVs are tethered robots controlled from the surface. They can stay underwater for days or weeks, collect samples, deploy instruments, and capture high-definition video. They do not tire. They do not require life support. They can go where it would be too dangerous or impractical to send humans. Early ROVs were simple and clumsy, but advances in robotics, materials, and communications transformed them into sophisticated tools. Today's ROVs are equipped with manipulator arms that can perform delicate tasks, sensors that can analyze water chemistry in real time, and cameras that can capture details invisible to the human eye. One of the most famous ROVs is Jason, operated by Woods Hole Oceanographic Institution. Since its introduction in the 1980s, Jason and its successors have explored hydrothermal vents, investigated undersea landslides, studied deep-sea corals, and recovered samples from the seafloor. Another is Ropos, a Canadian ROV used for geological and biological research. ROVs like these have vastly expanded our ability to explore the deep ocean. They allow scientists to study regions that were once inaccessible, and to conduct research that would be impossible with human-occupied vehicles alone. The next step in this technological evolution is autonomous underwater vehicles, or AUVs. Unlike ROVs, AUVs operate without direct human control. They follow pre-programmed missions, collecting data as they travel, and can operate for days or even weeks without surfacing. They can map vast areas of the seafloor, track ocean currents, and monitor environmental conditions. Some are small enough to be deployed from small boats, while others are large and capable of operating in the deepest parts of the ocean. AUVs represent a shift from exploration, as a series of discrete expeditions, to exploration as a continuous process. They are the scouts and surveyors of the deep, gathering the data that will guide future missions. Each of these advances, bathyspheres, bathyscarfs, submersibles, ROVs, AUVs, represents a step in humanity's gradual descent into the abyss. Each overcame challenges that once seemed insurmountable, and each revealed new layers of mystery. Together, they have transformed the deep sea from an imagined realm into a place we can observe, measure, and study. And yet, even with all this progress, our reach remains limited. Human-occupied submersibles can carry only a handful of people and visit only a few sites per year. Rovers and AUVs can cover more ground, but they are still constrained by power, communication, and cost. Vast regions of the ocean remain unexplored, unseen, and unknown. This limitation is not just technological but philosophical. Exploration has always been driven by curiosity, but curiosity must contend with risk and reward. The deep sea is expensive to reach and difficult to study. Its discoveries, while scientifically profound, rarely have immediate economic or political benefits. As a result, investment has often lagged behind potential. Space exploration, by contrast, captures the public imagination and inspires funding. The deep sea, hidden and silent, struggles to compete. The bathysphere was built with private funds. The Trieste was a military project. Many submersibles and ROVs rely on university or government budgets that are vulnerable to shifting priorities. The result is that deep-sea exploration progresses in fits and starts, driven by bursts of funding and interest rather than sustained commitment. And yet, despite these obstacles, the story of deep-sea exploration is one of remarkable perseverance. It is a story of individuals and institutions willing to risk failure for the sake of knowledge. It is a story of engineers solving problems that seemed impossible, of scientists venturing into hostile environments to answer questions no one had asked before. It is a story that continues to this day, as new technologies push the boundaries of what we can reach and what we can learn. And it is a story that is far from over. The tools we have built so far are only the beginning. They have allowed us to touch the deep, but not yet to know it fully. Even as we celebrate these achievements, we must also confront the limits they reveal. We can descend to the sea floor, but we cannot yet stay there for long. We can map small areas in detail, but we cannot yet map the ocean as a whole. We can sample individual ecosystems, but we cannot yet monitor their changes over decades or centuries. We are explorers still standing on the shoreline, peering into the darkness, taking our first tentative steps, and yet those steps matter. They are the reason we now know that hydrothermal vents exist, that chemosynthesis powers entire ecosystems, that strange creatures live in perpetual darkness. They are the reason we understand that the deep sea is not a static void, but a dynamic, living system. They are the reason we can begin to grasp the deep ocean's role in Earth's climate, geology, and biology. They are the reason we can even ask the questions we now ask. Without bathyspheres and bathyscaphs, without submersibles and ROVs, the deep sea would still be a realm of myth. But exploration is not only about technology. It is also about human limits, the physical, psychological, and biological constraints that define what we can and cannot do. Machines can go deeper and stay longer than we can, but there are things only humans can do. Observing subtle behaviors, making decisions in real time, recognizing patterns that no algorithm could detect, these are still human strengths. Yet sending humans into the deep sea is fraught with challenges, from the crushing pressure to the isolation and darkness that affect the mind. These challenges have shaped not only how we explore, but what we are willing to attempt. To understand why the deep sea remains so little known, we must confront those human limits directly. We must examine what it means to send people into an environment so hostile to life, how we have tried to overcome those barriers, and why some of them remain stubbornly in place. Because the deep ocean is not just a test of our machines, it is a test of ourselves. For all the triumphs of engineering that have carried us deeper into the ocean than anyone once thought possible, the most formidable barrier to exploration is not steel or circuitry, but the human body itself. Machines can be made stronger, more resistant, more enduring. They can operate in places that would crush us in an instant, travel where we could never go, and function without air or warmth or light. We, by contrast, are fragile. Our physiology is the product of life that evolved at the surface, under a single atmosphere of pressure, with abundant oxygen, stable temperatures, and the constant presence of sunlight. Everything about our biology, our lungs, our circulation, our senses, even our minds, is tuned to that narrow band of conditions. The deep ocean exists far outside it, and that is why, even after centuries of progress, the human body remains one of the greatest obstacles to understanding the abyss. The most immediate and obvious challenge is pressure. At sea level, the air around us presses on our bodies with a force of about 14.7 pounds per square inch. We are so accustomed to this that we barely notice it, but with every 10 metres of depth, pressure increases by another atmosphere. At 100 metres, it is roughly 11 times greater than at the surface. At 1,000 metres, it is about 100 times greater. At the deepest known point in the ocean, the Challenger Deep, nearly 11,000 metres down, pressure exceeds 1,100 atmospheres, more than 16,000 pounds per square inch. The human body is not built to withstand such forces. Air-filled spaces like lungs, sinuses, and the middle ear would collapse. Gases dissolved in the blood would behave differently. Proteins would denature. Cell membranes would fail. Even bones would not survive intact. Without the protection of a pressure-resistant vessel, a human at that depth would die instantly. Even well above those extreme depths, pressure presents serious physiological problems. Divers who breathe compressed air at depth must contend with the effects of nitrogen and oxygen, which behave differently under pressure than they do at the surface. Nitrogen, which makes up about 78% of the air we breathe, is relatively inert at atmospheric pressure. But under higher pressure, it dissolves more readily into the blood and tissues. At sufficient concentrations, it can affect the nervous system, producing a state known as nitrogen narcosis, a kind of intoxication that impairs judgment, slows reaction times, and can lead to dangerous mistakes. The deeper a diver goes, the more pronounced this effect becomes. At depths greater than 30 metres, it is noticeable. At 100 metres, it can be debilitating. Beyond that, it can be fatal. Oxygen, too, becomes hazardous at depth. Although it is essential for life, high partial pressures of oxygen can cause convulsions, lung damage, and other serious complications. To mitigate these risks, deep divers use special gas mixtures, replacing some of the nitrogen with helium, which is less soluble and less narcotic, and adjusting the oxygen content to safe levels. Heliox and trimix, as these mixtures are known, allow divers to work safely at greater depth than would be possible with air alone. But even with these precautions, there are limits. Most commercial and military dives do not exceed about 300 metres, and even saturation divers, those who live and work in pressurised habitats for extended periods, rarely go deeper than 500 metres. Beyond that, the risks become too great, and the physiological challenges too severe. Even returning to the surface carries dangers. As pressure decreases, gases dissolved in the blood and tissues must be released slowly. If a diver ascends too quickly, nitrogen can come out of solution and form bubbles in the body, a condition known as decompression sickness, or the bends. These bubbles can block blood flow, damage tissues, and cause excruciating pain, paralysis, or death. To prevent this, divers ascend gradually, pausing at intervals to allow gases to leave the body safely. The deeper and longer the dive, the more cautious the ascent must be. In saturation diving, where divers live at high pressure for days or weeks, decompression can take many hours, even days. Some have tried to extend human reach deeper still. In the mid-20th century, experiments in hydreliox and hydrogen diving explored the use of hydrogen in breathing mixtures, which could theoretically allow safe dives beyond 500 metres. Hydrogen is less dense and less narcotic than nitrogen or helium, and it can help prevent high-pressure nervous syndrome, a condition that affects the nervous system at extreme pressures. But hydrogen also poses risks, including the potential for explosive mixtures and unknown physiological effects. Despite decades of research, hydrogen diving remains largely experimental, and the deepest human dives, such as the record-setting 701-metre commercial dive in 1992, remain rare and dangerous exceptions. Even if the physiological challenges of pressure could be solved, others would remain. The deep ocean is dark and cold. Sunlight disappears entirely below about 1,000 metres, leaving a world of perpetual night. Human vision is poorly adapted to such conditions. Our eyes evolved to detect a narrow range of wavelengths, those abundant in sunlight, and without light they are almost useless. Artificial illumination can help, but it is limited. Light from lamps and spotlights scatters quickly in water, illuminating only a small area and often startling or driving away the very creatures scientists wish to observe. In the deep, sight becomes a blunt instrument, and humans must rely on other senses and tools to perceive their surroundings. Temperature is another challenge. Deep ocean water is typically just a few degrees above freezing. Human bodies generate heat, but we lose it quickly in water, which conducts heat about 25 times more efficiently than air. Without protection, hypothermia can set in within minutes. Even in protective suits, prolonged exposure is dangerous. Submersibles and diving suits can be heated, but doing so adds complexity, weight, and energy demands. And temperature is not uniform. Near hydrothermal vents, water can exceed 400 degrees Celsius, hot enough to melt lead, but it does not boil because of the immense pressure. These extremes, freezing cold and scalding heat, exist side by side, creating environments that are not just inhospitable, but potentially lethal to humans and their equipment alike. Isolation and confinement add psychological burdens to the physiological ones. Working in the deep ocean means spending hours, sometimes days, in cramped, windowless spaces, cut off from the outside world. Communication is limited and delayed. Movement is restricted. Time loses its familiar markers. These conditions can lead to disorientation, anxiety, claustrophobia, and cognitive fatigue. Submersible pilots and saturation divers must undergo rigorous training to prepare for the mental demands of their work. Even then, the strain can be intense. In a place where even minor errors can have catastrophic consequences, psychological resilience is as important as physical endurance. The human body also struggles with the simple act of movement at depth. Water is dense and resistant, and every motion requires more effort than it does in air. Divers must work harder to swim, to maneuver, to handle tools. Fatigue sets in quickly. Fine motor skills are impaired by gloves and pressure suits. Even breathing is more difficult, as the density of the breathing gas increases with pressure. These factors combine to limit how much work humans can do underwater and how long they can do it. The logistics of supporting human life in the deep ocean are formidable as well. Submersibles must carry enough oxygen, remove carbon dioxide, regulate temperature and humidity, and protect their occupants from pressure. They must provide power for lights, instruments, and propulsion. They must withstand mechanical stresses, resist corrosion, and operate reliably in an environment that punishes even the smallest flaw. Every additional system adds weight and complexity, which in turn adds cost. And because safety margins must be absolute, engineering standards are uncompromising. This is one reason why human-occupied vehicles are so expensive and rare. Each dive represents years of design, testing, and preparation, and even then the risks can never be entirely eliminated. Despite these challenges, humans continue to descend. The desire to witness the deep directly, to see it not through cameras or instruments but with our own eyes, is powerful. It is not just about data, it is about perspective. There is something irreplaceable about human presence, about the ability to respond intuitively to what is seen, to notice patterns that no machine would recognize, to make decisions in the moment. Human explorers have described moments of profound connection and awe on the seafloor. moments that reshape their understanding of the planet. Those moments are part of what drives exploration forward, even when it is dangerous and difficult. Yet the limits of our physiology ensure that humans will never explore the deep ocean the way we explore the land or even low Earth orbit. We will always rely on machines to extend our reach, to go deeper, stay longer, and operate in places we cannot. Human presence will remain rare and precious, reserved for tasks that require it most. The rest will be done by robots, sensors, and remote instruments. This is not a failure, but a recognition of reality. The deep ocean is not our natural environment. It is a world apart, and our place within it will always be partial. Understanding these human limits is crucial not only for exploration, but for safety and planning. It informs the design of submersibles and habitats, the composition of breathing gases, the protocols for ascent and decompression. It shapes training programs for divers and pilots. It influences how missions are scheduled, how long they last, and what they attempt to achieve. It determines how we balance human presence with robotic capability. And it reminds us that exploration is not just a matter of technology, but of biology, that the boundaries of our bodies are as important as the boundaries of our machines. It also reveals something deeper about our relationship with the unknown. The fact that we cannot easily enter the deep ocean does not diminish our desire to understand it. If anything, it amplifies it. The very hostility of the environment becomes part of its allure. It challenges us, tests us, forces us to adapt and innovate. It pushes us to build machines that can go where we cannot, and to imagine ways of sensing and understanding that go beyond our natural capacities. It humbles us, reminding us that we are not the measure of all things, that there are places on our own planet where we do not belong, where we can only visit briefly and with great effort. Yet those visits, as fleeting as they are, have already transformed our understanding of the world. They have revealed ecosystems that operate on principles we never suspected, geological processes that shape the planet in ways we'd not imagined, and chemical cycles that sustain life in the most unlikely places. They have shown us that the deep ocean is not a static abyss, but a dynamic, living system that influences everything from the climate to the evolution of species. And they have shown us that even in a place so hostile to human life, life itself flourishes in astonishing diversity. The deep ocean forces us to confront the limits of our own nature, but it also expands them. It compels us to think beyond the surface, beyond the familiar, beyond the boundaries of our senses and our bodies. It invites us to imagine what lies beyond those limits, not just in the ocean, but in the universe as a whole. If life can exist here, under such crushing pressure and in such total darkness, what else might be possible elsewhere? If we can build machines to explore this alien realm beneath our own feet, what might we build to explore other worlds? These questions remind us that the human story of exploration is not finished. It is only beginning. The deep ocean is not the end of our reach, but a new horizon. And to move beyond that horizon, we must confront not only the physical and physiological limits that hold us back, but also the social, economic, and political forces that shape what we choose to explore. Because even if we could overcome every biological constraint, we would still face another barrier, one built not of pressure or darkness, but of priorities and resources. Even if we had bodies that could shrug off the crushing weight of the deep, if our lungs could breathe safely at depth and our minds could remain calm in darkness, even if our machines could operate indefinitely in those cold and hostile conditions, the reality is that exploration does not happen in a vacuum. It happens in a world shaped by economics, politics, culture, and human priorities. And perhaps nowhere is that clearer than in the strange disparity between how much we invest in exploring the cosmos above us and how little we devote to exploring the vast, living world beneath our own feet. It is one of the great paradoxes of our age. We have sent robots billions of kilometers across space, landed rovers on Mars, and mapped the surfaces of distant planets in exquisite detail. yet more than 80% of Earth's ocean remains unmapped, unobserved, and unexplored. The reasons for this imbalance are complex, and they reveal as much about ourselves as they do about the worlds we seek to know. On a purely practical level, exploring the deep ocean is expensive, often more expensive per kilometre than exploring space. Ships capable of launching deep-sea submersibles cost tens of thousands of dollars a day to operate. Building a submersible that can withstand the immense pressure of the abyss can cost tens or even hundreds of millions. Maintaining and staffing research vessels requires crews, scientists, engineers and technicians, all of whom must be paid and supported at sea. Missions are weather-dependent, logistically complex, and often limited to small windows of time. And because each expedition typically explores only a tiny fraction of the ocean, dozens or even hundreds of missions would be required to survey it thoroughly. The costs add up quickly, and the return on investment is often uncertain. Space exploration is expensive too, of course, but it benefits from economies of scale and decades of sustained investment. Launch vehicles, spacecraft, and satellite systems are developed and reused across multiple missions. Data from one mission can inform and improve the next. International collaboration spread costs and risks among many partners. Space agencies have permanent budgets, infrastructure, and political backing. Deep-sea exploration rarely enjoys the same level of institutional support. Most missions are one-off projects, funded piecemeal by research grants or limited government programs. Once they're completed, the infrastructure is often mothballed or dismantled and the expertise dispersed. The lack of continuity means that every new expedition must reinvent part of the wheel, driving up costs and slowing progress. There is also the problem of visibility, both literal and metaphorical. Space exploration captures the public imagination in ways the deep sea often does not. Images of distant planets, dramatic rocket launches, astronauts floating above Earth. These are powerful symbols of human achievement. They speak to our ancient desire to reach beyond our world, to transcend our limits, to see what lies beyond the horizon. They are visible and spectacular, easy to share and celebrate. The deep ocean, by contrast, is invisible. Its wonders are hidden beneath kilometres of water, its landscapes cloaked in darkness. There are no dramatic launches, no glowing nebulae, no alien sunsets. The discoveries it yields are subtle. New species, new chemical processes, new geological formations, and often invisible to the naked eye. They require explanation and context to be appreciated, and even then, they may not stir the same visceral excitement. This disparity in public perception has real consequences. Funding for exploration is not determined solely by scientific need. It is shaped by public interest and political will. Projects that capture the imagination are more likely to receive support. Politicians are more willing to allocate funds to programs that inspire pride, attract media attention, or promise geopolitical advantage. Space exploration has long benefited from this dynamic. From the space race of the Cold War to the ongoing competition to reach Mars, space has been a stage for national ambition and global cooperation alike. It is a domain where nations project power, prestige, and technological prowess. Deep-sea exploration, by contrast, lacks that same geopolitical weight. It is seen as science, not strategy, valuable but not essential. Economics plays a role in another way as well. The potential for commercial return. Space exploration, for all its costs, offers the promise of new markets. Satellite communications, Earth observation, space tourism, asteroid mining. These possibilities attract private investment and create partnerships between governments and industry. Deep-sea exploration, though it also offers economic potential, has struggled to generate the same excitement. Deep-sea mining could provide access to valuable metals like cobalt, nickel, and rare earth elements, but it is controversial and heavily regulated. Fisheries already exploit many deep-sea species, but overfishing and ecological concerns limit expansion. Bioprospecting, the search for useful compounds from deep-sea organisms, holds promise for medicine and biotechnology. But the path from discovery to profit is long and uncertain. These realities make private investors cautious and limit the flow of capital into deep-sea research. The structure of global funding also reinforces the imbalance. Space exploration is dominated by a few large, well-funded agencies, NASA, ESA, Roscosmos, CNSA, that coordinate missions, build infrastructure, and sustain programs over decades. Deep-sea research, by contrast, is fragmented. It is conducted by universities, national research institutions, and occasional international partnerships, each with its own priorities and budgets. Coordination is limited, data sharing is inconsistent, and efforts are often duplicated. The result is a patchwork of projects rather than a coherent global strategy. This fragmentation makes it harder to secure large-scale funding, to plan long-term missions, or to sustain public interest. There is also a cultural dimension to the disparity. Humanity has long looked to the sky as a symbol of aspiration. The stars have inspired myths, religions, philosophies, and dreams. They represent transcendence, possibility, the unknown made visible. The ocean, by contrast, has often been seen as a barrier, a force to be crossed, feared, or conquered, but not embraced. It is associated with danger, isolation, and loss. These cultural narratives shape how we think about exploration. Reaching for the stars feels like progress, like moving forward. Descending into the depths can feel like going backward, into darkness and mystery. This bias is subtle, but powerful, and it influences decisions about where we direct our resources and attention. And yet, when measured purely by potential impact, the deep ocean is arguably more important to our future than distant planets. It regulates Earth's climate by absorbing heat and carbon dioxide. It drives weather patterns and influences the distribution of life on land. It holds vast reservoirs of biodiversity, much of it unknown and potentially valuable. It contains mineral resources that could support the technologies of a renewable future. It may even hold clues to the origins of life itself. Understanding the deep ocean is not a luxury. It is essential to understanding the planet we live on and to managing the changes that lie ahead. Yet because its importance is less visible, it often struggles to compete for attention and funding. This imbalance has practical consequences. Our maps of the seafloor are crude compared to our maps of Mars or the Moon. Much of the ocean remains unexplored, its ecosystems unstudied, its geological processes poorly understood. We're trying to manage fisheries, regulate mining, and predict climate change with incomplete data. We are making decisions about the use and protection of marine resources without fully understanding what is at stake. The lack of investment in deep-sea exploration is not just a missed opportunity, it is a risk, one that could have profound consequences for the planet's future. There are signs that this is beginning to change. Growing awareness of the ocean's role in climate regulation has brought new attention to deep-sea processes. Concerns about biodiversity loss have highlighted the importance of understanding deep ecosystems. Interest in deep-sea mining has spurred investment in mapping and sampling, even as it raises difficult ethical questions. International initiatives such as the United Nations Decade of Ocean Science for Sustainable Development 2021 to 2030 aim to coordinate research, share data, and mobilize resources on a global scale. Private companies are beginning to show interest in deep-sea exploration, driven by potential commercial opportunities and corporate responsibility. These developments are promising, but they are still small steps compared to the sustained, coordinated investment that space exploration enjoys. The disparity is not inevitable, it is the result of choices. Choices about what we value, what we fear, what we aspire to. Changing those choices requires shifting perceptions as much as reallocating budgets. It means telling the story of the deep ocean in ways that capture the imagination, that make its importance visible, that connect its mysteries to the broader human story. It means building institutions and partnerships that can sustain exploration over decades, not just single expeditions. It means integrating deep-sea science into global priorities, from climate policy to economic development. And it means recognizing that the frontier beneath our feet is as vast and as vital as the one above our heads. It also means confronting uncomfortable questions about how we explore and why. Space exploration is often justified by the promise of future colonization, by the idea that humanity must spread beyond Earth to survive. Deep-sea exploration offers no such narrative. We cannot live in the abyss. We cannot build cities on the seafloor. Its value is not in providing a new home, but in deepening our understanding of the one we already have. That may make it harder to sell as a grand vision, but it also makes it more urgent. We can survive without ever setting foot on Mars. We cannot survive if we fail to understand and protect the systems that sustain life on Earth. There is another irony here. The technologies developed for space exploration often find their way into deep-sea research, and vice versa. Advances in robotics, sensors and materials benefit both fields. Autonomous vehicles designed for Mars rovers share principles with those used for ocean exploration. High-pressure systems built for submersibles inform spacecraft engineering. The challenges of communication, navigation and power are common to both. The boundaries between the two are more porous than they appear, yet the flow of funding and attention remains heavily weighted towards space. This imbalance also reflects deeper human impulses, our desire to look outward rather than inward, to seek novelty rather than confront complexity. Space is distant and abstract, invites us to imagine a blank slate, a new beginning. The ocean is close and complicated. It confronts us with the consequences of our actions, overfishing, pollution, climate change, and demands solutions that are messy and difficult. It asks us to care for what we already have rather than dream of escape. In this sense, the deep sea is not just a scientific challenge, it is a philosophical one. But perhaps the most important reason to invest in exploring the deep ocean is that it remains, quite simply, unknown. We cannot predict what we will find there. New forms of life, new ecosystems, new resources, new processes that reshape our understanding of the planet. History shows that exploration often yields discoveries no one anticipated, discoveries that transform science, technology, and society. The same is almost certainly true of the deep sea. We cannot know what we are missing until we look. The economics of the unknown are always difficult. Exploration requires spending money now for benefits that may not materialize for decades, if at all. It requires risk, of failure, of wasted effort, of political backlash. It requires faith that knowledge itself is worth pursuing, even when its practical applications are not immediately clear. These are challenges in any field, but they are especially acute in deep-sea exploration, where the unknown is so vast and the obstacles so great. Yet the potential rewards, scientific, environmental, economic, philosophical, are equally vast. The choice is not between space and sea. It is not a zero-sum game. We can and should explore both. But the imbalance between them reflects a deeper question about how we define exploration and what we believe it is for. If exploration is about expanding human presence, then space will always have the edge. If it is about understanding the systems that sustain us, then the deep ocean is just as important, perhaps more so. And if it is about confronting the unknown in all its forms, then we ignore the abyss at our peril. Ultimately, the disparity between space and sea is a mirror. It reflects our ambitions, our fears, our values. It shows us what we choose to celebrate and what we choose to overlook. It reveals how we think about ourselves and our place in the universe, and it challenges us to ask whether those choices are wise. The deep sea is not less mysterious than Mars or Europa. It is not less worthy of exploration. It is simply less visible, less romantic, less woven into the stories we tell about ourselves. But that can change. It must change. Because even if we never set foot on another planet, the deep ocean will continue to shape our world. It will continue to regulate our climate, feed our populations, and support the diversity of life. It will continue to hide secrets that could transform our science and our technology. It will continue to remind us that there is still so much we do not know. And it will continue to wait, silent and vast beneath the waves, not indifferent, not unreachable, but unexplored. And if we ever hope to explore it more fully, we must also confront the forces that shape it from within. For the deep sea is not just a passive environment waiting to be studied, it is an active, dynamic part of the planet, a place of fire and water, creation and destruction. Beneath the darkness and pressure, volcanic forces shape the sea floor, building mountains and tearing them apart. Black smokers belch mineral-rich fluids into the water. Earthquakes rumble silently through the crust. These forces are not just geological curiosities. They are fundamental to how the deep sea works, and they are key to understanding why this hidden realm matters not only to science, but to the planet itself. Beneath the darkness and pressure, beneath the silence that seems to stretch forever, the deep ocean is anything but still. It is alive with movement and force, shaped by the same planetary energies that built the continents and carved the mountains. For all its alien qualities, the deep is not separate from Earth's heart. It is an extension of it, a place where the planet's interior and exterior meet in violent, creative ways. It is here, far from sunlight and human eyes, that Earth remakes itself continuously. It is here that volcanic forces shape the seafloor, build new crust and pour heat and minerals into the water. And it is here, in the strangest and most inhospitable corners of the ocean, that some of the most extraordinary phenomena on the planet occur. Black smokers and submarine volcanoes, the fiery heartbeat of a world that never stops changing. The seafloor is not a static surface. It is a living landscape in motion, reshaped constantly by tectonic forces. Earth's outer shell is broken into a mosaic of plates that float on the mantle beneath. Where they move apart, new crust forms. Where they collide, old crust is destroyed. Most of this activity happens beneath the ocean. The longest mountain range on Earth, the mid-ocean ridge system, runs for more than 65,000 kilometers beneath the sea, circling the planet like a scar. Along this ridge, molten rock rises from the mantle, cools and solidifies, creating new seafloor. This process, called seafloor spreading, is one of the most fundamental ways Earth renews itself. It pushes continents apart, reshapes ocean basins, and drives the movement of tectonic plates. The creation of new crust is not a gentle process. It is volcanic, explosive, and continuous. Eruptions along the mid-ocean ridges are among the most common volcanic events on Earth, though most go unnoticed because they occur far from human sight. Lava wells up through cracks in the crust, spilling out in long sheets or erupting in dramatic bursts. It cools quickly in the near-freezing water, forming pillow-shaped structures that pile up into ridges and mounds. Over time, these eruptions build vast underwater mountain ranges and shape the topography of the ocean floor. In some places, volcanic activity pushes the seafloor upward until it breaches the surface, creating islands like Iceland and the Azores. But most of it remains hidden, reshaping the planet in silence and darkness. These volcanic processes do more than build crust. They also drive one of the most remarkable features of the deep ocean: hydrothermal vents. As seawater seeps into the cracks and fissures of the newly formed crust, it is drawn deeper into the earth, where it encounters hot rock. The water heats rapidly, sometimes to temperatures of more than 400 degrees Celsius. It reacts chemically with the surrounding rock, dissolving metals and minerals. Then, buoyant and pressurized, it rises back toward the surface, emerging from the seafloor in jets of superheated fluid. When this fluid hits the near-freezing seawater, the dissolved minerals precipitate out, forming towering chimneys of metal sulfides, and releasing clouds of black, mineral-rich particles. These vents, known as black smokers, are among the most extraordinary phenomena on Earth. Black smokers are not just geological curiosities, they are windows into the deep workings of the planet. The fluids they release reveal the chemistry of the Earth's interior and the ways in which rock and water interact under extreme conditions. The structures they build, some rising more than 60 meters from the sea floor, are records of geological processes that have been shaping the planet for billions of years, and the ecosystems they support are unlike anything else on Earth. Around these vents, in total darkness and at crushing pressures, life flourishes without sunlight. Instead of photosynthesis, these organisms rely on chemosynthesis, using the chemical energy in vent fluids to power their metabolism. Giant tube worms, clams, mussels, shrimp, and countless microbes thrive in dense communities, sustained by energy from the Earth's interior rather than the sun. It is one of the most profound revelations of modern science that life does not require sunlight to exist. It can emerge and thrive wherever energy and water interact, even in the most hostile environments imaginable. The discovery of hydrothermal vents in 1977 near the Galapagos Rift was a turning point in our understanding of the deep ocean and of life itself. Before then, scientists believed that the deep sea was a nutrient-poor desert, sparsely populated and dependent on organic matter falling from the surface. The idea that entire ecosystems could exist independently of sunlight was revolutionary. It forced biologists to rethink the conditions necessary for life, and geologists to reconsider the role of the deep ocean in Earth systems. It also raised profound questions about the origins of life. Some scientists now believe that life on Earth may have begun at hydrothermal vents, where heat, minerals, and organic molecules combine to create the first self-replicating systems. If that is true, then the deep sea is not just a remote frontier. It is the cradle of life itself. The implications extend beyond Earth. If life can exist in the dark, pressurized, mineral-rich environment of a hydrothermal vent, then it might also exist in similar environments elsewhere, beneath the icy crust of Europa or Enceladus, for example, where subsurface oceans are thought to interact with rocky cores. The discovery of vent ecosystems transformed our search for life in the universe, shifting the focus from planets with surface water and sunlight to worlds with liquid water and internal heat. The deep ocean, once thought of as a distant and alien realm, became a model for environments that might exist far beyond our planet. But hydrothermal vents are only one expression of the deep ocean's fiery heart. Elsewhere, volcanic activity shapes the seafloor in ways that are less spectacular but equally profound. Along mid-ocean ridges, magma continuously wells up from the mantle, creating new crust and pushing older crust outward. At subduction zones, where one tectonic plate is forced beneath another, magma generated by the melting of the descending plate rises to form volcanic arcs and undersea volcanoes. These volcanoes are not rare. Scientists estimate that there may be more than 1 million submarine volcanoes worldwide, and while most are small, some rival the size of terrestrial giants, many erupt regularly, releasing lava, ash and gases into the water. Some build seamounts that rise thousands of meters above the sea floor. A few even breach the surface, creating islands that emerge suddenly from the sea. The scale and frequency of submarine volcanism are staggering. It is estimated that about 75% of Earth's volcanic activity occurs beneath the ocean, most of it unseen. Each year, mid-ocean ridges produce enough new crust to pave a continent. Massive eruptions reshape the seafloor, alter ocean circulation, and release vast amounts of heat and chemicals into the water. These processes are fundamental to the planet's geological and chemical balance. They regulate the composition of seawater, influence the distribution of minerals, and contribute to the cycling of elements essential for life. They also drive tectonic processes that shape the continents and ocean basins over geological timescales. Studying these processes is difficult. Most submarine eruptions occur without warning and without witnesses. They may last only hours or days, and their evidence can be erased quickly by subsequent activity. Detecting them requires a combination of seismic monitoring, temperature sensors, chemical detectors, and sometimes sheer luck. Even when eruptions are detected, reaching them in time to observe them directly is rare. The deep ocean does not yield its secrets easily, and much of what we know about its volcanic activity comes from indirect evidence. Fresh lava flows discovered long after the eruption, changes in the chemistry of vent fluids, or seismic signals recorded on distant instruments. Yet even these glimpses reveal a dynamic world. In 1993, scientists discovered an active eruption on the Juan de Fuca Ridge off the coast of the Pacific Northwest, one of the first times a deep-sea eruption had been observed as it happened. The eruption created new vents and reshaped the seafloor. In 2011, another eruption occurred at Axial Seamount, a submarine volcano about 480 kilometers off the Oregon coast. Scientists had installed instruments there in anticipation of an eruption, and for the first time they were able to monitor one in detail. They recorded seismic activity, temperature changes, and fluid chemistry before, during, and after the event, providing invaluable data on the dynamics of submarine volcanism. These observations confirm that the processes shaping the deep ocean are as complex and varied as those shaping the continents, and that they are essential to the functioning of the planet as a whole. The interaction between volcanic activity and hydrothermal circulation also has profound implications for the ocean's chemistry. As seawater percolates through the hot, newly formed crust, it dissolves metals and other elements, which are then released back into the ocean at vents. These elements, including iron, manganese, and sulfur, are essential nutrients for marine life and play key roles in biogeochemical cycles. The flux of these materials from the seafloor influences everything from the productivity of surface waters to the carbon cycle. It also shapes the distribution of mineral deposits on the seafloor, including polymetallic sulfides and manganese nodules that are increasingly seen as potential resources for future mining. These geological processes do not occur in isolation. They interact with biological systems in complex and sometimes surprising ways. Microbes at hydrothermal vents catalyze chemical reactions that influence the composition of vent fluids and the precipitation of minerals. Mineral particles released by eruptions provide surfaces for microbial colonization and can be transported long distances by ocean currents, affecting ecosystems far from their source. Volcanic gases such as carbon dioxide and methane contribute to the global carbon cycle. Even large-scale geological events such as the formation of new ocean basins or the closure of old ones can reshape marine ecosystems over millions of years, driving evolution and extinction alike. Our understanding of these processes is still incomplete. The deep ocean remains largely unmapped, and many volcanic features have never been observed. The distribution and frequency of submarine eruptions are poorly constrained. The mechanisms that control hydrothermal circulation, the variability of vent chemistry, and the long-term impacts of these processes on ocean chemistry and biology are still subjects of active research. Each new discovery reveals not only new details but new questions, reminding us that the deep sea is not a static landscape but a dynamic, evolving system. The challenges of studying this fiery world are immense. Extreme pressure, darkness, and remoteness make direct observation difficult. Instruments must be designed to withstand corrosive fluids, intense heat, and crushing pressure. Deploying them requires ships, submersibles, and months of preparation. Recovering them can take years. Even then, data are often sparse and fragmentary. Much of what we know comes from a handful of well-studied sites, while vast areas remain unexplored. Yet these challenges also make the pursuit more rewarding. Every new measurement, every new sample, every new image expands our understanding of the planet we live on and the forces that shape it. The study of black smokers and submarine volcanoes is not just about understanding the deep ocean. It is about understanding Earth itself. It reveals how our planet recycles its crust, how it transfers heat from its interior to its surface, how it creates and distributes the elements that make life possible. It shows us that the ocean floor is not a dead, featureless plain, but a landscape of mountains, valleys, and volcanoes alive with activity. It reminds us that the deep ocean is not a passive receiver of material from above, but an active participant in the planet's systems, and it connects the deep sea to the rest of Earth in ways that are both profound and inescapable. It also connects the deep sea to human affairs. The minerals concentrated around hydrothermal vents are of growing interest to industry. The heat and chemical fluxes they release influence fisheries, climate, and the distribution of marine life. Submarine volcanoes can generate tsunamis, affecting coastal communities thousands of kilometers away. The gases they emit contribute to the global carbon budget, influencing climate over geological timescales. The processes that shape the deep ocean are not isolated from our lives. They shape the conditions we depend on, even if we are unaware of them. This connection is a reminder that the deep sea is not just a scientific curiosity. It is a vital part of the planet's machinery, a system that sustains and regulates life on Earth. Understanding it is not optional. It is essential. And yet, for all that we have learned, we have only begun to scratch the surface. Vast stretches of the mid-ocean ridges remain unexplored. Most submarine volcanoes have never been mapped. The diversity of hydrothermal systems is only beginning to be appreciated. The interactions between geological, chemical, and biological processes remain incompletely understood. The deep ocean continues to hide its secrets, even as we work to uncover them, and beyond the vents and volcanoes, beyond the fiery interactions of rock and water, there is another layer of mystery, one that is not about creation, but about transformation. The deep ocean does not only build, it also buries, recycles, and preserves. It is a place where the planet's past is recorded in sediments, where traces of ancient climates and extinct species lie entombed. It is a place where geological processes and biological activity intertwine to shape the evolution of the Earth over millions of years. If the black smokers and hidden volcanoes are Earth's heartbeat, then the sediments and deposits that blanket the seafloor are its memory. And to understand why the deep sea matters, and why it remains so unknown, we must turn our attention to that record, to the archive that lies hidden beneath the abyssal plains. The deep sea is not just a realm of geological creation, not merely a place where rock and water meet to forge new crust and release the planet's heat. It is also an archive, a vast and ancient library of Earth's history written not in ink but in stone, sediment, and DNA. The layers that blanket the seafloor are time itself, built grain by grain over millions of years, preserving traces of worlds that no longer exist. And within those depths, among the strange landscapes and chemical gradients, live creatures that seem to have stepped out of prehistory, organisms that have changed little, if at all, since the dawn of complex life. They are not relics in the sense of being obsolete. They are survivors, thriving in environments so stable and so isolated that evolution itself seems to slow to a crawl. The deep ocean is not just the planet's present. It is its past, still alive and moving quietly beneath the waves. Sediments are the first layer of this time capsule. Over millions of years, particles drift down from the surface, dust blown from continents, the remains of microscopic organisms, ash from distant eruptions, debris from cosmic impacts. Each particle settles gently on the seafloor, forming a thin layer that is soon buried by the next. Over time, these layers build up into deposits hundreds of meters thick, recording the passage of time with extraordinary fidelity. The composition of these sediments reflects the conditions of the world above: changes in climate, shifts in ocean currents, fluctuations in biological productivity. Ice ages leave their signature in the form of coarse glacial debris. Warm periods are marked by rich deposits of calcium carbonate from planktonic shells. Volcanic eruptions lay down layers of ash that can be traced across oceans. Even the impact that ended the reign of the dinosaurs is recorded in a thin layer of iridium-rich clay found on sea floors around the world. These sediments are more than a passive record. They are an active part of the planet's history, influencing the chemistry of the ocean and the cycling of elements. They are sites of microbial activity, where communities of bacteria and archaea break down organic matter and recycle nutrients. They are also a refuge, preserving delicate structures and fragile molecules that would be destroyed elsewhere. Fossils of microscopic plankton reveal how life responded to ancient climate shifts. Layers of organic-rich mud record changes in oxygen levels and carbon storage. Tiny magnetic grains preserve the history of Earth's magnetic field, flipping back and forth as the poles reversed over millions of years. Reading this archive is like reading the biography of the planet, page by page, layer by layer. But the sediments are only part of the story. The deep sea is also home to living fossils, organisms whose lineages stretch back hundreds of millions of years, whose bodies have remained almost unchanged while continents drifted, climates shifted, and entire species rose and vanished. These creatures are not primitive in the sense of being unfinished. They are perfectly adapted to environments that have themselves changed little over vast spans of time. Where conditions are stable, evolution has little reason to tinker. The result is a living window into Earth's distant past. One of the most striking examples is the coelacanth, a lobe-finned fish thought to have gone extinct with the dinosaurs until a living specimen was caught off the coast of South Africa in 1938. Coelacanths first appeared more than 400 million years ago, and their anatomy has changed little since. They have fleshy, limb-like fins, a hinged skull that allows them to open their mouths wide, and a unique rostral organ that may detect electric fields. They give birth to live young, an unusual trait among fish. Today, coelacanths inhabit deep, rocky caves at depths of 150 to 700 meters, emerging at night to feed. Their discovery was a scientific sensation, a reminder that the deep sea can harbour survivors from eras long thought gone. The coelacanth is not alone. Hagfish, eel-like scavengers that secrete copious amounts of slime, have existed for more than 300 million years with little change. They lack jaws, bones, and true vertebrae, traits that place them close to the base of the vertebrate lineage. Their physiology, simple yet effective, has allowed them to thrive in deep-sea environments where competition is limited and food is scarce. Horseshoe crabs, though not deep-sea dwellers themselves, have close relatives that inhabit the depths, and their basic body plan has remained stable for more than 450 million years. Nautiluses, with their coiled shells and jet-propelled movement, are living descendants of a group that once dominated the seas in the Paleozoic era. Their deep-sea habitats have shielded them from many of the environmental changes that drove their relatives to extinction. Even more ancient are some of the microorganisms that inhabit deep-sea sediments and hydrothermal vent systems. Many archaea, single-celled organisms distinct from bacteria and eukaryotes, thrive in extreme conditions of heat, pressure, and chemical gradients. Some of these lineages may resemble the earliest forms of life on Earth, living analogues of organisms that existed billions of years ago. They metabolize hydrogen, sulfur, and methane, deriving energy from chemical reactions rather than sunlight. Their ability to survive and even flourish under such conditions suggests that life could have originated in similar environments, and that it could exist in comparable environments on other worlds. These ancient lineages persist in part because the deep ocean is remarkably stable. Unlike surface environments, which are subject to rapid changes in temperature, light, and nutrient availability, the deep sea changes slowly. Temperatures remain near freezing, light is absent, and currents move sluggishly. Food is scarce, arriving mostly as a slow rain of organic material from above. Predators are fewer, competition is less intense, and disturbances are rare. In such conditions, traits that work well tend to remain unchanged. Evolution continues, but it does so at a slower pace, preserving forms and functions that might be outcompeted or transformed in more dynamic environments. This stability is not absolute. Over geological timescales, the deep ocean has undergone profound changes. Ocean circulation patterns have shifted, oxygen levels have fluctuated, and entire ecosystems have come and gone. Mass extinctions that wiped out species on land and in shallow seas have left their mark in the deep as well. Yet even through these upheavals, some lineages have endured, adapting just enough to survive without altering their fundamental design. Their persistence is a testament to the resilience of life and to the buffering power of the deep ocean. The deep also preserves evidence of life that no longer exists. Fossilized remains of deep-sea organisms are rare, but they do occur, particularly in fine-grained sediments that capture delicate structures. Microfossils of foraminifera, diatoms and radiolarians, tiny plankton with intricate shells, provide detailed records of past ocean conditions. Changes in their abundance, diversity and morphology reveal shifts in temperature, nutrient availability and acidity. Layers rich in organic matter record blooms of productivity and episodes of anoxia. Burrows and trace fossils reveal the activity of ancient worms and other soft-bodied creatures. Together, these records allow scientists to reconstruct the evolution of deep-sea ecosystems over millions of years. Some of the most remarkable discoveries have come from drilling into deep-sea sediments and crust. Projects like the Deep Sea Drilling Project, the Ocean Drilling Program, and the Integrated Ocean Drilling Program have retrieved cores that extend tens or even hundreds of millions of years into the past. These cores reveal not only the history of life, but also the history of the planet. They show how ocean chemistry has changed over time, how volcanic activity and tectonic movements have shaped the sea floor, how climate shifts have altered circulation patterns. They record mass extinctions, abrupt warming events, and the slow dance of ice ages and interglacial periods. They show how life and Earth have co-evolved, each shaping and responding to the other. The concept of the deep sea as a time capsule extends beyond biology and geology. It encompasses the ways in which the deep preserves signals of human activity as well. Even in the most remote parts of the ocean, sediments contain traces of industrial pollutants, microplastics, and radioactive isotopes from nuclear testing. These markers, barely a century old, will remain in the geological record for millions of years. They are a stark reminder that even the deepest and most ancient environments on Earth are not isolated from human influence. The time capsule of the deep now contains our story too. A brief, intense layer marking the arrival of a species that has transformed the planet in an instant of geological time. This duality, ancient and modern, stable and changing, is what makes the deep ocean so compelling. It is a place where time stretches in both directions, where the past is preserved and the present leaves its mark. It is a place where evolution slows but never stops, where ancient lineages persist alongside newly evolved forms. It is a place where the planet's memory is written in layers of sediment and strands of DNA, and it is a place where the line between living fossil and living future blurs, where the origins of life and the possibilities of life beyond Earth intersect. Studying these ancient organisms and records is not just an exercise in curiosity, it has practical and philosophical implications. Understanding how life has persisted in stable environments for hundreds of millions of years can shed light on how it might respond to future changes. It can reveal how ecosystems recover from mass extinctions, how they adapt to slow shifts and sudden shocks. It can inform conservation strategies by identifying species and systems that are particularly vulnerable or resilient. It can guide the search for life beyond Earth by showing what kinds of environments can sustain life over geological timescales. It also forces us to rethink what we mean by progress. Evolution is often portrayed as a relentless march toward complexity and innovation, but the deep sea shows that success can also mean stability. Some of the most successful organisms in Earth's history are those that found a way to thrive and then stayed much the same for hundreds of millions of years. They are not relics of the past. They are masters of persistence, adapted to niches that have remained constant while everything around them changed. Their survival is not an accident, it is an achievement, and yet, even this ancient stability is now under threat. Human activities are altering the deep ocean in ways that could disrupt systems that have been stable for millions of years. Climate change is warming the deep sea and changing its circulation patterns. Carbon dioxide is acidifying the water, affecting the ability of organisms to build shells and skeletons. Deep-sea mining threatens habitats that have remained undisturbed since before humans existed. Pollution is introducing new chemicals and materials into sediments that have long recorded only natural processes. The time capsule of the deep is still being written, but we are now among its authors, and our influence may reverberate far into the future. This realization adds urgency to the study of the deep ocean. It is not just about understanding the past. It is about preserving the conditions that have allowed life to endure for so long. It is about recognizing the value of systems that operate on timescales far longer than human lifespans. It is about learning from organisms that have mastered the art of survival in extreme and stable environments. And it is about ensuring that the time capsule remains a record of resilience rather than a monument to loss. The deep sea, in all its ancientness, is not static. It is alive, evolving, responding to change even as it preserves the past. It is a bridge between Earth's earliest history and its far future. And as we learn more about it, we begin to see that the story it tells is not just about life that hasn't changed. It is about life that endures, life that has weathered cataclysms and adapted to extremes, that has persisted through upheavals that reshape the surface world. It is about the continuity of life itself, written in the language of genes and fossils, sediments and stones, and as we dig deeper into that continuity, we begin to glimpse something even larger, the way the deep ocean connects Earth's past to its present and future, and the way it connects our planet to others. Because if the deep sea holds the memory of life on Earth, it may also hold the key to understanding life elsewhere. And to see that connection clearly, we must look beyond the biological and geological, beyond the physical and chemical, to the patterns and principles that govern life in extreme environments. We must look at how the deep ocean shapes and is shaped by the planet as a whole, and how in turn it may help us understand our place in the cosmos. For all the stillness and darkness that define the deep ocean, it is far from lifeless. In fact, it is in that very darkness that one of the most extraordinary phenomena in nature flourishes. Where sunlight fades and vision should be useless, countless organisms have evolved to produce their own light. It is not borrowed light from the sun, not a reflection or a refraction, but light born from within, chemical light, cold light, purposeful light. It is bioluminescence, and in the deep ocean, it is everywhere. It pulses in the water column like constellations scattered through a black sky. It glows in the bodies of fish, jellyfish, squid, shrimp, and microbes. It flashes, shimmers, and drifts, transforming the abyss into something that feels almost cosmic. In the absence of stars above, the deep sea makes its own. The chemistry behind this phenomenon is deceptively simple. Bioluminescence is the result of a chemical reaction between a light-producing molecule called luciferin and an enzyme called luciferase. When luciferin is oxidized, combined with oxygen, it releases energy in the form of light. The specifics of this reaction vary among species, and so do the molecules involved, but the basic principle is remarkably consistent across the tree of life. What is more astonishing is how often it has evolved. Bioluminescence is not the result of a single ancestral innovation. It has appeared independently dozens of times in different lineages, in bacteria, fungi, insects, fish, and cephalopods. In the deep sea, where darkness is the rule, it is not the exception, but the norm. Scientists estimate that more than 3/4 of deep-sea organisms produce light in some form. This abundance raises a question: why? Light is expensive to make. It requires energy and specialized biochemistry. It serves no purpose unless it gives the organism that produces it some advantage, and in the deep ocean it serves many. Bioluminescence is not one thing but many things, a tool adapted to countless purposes. It is communication and camouflage, lure and weapon, distraction and disguise. It is as versatile and as essential as sight is on land. For many organisms, bioluminescence is a means of hiding rather than revealing. It is a paradox that makes perfect sense in the deep sea. At depths where sunlight is faint or absent, the faint glow from above filters down as a dim blue haze. Predators looking upward can see the silhouettes of their prey outlined against that light. To counter this, many animals produce their own light on their undersides in a process known as counter-illumination. By matching the brightness and wavelength of the light from above, they erase their silhouettes, blending into the background and becoming nearly invisible. Squid, shrimp, and small fish use this strategy, adjusting the intensity of their light to match changing conditions. It is camouflage not by hiding in shadow, but by creating it. Other creatures use light as a lure. The most famous example is the anglerfish, whose name itself speaks to its strategy. A long, thin appendage extends from its head, tipped with a glowing lure produced by symbiotic bacteria. In the darkness of the deep, that point of light is irresistible to smaller fish, which mistake it for prey. They swim closer, only to be swallowed whole by the waiting predator. Some deep-sea squid dangle glowing tentacles to attract shrimp. Certain jellyfish trail bioluminescent filaments that entice plankton. Even microscopic organisms use light to attract hosts or prey. It is deception, as elegant as it is deadly. A trap baited not with food, but with light itself. Bioluminescence can also be a weapon of defense. When disturbed, some organisms release clouds of glowing fluid into the water, confusing or startling predators and providing a chance to escape. Others flash brightly when attacked, drawing the attention of larger predators that might in turn attack their attacker. Some squid eject glowing mucus instead of ink, blinding their pursuers with light rather than darkness. Even tiny dinoflagellates, single-celled plankton, can flash when disturbed, perhaps to attract fish that feed on the small crustaceans trying to eat them. In the deep ocean, where speed and strength are often limited by energy constraints, light can level the playing field. Light is also a language. Many deep-sea organisms use bioluminescence to communicate with one another, to attract mates, coordinate movements, or signal threats. Some fish produce species-specific patterns of light that help them find and recognize partners in the vast darkness. Certain squid display complex sequences of flashes during courtship, turning their bodies into living messages. Even some bacteria use light as a signal, glowing only when they reach a certain density inside their hosts. These signals can be subtle or spectacular, simple or intricate, but all demonstrate that light in the deep is not just a physical phenomenon. It is a form of information. In some cases, light serves more than one function at once. The dragonfish, a predator that lives in the mesopelagic zone, uses bioluminescence both to see and to hunt. It produces red light, a rarity in the deep, where most bioluminescence is blue or green, and it can see that light with specialized eyes. Because most other animals cannot, the dragonfish effectively uses an invisible flashlight to illuminate its prey without revealing itself. It is a remarkable adaptation, one that shows how evolution can push bioluminescence beyond simple signaling or deception and turn it into a sophisticated tool. The diversity of bioluminescent strategies is matched by the diversity of the organisms that use them. Some fish have light organs, photophores, arranged in precise patterns along their bodies, each controlled by nerves and muscles. Some squid can control the shape and intensity of their light by expanding and contracting chromatophores around their photophores. Certain jellyfish produce light when touched, while others glow constantly. Many deep-sea creatures do not produce light themselves, but rely on symbiotic bacteria housed in specialized structures. These bacteria, often of the genus Vibrio, glow continuously, and the host organism controls the light by regulating the flow of oxygen or the position of shutters. This partnership is ancient and widespread, a striking example of how life in the deep has evolved cooperative strategies to harness light. The physical properties of water shape how this light behaves. Water absorbs light quickly, and longer wavelengths like red and orange vanish within the first few meters. Blue and green penetrate farther, which is why most bioluminescence appears in those colors. The light produced is typically dim, often no brighter than a watch face. But in the total darkness of the deep, it is more than enough. Because it is produced by chemical reactions rather than heat, it is also cold, wasting little energy. And because it can be switched on and off almost instantly, it can be used with exquisite precision. For scientists, studying bioluminescence is challenging but rewarding. Observing it in the wild requires specialized equipment and careful planning. Many deep-sea organisms are fragile and difficult to keep alive in captivity, and their light-producing mechanisms often stop functioning outside their natural conditions. But advances in imaging, deep-sea submersibles, and molecular biology are revealing more about this phenomenon every year. Researchers are uncovering the genetic basis of bioluminescence, the diversity of luciferins and luciferases, and the evolutionary pathways that led to their repeated emergence. They are also discovering new functions and behaviors, many of which challenge existing assumptions. The study of bioluminescence has practical applications far beyond marine biology. The luciferous-luciferin reaction is widely used in medical diagnostics, biotechnology, and environmental monitoring. It allows scientists to track gene expression, detect pollutants, and measure cellular activity. Bioluminescent markers have revolutionized molecular biology, enabling researchers to visualize processes that were once invisible. Understanding how organisms control and use light could lead to new technologies in imaging, communications, and materials science. Even the symbiosis between bacteria and hosts offers insights into microbiomes and cooperative evolution. But perhaps the most profound impact of bioluminescence is not practical, but philosophical. It challenges our assumptions about light and life. On the surface, light is synonymous with the sun. It defines day and night, life and death. Plants use it to grow, and animals depend on it to see. It structures our time, our behavior, and even our language. But in the deep sea, light is not a gift from the sun. It is a creation of life itself. It emerges from darkness, not in defiance of it, but because of it. It is not a passive condition of the environment, but an active adaptation to it. It is not universal, but local, specific, and diverse. This inversion forces us to rethink our notions of habitability and possibility. If life can make its own light, it does not need a star. If ecosystems can thrive without sunlight, they might exist in places we once thought impossible. Beneath the ice of Europa, in the subsurface oceans of Enceladus, in the dark interiors of exoplanets far from any sun. Bioluminescence shows that light and life are not inseparable. It shows that life is not merely a passenger of its environment, but an agent that reshapes it. It shows that the boundaries of the possible are far wider than we imagined. Bioluminescence also deepens our appreciation of the deep sea as an ecosystem. It is not a barren void, but a vibrant, dynamic world where light is a tool, a language, a weapon, and a lure. It is a world where communication is written in flashes and glows, where predators and prey wage battles of deception and detection, where cooperation and competition play out in patterns of light. It is a world where the absence of sunlight has not limited life, but inspired it to invent new ways of seeing, hiding, and surviving. And yet, for all that we have learned, bioluminescence remains one of the least understood phenomena in the ocean. Many species that produce light have never been observed alive. Their light organs are known only from preserved specimens. The chemical pathways that produce their light are unknown. The purposes of their glows are still speculative. Even the basic question of how many bioluminescent species exist has no clear answer. Every deep-sea expedition reveals new ones, and many more almost certainly remain undiscovered. The stars that swim in the deep are countless, and we have mapped only a few. This ignorance is not a failure. It is a sign of how much remains to be explored. The deep ocean is vast, and our glimpses of it are brief and narrow. Bioluminescence reminds us of that vastness. It is a phenomenon that is at once familiar and alien, simple in principle, yet endlessly varied in expression. It is a reminder that even in places where we think we understand the basics, light, vision, communication, life can surprise us. It is also a reminder that our planet still holds wonders as strange and beautiful as anything we might hope to find elsewhere. The night sky inspires awe because it is filled with stars, distant and unreachable. The deep ocean is no less awe-inspiring. Its stars swim instead of shine. They drift and dart, pulse and fade. They live and die. They are part of a living cosmos beneath our feet, one that we are only beginning to know. Bioluminescence connects the deep sea to the rest of the planet in unexpected ways. It influences predator-prey dynamics, shaping who eats whom and how. It affects the behavior of species across trophic levels, from microbes to fish to whales. It even plays a role in the cycling of carbon, as glowing plankton attract grazers that move organic matter through the food web. It is a fundamental part of the deep ocean's ecology, woven into its fabric as deeply as photosynthesis is woven into life on land. And because of that, understanding it is essential to understanding the deep sea itself. It also connects the deep to our imagination. Bioluminescence has fascinated humans for as long as we have known of it. Ancient sailors told stories of glowing seas and fire in the water, attributing them to spirits, gods, or magical creatures. Even today, the sight of a bioluminescent wave breaking on a beach or a glowing jelly drifting past a submersible window evokes a sense of wonder. It blurs the line between the earthly and the cosmic, the familiar and the alien. It reminds us that mystery is not confined to distant galaxies. It thrives here, in the water that covers most of our planet. And if we follow that light deeper, if we trace it beyond the individual flashes and glows to the ecosystems and processes it illuminates, we begin to see an even larger picture. Bioluminescence is not an isolated curiosity. It is part of a complex network of interactions that sustain life in the deep. It shapes behaviours, structures, communities, and influences the flow of energy and matter. It links the biological to the geological, the chemical to the ecological. It is one thread in the vast tapestry of the deep ocean, a thread that, once noticed, changes how we see the whole. In that sense, the stars that swim are more than just beautiful. They are essential. They are signs of life adapting to darkness, of energy flowing through ecosystems, of evolution finding new paths. They are evidence of the creativity of life and of the deep ocean's capacity to surprise us. And they are reminders that the unknown is not just a place we have not yet explored. It is a reality that life continues to shape and inhabit in ways we do not yet understand. The light of the deep sea is not eternal. It flickers, shifts, evolves. It reflects the balance between predator and prey, the availability of nutrients, the stability of ecosystems. It can be disrupted by human activity, by noise, by pollution, by climate change. Changes in surface conditions can alter the reign of organic matter that sustains deep sea life, changing the abundance and distribution of bioluminescent species. Deep sea mining and drilling can destroy habitats before we have even documented the creatures that live there. The stars that swim are fragile, and their future depends on choices we make far above them. To understand and protect them, we must continue to explore. We must build tools that can see in the dark, sample gently, and measure precisely. We must invest in missions that spend weeks or months, not hours, in the deep. We must study not just individual species, but the networks and processes that connect them. And we must recognize that the deep ocean is not separate from us. It shapes our world, and we shape it in return. In doing so, we might also learn something about ourselves. Bioluminescence shows that life is not a passive passenger on a planet illuminated by a distant star. It is an active force that can make its own light, its own energy, its own meaning. It shows that darkness is not the absence of possibility, but a canvas for innovation. And it shows that even in the most extreme and alien environments, life finds ways not just to survive, but to shine. And if we follow that glow farther still, it leads us into realms even more hidden. Places where light is rare or absent entirely. Where the seafloor itself holds secrets that we have only begun to uncover. Beyond the shimmering bodies and flashing lures lies a landscape carved by time and shaped by forces as powerful as any on Earth. There, the abyss holds structures that dwarf our tallest buildings and mysteries that challenge our deepest assumptions. And to understand why the deep sea remains so unknown, we must turn our attention next to that landscape, to the trenches and ridges, the canyons and plains, the hidden geography of the greatest wilderness on Earth. If light in the deep ocean is a rare and precious resource, then sound is its opposite. It is abundant, omnipresent, and capable of travelling where light never could. In the near-total darkness of the abyss, where vision is limited or meaningless, sound becomes the primary medium of connection. It is the carrier of information, the mapmaker of space, the heartbeat of ecosystems, and the thread that links distant lives together across vast expanses of water. Where stars that swim flicker and fade within meters, sound can travel for thousands of kilometers, bending and bouncing through layers of water in ways that still surprise scientists. It is the deep ocean's most powerful messenger, and without it, life in that silent world would be almost impossible. Sound behaves differently in water than in air. It moves about 5 times faster and travels much farther because water is denser and more elastic. Low-frequency sounds, in particular, can propagate over immense distances, sometimes circling entire ocean basins. Even subtle noises can carry far from their source. This efficiency makes sound a uniquely valuable tool in an environment where visibility is limited to a few meters and chemical cues diffuse slowly. It is why so many marine organisms have evolved to use sound for communication, navigation, hunting, and defense. It is why humans too rely on sound to explore and monitor the deep, using sonar to map the seafloor, detect submarines, and track marine life. And it is why the ocean, despite its apparent silence, is anything but quiet. To descend into the abyss with sensitive instruments is to enter a world filled with sound. Some of it is natural, the constant background hum of the planet at work. Wind and waves at the surface create a steady hiss. Rain produces a distinct patter, and ice breaking apart in polar seas adds sharp cracks and groans. Earthquakes send seismic waves rippling through the water, while submarine volcanoes produce deep rumbles and explosive booms. The grinding of tectonic plates, the carving of icebergs, even the faint vibrations of landslides all contribute to this underwater soundscape. These noises are not random. They carry information about the processes shaping the planet. Scientists have used them to monitor storm intensity, detect volcanic eruptions, and even track changes in the cryosphere. Layered on top of these geological and atmospheric sounds are the voices of life. Marine animals produce a staggering variety of sounds, from the infrasonic rumbles of great whales to the ultrasonic clicks of dolphins and porpoises. Even the smallest creatures contribute. Snapping shrimp, no larger than a finger, generate some of the loudest biological sounds in the ocean by snapping their claws shut so fast that they create a bubble that collapses with a sharp crack. Fish produce grunts, drums and hums by vibrating muscles attached to their swim bladders. Crustaceans scrape and click as they move across the sea floor. Together, these sounds form a complex and dynamic acoustic environment, a living symphony that changes with time of day, season, and location. Communication is one of sound's most vital roles in the deep. For animals that cannot rely on sight, acoustic signals are essential for finding mates, coordinating group behavior, and maintaining social bonds. Many fish species produce choruses at dawn and dusk, their synchronized calls marking territory and attracting partners. Male toadfish hum to lure females into their nests, creating a low, resonant tone that can be heard over long distances. Some species of squid and cuttlefish, though not vocal themselves, are sensitive to sound and may use it to locate prey or avoid predators. Even invertebrates like lobsters and crabs produce vibrations and low-frequency sounds to communicate during mating and aggression. Whales and other marine mammals take acoustic communication to an extraordinary level. Baleen whales such as blue, fin and humpback whales produce low-frequency songs that can travel hundreds or even thousands of kilometers. These songs serve a range of purposes, from attracting mates to navigating ocean basins, and they may even change in response to shifting environmental conditions. Humpback whale songs, in particular, are known for their complexity and evolution over time, with new phrases and structures emerging and spreading across populations like cultural trends. Toothed whales, including dolphins, sperm whales, and beaked whales, use high-frequency clicks and whistles for echolocation and communication. Their clicks act as biological sonar, bouncing off objects and returning echoes that reveal the size, shape, and distance of prey or obstacles. Their whistles convey social information, identifying individuals and maintaining cohesion within groups. In the deep ocean, where conditions are stable and light is scarce, sound can also serve as a beacon, a guide that helps animals orient themselves and navigate. Some fish and invertebrates use the soundscape itself as a map, recognizing the acoustic signatures of different habitats and using them to locate feeding grounds or spawning sites. Larval fish drifting in the currents may use reef noise to find their way to suitable settlement sites. Migrating whales use the Earth's low-frequency sound background, produced by wind, waves, and geological activity, as a kind of compass. Even subtle differences in sound can carry vital information about location, depth, and environmental conditions. Humans, too, rely on sound to explore and understand the deep. Sonar, sound navigation and ranging, is the primary tool for mapping the seafloor, detecting objects, and studying marine life. Active sonar systems send out pulses of sound and measure the echoes that return, revealing the shape of the seafloor, the presence of schools of fish, or the movement of submarines. Passive systems simply listen, detecting the sounds produced by animals, ships, and geological events. These technologies have revolutionized oceanography, allowing scientists to map terrain, track migrations, and monitor seismic activity. They have also revealed just how noisy the ocean is, and how much of that noise is produced by humans. Anthropogenic noise, the sound generated by ships, drilling, construction, and military activity, has become one of the defining features of the modern ocean soundscape. Large cargo vessels produce continuous low-frequency noise that can travel across entire ocean basins. Seismic surveys used in oil and gas exploration generate powerful pulses that can be heard for hundreds of kilometers. Naval sonar systems emit intense sounds that may disorient or harm marine mammals. Even the hum of offshore wind farms and the hammering of pile-driving operations add to the cacophony. This noise pollution can have profound effects on marine life, interfering with communication, navigation, and feeding. It can mask the songs of whales, disrupt fish spawning, and cause stress or even physical harm to sensitive species. The consequences of this growing noise are still being studied, but the evidence is troubling. Some whale populations have altered their migration routes, or changed their vocalizations in response to ship noise. Fish exposed to chronic noise show changes in growth, reproduction, and behavior. Invertebrates like squid and cuttlefish can suffer damage to sensory structures. Even microorganisms may be affected by vibrations in ways we do not yet understand. Because sound is so central to life in the ocean, altering the acoustic environment can ripple through entire ecosystems. Efforts to mitigate these impacts are underway. Quieter ship designs, speed limits, and rerouted shipping lanes can reduce noise in critical habitats. Restrictions on seismic surveys and naval sonar can protect sensitive species. Passive acoustic monitoring networks can help scientists track changes in the soundscape and assess their effects. But managing noise in the ocean is challenging, in part because sound does not respect boundaries. It travels far beyond the source, and its effects can accumulate in complex ways. Addressing this issue requires international cooperation and long-term commitment, the same qualities needed to tackle other global challenges. The study of the ocean soundscape is revealing more than just the impact of noise. It is providing new insights into the functioning of the planet. Acoustic sensors can detect changes in temperature, as sound speed depends on temperature, salinity, and pressure. They can track large-scale ocean circulation, monitor ice melt, and even detect tsunamis. Networks of underwater microphones, hydrophones, are being used to listen to everything from the calls of elusive whales to the rumblings of undersea volcanoes. These data are helping scientists build a more complete picture of the ocean's dynamics and how they're changing in a warming world. Sound is also revealing the deep in ways that light and touch cannot. Acoustic imaging systems can map structures buried beneath sediments, revealing buried channels, ancient coastlines, and hidden faults. They can detect plumes of methane rising from the seafloor, signaling areas of gas hydrate destabilization or seeps that support unique ecosystems. They can even eavesdrop on the movements of animals that are otherwise invisible, tracking migrations, feeding events, and social interactions in near real time. Through sound, the deep becomes legible, its hidden patterns audible to those who know how to listen. Listening to the deep ocean is not just a scientific exercise. It is also a way of connecting with a world that operates on timescales and scales far beyond our own. The low, slow moans of fin whales, repeated over hours and days, echo across hundreds of kilometers, linking distant individuals in a vast invisible network. The chorus of fish rising and falling with the day-night cycle mirrors the rhythms of light that never reach the depths. The crack and roar of calving ice sheets connect polar processes to equatorial waters. Even the faint continuous hum of microseisms, vibrations generated by waves interacting with the seafloor, reflects the heartbeat of the planet itself. These sounds remind us that the deep ocean is not silent or static. It is alive with energy and motion, conversation and conflict. It is a place where communication is not limited by proximity or sight, where messages travel far and fast, where the environment itself speaks in tones and frequencies that span the spectrum. It is a place where sound is not just a tool but a defining feature, shaping how life behaves, how ecosystems function, and how we come to know a world we cannot see. They also remind us that the deep ocean is not separate from the rest of the planet. The sounds of storms, ice, and earthquakes connect it to the atmosphere, the cryosphere, and the solid Earth. The songs of whales link polar feeding grounds to tropical breeding areas. The hum of ships and the thump of seismic air guns link distant economies and technologies to fragile ecosystems. The soundscape of the deep is a global phenomenon, a tapestry woven from natural and human threads alike. For all its importance, this soundscape is still poorly understood. We have only a handful of long-term acoustic records from the deep ocean, and many regions have never been monitored at all. We do not fully understand how soundscapes vary across time and space, how they respond to climate change, or how they influence ecological processes. We do not know how many species use sound in ways we have not yet detected, or how their behaviours might change in a noisier ocean. Each new hydrophone deployment, each new recording, reveals unexpected patterns, mysterious signals of unknown origin, unexplained shifts in frequency, unrecognised voices in the underwater chorus. These mysteries are not just curiosities. They hint at the complexity of a world that is still largely hidden from us. They suggest that sound may carry information we have not yet learned how to decode, that the deep may be telling stories we are not yet equipped to hear, and they challenge us to listen more carefully, to expand our attention beyond the spectacular to the subtle, beyond the obvious to the overlooked. In many ways, sound is the key to unlocking the deep. It allows us to map where we cannot see, to measure what we cannot touch, to monitor what we cannot reach. It connects us to processes that unfold over vast distances and long timescales. It reveals the presence of creatures that live beyond our sight, and it offers a way to understand and protect an environment that is as vital to our planet as any landscape on the surface. But sound is not just a scientific tool. It is a bridge between species, between ecosystems, between the present and the past. The songs of whales we hear today are echoes of ancient evolutionary histories, shaped by millions of years of adaptation. The rumbles of undersea volcanoes connect the deep to the planet's fiery interior, just as they did billions of years ago. The background hum of waves and wind links the ocean to the atmosphere in a feedback loop that sustains life. To listen to the deep is to listen to the Earth itself, speaking in a language older and more enduring than any human word. The soundscape of the abyss is a reminder that the deep sea is not defined solely by what it lacks — light, warmth, human presence — but by what it possesses in abundance: energy, motion, and connection. It is a reminder that communication does not require sight, that navigation does not require maps, that awareness does not require eyes, and it is a reminder that the unknown is not silent. It is speaking all the time. We simply need to learn how to hear it. And beyond the sounds themselves, beyond the echoes and vibrations, lies the role the deep plays in shaping the systems we depend on, systems that extend far beyond the ocean's edge. The deep does not merely receive sound. It helps regulate the climate, store carbon, and sustain the cycles that make life on Earth possible. To understand why this vast realm remains so unknown, and why it matters so deeply, we must follow the threads that connect its hidden processes to the surface world, to weather and climate, to atmosphere and biosphere, to the stability of the planet itself. For all the mystery and isolation that surround the deep sea, it is not a passive world sealed off from the rest of the planet. It is not a distant realm existing apart from the cycles and systems that shape life on the surface. It is, in fact, one of the most powerful engines of Earth's stability. It regulates temperature, stores carbon, circulates nutrients, and drives feedbacks that determine the planet's climate. It connects atmosphere and biosphere, geology and biology, past and future. And it does all this not through dramatic bursts of energy, but through slow, steady processes that unfold over decades, centuries, and millennia. Processes so vast and subtle that they are easy to overlook, even as they shape the conditions that make life possible. At the heart of this planetary engine is the ocean's capacity to absorb, store, and redistribute heat. More than 90% of the excess heat generated by human-caused greenhouse gas emissions has been absorbed by the ocean, and much of that heat ultimately ends up in the deep. Water has a high heat capacity, meaning it can store large amounts of heat without changing temperature dramatically. This property, combined with the vast volume of the ocean, allows it to act as a massive heat reservoir. Surface waters warmed by the sun mix with deeper layers through wind-driven currents, and vertical mixing. Over time, heat is transported downward, where it is stored for decades or centuries before slowly returning to the surface or being released to the atmosphere. Without this buffering capacity, Earth's climate would respond much more rapidly and violently to greenhouse gas forcing. The deep ocean, in a very real sense, slows time, stretching out the planet's response to change and buying us time to adapt. This redistribution of heat is part of a larger system known as thermohaline circulation, the global conveyor belt of water driven by differences in temperature and salinity. Warm, salty water from the tropics flows poleward at the surface, where it cools, becomes denser, and sinks to form deep water masses. These dense waters spread across the ocean basins, flowing along the seafloor and slowly rising back to the surface thousands of kilometers away. This circulation connects all the world's oceans into a single global system, transporting heat, carbon, oxygen, and nutrients. It influences regional climates, stabilizes weather patterns, and sustains marine ecosystems. It is one of the most important processes on Earth, and much of it takes place in the deep. The formation of deep water is especially critical. In the North Atlantic, where cold, salty water sinks near Greenland and Iceland, and in the Southern Ocean, where frigid waters form near Antarctica, massive volumes of water descend into the abyss, carrying with them not just heat but dissolved gases, including carbon dioxide. Once in the deep, this water can remain isolated from the atmosphere for hundreds or even thousands of years. During that time, it circulates slowly, absorbing more carbon from sinking organic matter and chemical reactions. This deep storage of carbon is one of the most important regulators of Earth's climate. It removes carbon dioxide from the atmosphere, lowering greenhouse gas concentrations and helping to stabilize temperature. It also means that the ocean's response to changes in carbon emissions is delayed, creating a lag between cause and effect that shapes the trajectory of climate change. Carbon storage in the deep ocean is closely linked to the biological pump, the movement of carbon from the surface to the deep driven by life. Phytoplankton, microscopic plants that live in the sunlit upper layers, use carbon dioxide to build organic matter through photosynthesis. When they die or are consumed, some of that carbon sinks as particles to deeper waters. Along the way, it is broken down by bacteria, releasing nutrients and dissolved carbon that enrich the deep. A fraction of it continues downward, eventually reaching the seafloor, where it can be buried in sediments and locked away for millions of years. This biological pump is a powerful force. It transfers about 10 billion tons of carbon from the surface to the deep ocean every year, helping to keep atmospheric carbon dioxide levels lower than they would otherwise be. Without it, Earth's climate would be significantly warmer. The physical and biological pumps work together to shape not just carbon storage, but also nutrient cycling. As deep waters circulate, they accumulate nutrients from decomposing organic matter, nitrogen, phosphorus, iron, and other elements essential for life. When these waters eventually return to the surface, they fertilize phytoplankton, fueling new growth and sustaining marine food webs. Upwelling zones, where deep waters rise to the surface, are among the most productive regions on Earth, supporting vast fisheries and diverse ecosystems. These cycles are not just biological curiosities, they are integral to the functioning of the planet. They connect the deep ocean to the surface and the atmosphere, linking the fate of microscopic plankton to the climate that shapes human societies. The deep sea also influences climate through its role in storing and releasing greenhouse gases other than carbon dioxide. Methane, a potent greenhouse gas, is trapped in vast quantities beneath the seafloor as methane hydrates, ice-like structures formed under high pressure and low temperature. These deposits, found on continental margins and in deep sediments, are stable under current conditions but could become unstable if temperatures rise or pressure decreases. If released, methane could accelerate warming, creating a powerful feedback loop. Understanding the stability of these deposits and how they might respond to a warming ocean is a major focus of climate research. Another critical aspect of the deep ocean's climate role is its interaction with ice. In the polar regions, deep currents influence the formation and melting of sea ice and ice shelves. Warm deep water intruding onto continental shelves can melt the base of ice sheets from below, contributing to sea level rise. Conversely, changes in ice cover can alter surface salinity and temperature, affecting deep water formation and circulation. These feedbacks are complex and interconnected, linking the deep ocean to the stability of the cryosphere and the pace of climate change. They also highlight the importance of understanding the deep ocean's dynamics in predicting future sea level rise and polar change. The deep ocean's climate influence is not static. It has varied over geological time, shaping and responding to Earth's climate history. During ice ages, changes in ocean circulation and carbon storage helped amplify or dampen global temperature shifts. Periodic slowdowns or reorganizations of thermohaline circulation have been linked to abrupt climate events, such as the Younger Dryas cold period 12,100 years ago. Over millions of years, changes in seafloor spreading rates and volcanic outgassing have altered the balance of carbon between the ocean and atmosphere. The deep ocean has been both a driver and a responder in these processes, a dynamic participant in the Earth system. Today, that dynamic role is changing in response to human activity. As the planet warms, surface waters are becoming warmer and less dense, reducing their tendency to sink and potentially slowing the formation of deep water. Increased freshwater input from melting ice and precipitation further reduces salinity and density, compounding the effect. A slowdown in thermohaline circulation could have profound consequences, altering regional climates, reducing nutrient supply to surface waters, and weakening the ocean's capacity to absorb carbon and heat. Observations suggest that parts of the Atlantic meridional overturning circulation, a key component of global circulation, may already be weakening, though the extent and future trajectory of this change remain uncertain. Warming also affects the biological pump. Changes in temperature and stratification can alter phytoplankton communities, productivity, and the efficiency of carbon export to the deep. Ocean acidification, caused by the absorption of carbon dioxide, affects the ability of many plankton to build shells, altering the composition of sinking particles. Deoxygenation, another consequence of warming and stratification, can reduce the activity of deep-sea microbes and change the balance of nutrient cycling. These changes can weaken the ocean's role as a carbon sink and disrupt the feedbacks that regulate climate. Even the deep seafloor is feeling the impact of a warming world. Sediment cores show that deep-sea temperatures are rising, albeit slowly. These changes may seem small, often fractions of a degree, but they can affect the stability of methane hydrates, the behavior of deep currents, and the chemistry of the seafloor. They also signal that no part of the ocean, no matter how remote or insulated, is immune to the influence of human activity. The deep is not a separate world. It is part of the same Earth system that we are altering on the surface. Understanding these changes is crucial, but it is also challenging. The deep ocean is vast, remote, and difficult to study. Measurements are sparse and long-term records are rare. Many processes unfold over centuries or millennia, far beyond the timescales of most research projects or political decisions. Yet without this understanding, our predictions of future climate will remain incomplete. Climate models must account for deep ocean circulation, heat storage, carbon cycling, and feedbacks to be accurate. Observations from the deep are essential for testing and improving those models. Investments in deep-sea research, from autonomous vehicles and moorings to global observing networks, are therefore not just scientific luxuries. They are necessities for understanding and managing our changing climate. The deep ocean's role in climate is also a reminder of how interconnected Earth systems are. What happens in the atmosphere affects the ocean, and what happens in the ocean affects the atmosphere. Changes in polar ice influence circulation, which in turn influences weather patterns thousands of kilometers away. The growth of microscopic plankton affects carbon storage, which affects temperature, which affects ice and circulation. These feedbacks operate across scales of space and time, linking individual organisms to planetary processes. They demonstrate that the deep sea is not an isolated curiosity, but a central component of the Earth system, one that must be understood and protected if we are to navigate the challenges ahead. The scale of this influence is humbling. The deep ocean covers more than half the planet's surface and contains more than 95% of its habitable volume. Its circulation patterns move water masses the size of continents. Its carbon reservoir dwarfs the atmosphere's. Its heat capacity stabilizes global temperatures. Its nutrient cycling sustains marine life and, by extension, the human societies that depend on it. It is, quite literally, the engine room of the planet, and yet it operates silently, invisibly, beneath the waves. A hidden force that most people will never see, but on which we all depend. Recognizing this does more than deepen our understanding of the ocean. It reshapes how we think about climate and our relationship with the planet. It reminds us that the systems that sustain us are complex, interconnected, and often hidden from view. It challenges the notion that climate change is solely an atmospheric problem, showing that it is also an oceanic one. And it highlights the importance of protecting the deep sea, not just for its biodiversity or its mysteries, but for its role in maintaining the stability of the planet itself. Protecting that role means addressing the pressures we are placing on the ocean. Reducing greenhouse gas emissions is essential to slow warming and limit disruption to circulation and carbon cycling. Managing pollution, overfishing, and habitat destruction can help maintain the health of surface ecosystems that feed the biological pump. Regulating deep-sea mining and drilling can prevent disturbances that might release methane or disrupt sediment processes. Expanding marine protected areas, including in the deep, can safeguard critical habitats and processes. These actions are not separate from climate policy. They are climate policy because the deep ocean is central to the climate system. It also means expanding our exploration and observation of the deep. We cannot manage what we do not understand, and we cannot understand what we do not measure. Long-term monitoring networks, deep-diving vehicles, and new sensor technologies are essential tools for tracking changes in heat, carbon, circulation, and chemistry. International collaboration is equally important. The deep ocean is a shared resource, and its stability affects every nation. Coordinated efforts to study and protect it are in everyone's interest. The deep ocean's role in climate also offers a measure of hope. Despite the profound changes we are causing, the ocean continues to buffer much of the excess heat and carbon we produce. Its vastness and inertia give us time to act, time to adapt, time to change course. That time is not unlimited, and it should not be squandered. But it is a reminder that the systems we rely on are resilient as well as vulnerable. They can absorb shocks, adapt to change, and continue to function if we give them the chance. In the end, the deep ocean's role as a climate regulator is a story of balance. A balance between heat and cold, carbon and oxygen, stability and change. It is a story of connection, linking the smallest plankton to the largest ocean currents, the deepest trenches to the highest clouds. And it is a story of time, unfolding over centuries and millennia, shaping the planet in ways that transcend human lifespans. It is a story we are only beginning to understand, but one that we cannot afford to ignore. And beyond the physics and chemistry, beyond the cycles of carbon and heat, lies another dimension of the deep's connection to climate, its vulnerability. The deep ocean may buffer change, but it is not immune to it. Human activities are reaching farther and deeper than ever before, bringing new pressures to a realm that has long been shielded by distance and depth. Pollution, mining, and the spread of industrial activity threaten to disrupt the deep's delicate balance. And to understand why the deep sea remains so unknown, and why that matters, we must confront those threats directly, and consider how they are reshaping the very systems we depend on. For most of human history, the deep ocean was beyond our reach, and therefore beyond our concern. Its darkness and depth seemed to shield it from the consequences of our actions, a hidden world insulated from the turmoil at the surface. That illusion no longer holds. The deep is no longer untouched. It is no longer immune. Human influence now extends into its most remote corners, carried by currents, driven by technology, and embedded in the very fabric of the planet. And though we rarely see the damage we cause, the threats are there, insidious, persistent, and growing. Pollution, mining, climate change, and exploitation are altering the deep ocean in ways that could reshape its ecosystems and disrupt the planetary functions it sustains. They are not distant possibilities. They are happening now, often in places we have never seen, and to organisms we have never named. Pollution is perhaps the most pervasive of these threats because it does not require deliberate intrusion to reach the deep. It arrives uninvited, carried by rivers, winds, and currents, sinking slowly through the water column until it settles on the seafloor. Plastics are among the most visible examples, though ironically they are often invisible to us once they enter the deep. Every year, millions of tons of plastic waste enter the ocean, breaking down into fragments and fibres that are carried far from their source. These particles, microplastics and nanoplastics, have been found in the deepest ocean trenches, more than 10 kilometres below the surface. They accumulate in sediments, are ingested by deep-sea organisms, and enter food webs that were once thought to be isolated from surface pollution. Their presence is not just a marker of human impact, it is a physical change to the environment, altering the properties of sediments, interfering with feeding and digestion, and potentially transporting toxic chemicals into sensitive ecosystems. Chemical pollutants follow similar paths. Persistent organic pollutants, industrial chemicals, pesticides and byproducts resist degradation and bind to particles that sink into the deep. Heavy metals like mercury and lead, released by mining, burning and industry, are transported by atmospheric deposition and ocean currents, eventually accumulating in deep-sea sediments and organisms. Even radioactive isotopes from nuclear testing and accidents have been detected in the deep ocean, carried thousands of kilometres from their source. These substances do not remain inert. They can disrupt biological processes, accumulate in tissues, and move up the food chain. In some cases, they can persist for centuries or millennia, altering ecosystems long after their release has stopped. Pollution also takes more subtle forms. Excess nutrients from agriculture and sewage drive algal blooms that, when they die and decompose, deplete oxygen in the water. These low oxygen zones can expand and intensify, altering deep-sea habitats and stressing or killing organisms that cannot escape. Increased carbon dioxide in the atmosphere dissolves into the ocean, lowering its pH and causing acidification. This affects the ability of organisms to build shells and skeletons, alters chemical reactions in sediments, and changes the availability of nutrients and metals. Even noise is a form of pollution, as the rising din of shipping, drilling and sonar disrupts the soundscape that deep-sea organisms depend on for communication and navigation. Each of these pressures alone is significant. Together they can interact in complex and unpredictable ways, compounding their effects and making recovery more difficult. If pollution is the passive consequence of our surface activities, deep-sea mining is a deliberate intrusion, an intentional effort to exploit the resources of the abyss. For decades, the deep ocean was seen primarily as a scientific frontier. That view is changing as demand for metals essential to modern technologies, cobalt, nickel, copper, rare earth elements, continues to grow. These metals are critical for batteries, renewable energy infrastructure and electronics, and much of the remaining terrestrial supply is concentrated in politically unstable regions or environmentally sensitive areas. The deep seabed, by contrast, is rich in these materials, contained in polymetallic nodules scattered across abyssal plains, in sulfide deposits around hydrothermal vents, and in cobalt-rich crusts on seamounts. These resources have attracted the attention of governments and corporations alike, and industrial-scale extraction is moving from concept to reality. The prospect of deep-sea mining raises profound questions and serious concerns. Collecting polymetallic nodules, for example, involves deploying massive machines that crawl across the seafloor, vacuuming up nodules and sediment alike. This process can strip vast areas of their biological communities, many of which are slow-growing and poorly understood. The disturbance of sediments can create plumes that spread for kilometres, smothering organisms and altering chemical gradients. The removal of nodules eliminates habitat for species that rely on them, and because nodules grow extremely slowly, millimetres per million years, their loss is effectively permanent on human timescales. Mining around hydrothermal vents poses even greater risks, as these sites host unique ecosystems found nowhere else on Earth. Disturbing them could wipe out species before they are even described, destroying natural laboratories that might hold clues to the origins of life or novel biotechnologies. The environmental impacts of deep-sea mining are not limited to the seafloor. Noise and light from mining operations can disrupt sensitive species. Sediment plumes created by discharge from mining vessels can spread into the water column, affecting organisms far above the seafloor. The release of metals and other substances from disturbed sediments could alter water chemistry and bioavailability. Even the infrastructure needed to support mining, ships, pipelines, processing facilities, contributes to greenhouse gas emissions, pollution and noise, and because the deep ocean is interconnected, impacts in one area can propagate through currents, ecosystems and cycles, reaching far beyond the mining site itself. Despite these risks, the push toward deep-sea mining is accelerating. The International Seabed Authority, ISA, the organisation responsible for regulating mining in international waters, has already issued dozens of exploration licenses covering millions of square kilometres of the seafloor. Companies are testing prototype mining systems, and commercial operations could begin within the next decade. Proponents argue that deep-sea mining is necessary to meet the demand for critical minerals, reduce dependence on terrestrial mining, and support the transition to renewable energy. They claim that with proper regulation and technology, its impacts can be minimised. Critics counter that the risks are too great and too poorly understood, and that mining should not proceed until comprehensive scientific assessments and legal frameworks are in place. The debate reflects a broader tension between exploitation and stewardship, between short-term needs and long-term consequences. It raises fundamental questions about how we value the deep ocean and what responsibilities we have toward it. The resources of the deep are tempting, but they are also finite, and the ecosystems that inhabit those regions are fragile. Once destroyed, they may never recover. The decision to mine the deep is not just a technical or economic choice. It is an ethical one, with implications for biodiversity, climate, and the stability of the planet. Pollution and mining are not the only threats. Climate change itself is altering the deep in ways that magnify other impacts. As the ocean warms, oxygen levels decline, and many deep-sea species are already living near their physiological limits. Even small changes can push them beyond those limits, leading to shifts in distribution, declines in abundance, and changes in community structure. Acidification too affects deep-sea ecosystems, particularly those that rely on calcium carbonate structures. Corals, mollusks, and some plankton may struggle to build and maintain their skeletons and shells, leading to cascading effects throughout food webs. These changes occur against a backdrop of slow growth, long lifespans, and low reproductive rates that make deep-sea organisms particularly vulnerable to disturbance and slow to recover. The cumulative effects of these pressures are difficult to predict, in part because we know so little about the baseline state of the deep ocean. In many regions, we lack even basic data on species composition, abundance, and ecological interactions. Without that knowledge, assessing the impacts of pollution, mining, or climate change is guesswork. The danger is that by the time we understand the consequences, the damage will already be done. And because the deep operates on such long timescales, recovery, if it happens at all, could take centuries or millennia. There is a deep irony in all this. The same qualities that make the deep ocean valuable, its vastness, its stability, its richness in resources, also make it vulnerable. Its ecosystems are adapted to constancy, not rapid change. Its resources accumulate over geological timescales, not human lifetimes. Its processes unfold slowly and subtly, easily disrupted by sudden disturbances. Treating it as an inexhaustible frontier ignores these realities and risks undermining the very functions that make it vital to the planet. There are alternatives to this path. Reducing plastic use and improving waste management can limit the flow of pollution into the ocean. International agreements can restrict the use of harmful chemicals and regulate emissions of heavy metals. Stronger monitoring and enforcement can reduce illegal dumping and hold polluters accountable. Transitioning to a circular economy, one that emphasizes recycling, reuse, and sustainable design, can reduce the demand for virgin materials, including those from the deep. Advances in battery technology and material science may reduce the need for some critical minerals, lessening the pressure to mine the seafloor. And comprehensive environmental impact assessments, precautionary regulations, and transparent governance can ensure that if mining does proceed, it does so with minimal harm. Some of these steps are already being taken. Efforts to ban or restrict single-use plastics are gaining momentum worldwide. Agreements like the Stockholm Convention aim to reduce persistent organic pollutants. Research into biodegradable materials and alternative mining methods is expanding. The ISA has begun developing environmental regulations, and some countries and companies have called for a moratorium on deep-sea mining until more is known about its impacts. These are important developments, but they are only beginnings. The scale of the problem demands more ambitious action and a deeper commitment to stewardship. Ultimately, the question is not whether the deep ocean can withstand human activity. It is whether we can act with enough foresight and restraint to ensure that it remains the stable, life-sustaining system it has always been. The deep is resilient, but it is not invulnerable. It can absorb shocks and recover from disturbances, but only if those disturbances are within the bounds of its capacity. Push too far, too fast, and the consequences could reverberate through the entire Earth system, altering climate, disrupting ecosystems, and undermining the services on which we depend. The threats we barely see are no less real for being hidden. They are part of the same web of causes and effects that links human activity to planetary change. They are reminders that our actions do not stop at the water's edge or the continental shelf. They sink, drift, and diffuse, reaching even the most remote corners of the planet. And they are warnings that ignorance is not protection. The deep may be out of sight, but it is not beyond our reach, and therefore not beyond our responsibility. And if there is a lesson in all this, it is that the unknown is not a void waiting to be filled. It is a living system with its own rhythms, limits, and values. Treating it as empty space for exploitation misunderstands its nature and endangers its function. Protecting it requires knowledge, respect, and humility. Qualities that are too often in short supply but are essential if we are to coexist with the rest of the planet. And perhaps this is where the unknown itself takes on a new meaning. Because even as we uncover more about the deep, even as we measure its currents and sample its sediments, vast mysteries remain. There are processes we do not understand, species we have not discovered, interactions we have not imagined. There are questions we do not yet know how to ask, and in those mysteries lies a different kind of value, one that cannot be mined, extracted, or consumed. It is the value of wonder, of curiosity, of possibility. It is the value of the unknown itself, and it may be the most important reason of all to protect the deep sea before it is too late. For all our instruments and equations, for all our satellites and submersibles, for all the data we gather and the models we refine, the truth is that most of the ocean, and indeed most of the universe, remains unknown. This is not a failure of science. It is the natural state of things. Knowledge is always a small island surrounded by a vast sea of mystery, and as that island grows, so too does its shoreline, the edge where the known meets the unknown. The deep ocean embodies this truth more completely than almost any other part of the natural world. It is a place where the limits of our understanding are not just encountered, but confronted, where our instruments falter, our concepts blur, and our confidence dissolves into questions. It is not simply that we have not explored it yet, it is that the unknown is intrinsic to it, woven into its very nature, and that matters more than we often admit. Mystery is not merely a gap to be filled, an obstacle to overcome on the way to complete knowledge. It is a driving force. It is what pulls us forward, what sparks curiosity and creativity, what pushes us to ask better questions and build better tools. Without mystery, science would be nothing more than bookkeeping, the cataloguing of facts without the pursuit of meaning. The unknown gives science its purpose and its power. It is the reason we peer into microscopes and telescopes, launch probes into space, and send submersibles into the abyss. It is the reason we speculate, hypothesize, and imagine. It is the reason we care. The deep ocean teaches this lesson again and again. Each time we descend into its darkness, we find things we did not expect. Entire ecosystems thriving without sunlight, animals with anatomies unlike anything seen on land, geological processes operating on scales we had not imagined, chemical reactions that rewrite our understanding of life's possibilities. Each discovery answers some questions but raises others, often more profound than the ones we started with. In this way, the unknown is not a wall, but a door. Every time we open it, we find more doors beyond. It is tempting to think of the unknown as a temporary condition, something that will shrink and eventually disappear as our knowledge expands. But the history of science suggests otherwise. Every breakthrough expands the horizon of what we do not know. The discovery of hydrothermal vents, for example, did not solve the mystery of how life survives without sunlight. It created new questions about the origins of life, the limits of habitability, and the nature of energy flow in ecosystems. Mapping the seafloor did not end our curiosity about the deep. It revealed complex landscapes that raised new questions about geology, chemistry, and biology. Even something as seemingly straightforward as measuring temperature at depth leads to deeper questions about circulation, heat transfer, and climate feedbacks. The unknown is not erased by discovery, it multiplies. This is why mystery matters. It is not the absence of knowledge, but the context that gives knowledge meaning. It reminds us that what we know is partial and provisional, that our theories and models are maps, not territories. It keeps science humble, open, and dynamic. It encourages us to revise our ideas when new evidence emerges, to embrace uncertainty rather than fear it. Without mystery, science would stagnate. With it, science thrives. Mystery also matters because it shapes how we see ourselves. In the presence of the unknown, we are reminded of our place in the world, not as masters of nature, but as participants in it, as learners rather than owners. The deep ocean humbles us in a way that few other environments can. Its vastness dwarfs our ambitions. Its age renders our histories fleeting. Its complexity outstrips our comprehension. To encounter it is to confront our limits, and in doing so, to appreciate the scale and richness of the world beyond them. That humility is not a weakness, it is a strength. It fosters respect, caution, and wonder. It tempers the impulse to exploit without understanding, to act without considering consequences. It reminds us that we are part of a larger system, dependent on forces and processes that we cannot fully control. It also inspires awe, not the passive awe of spectatorship, but the active awe that drives exploration, creativity, and care. Awe is not just an emotion, it is a form of attention, one that sharpens our senses and broadens our perspectives. It connects us to something larger than ourselves, and in doing so, it changes how we act. The unknown is also valuable because it expands the range of what we consider possible. Before the discovery of deep-sea hydrothermal vents, few scientists imagined that complex ecosystems could exist without sunlight. Before the detection of bioluminescence in the deep, few considered that light could be produced in total darkness. Before the realization that microbes thrive kilometers beneath the seafloor, few thought life could exist in such isolation. Each of these discoveries did more than add new facts. They expanded the boundaries of possibility, showing us that the rules we thought were universal were in fact local. They forced us to rethink not only the deep ocean, but the conditions for life itself, on Earth and beyond. This expansion of possibility has practical consequences. It informs our search for life elsewhere in the universe, guiding missions to icy moons and distant planets. It shapes our understanding of Earth's past, revealing how life began and how it has persisted through cataclysms. It influences biotechnology, medicine, and engineering, as organisms from the deep inspire new materials, processes, and ideas. The unknown is not a void. It is a reservoir of potential, a source of solutions we have not yet imagined. Yet there is another subtler reason why mystery matters, one that goes beyond science and utility. The unknown enriches our experience of the world. It gives it depth, texture, and meaning. A world in which everything is known would be flat and predictable, stripped of wonder and surprise. Mystery invites us to engage, to explore, to imagine. It makes the world more than just a collection of objects and processes. It makes it a story, one that is still being written, and in which we have a part to play. The deep ocean embodies this quality more fully than almost any other environment. It is not just unknown in detail, it is unknown in essence. We do not know how many species live there, what forms they take, how they interact, or how they will respond to change. We do not know how many geological processes operate unseen beneath the seafloor, or how many chemical reactions shape the composition of the ocean and atmosphere. We do not know how much carbon is stored in its depths, how it circulates, or how it will change as the planet warms. We do not know what secrets of life's origin or future are hidden in its extreme environments. Each of these unknowns is not a void, but a possibility, a frontier of discovery that could transform how we understand the planet and ourselves. There is, of course, a tension in our relationship with the unknown. We fear it even as we seek it. We crave certainty and control, and mystery resists both. It forces us to admit ignorance, to embrace uncertainty, to live with incomplete knowledge. That is uncomfortable, especially in a world where decisions must be made and risks managed. But it is also necessary. Certainty without understanding is dangerous. It leads to overconfidence, to exploitation without caution, to interventions that do more harm than good. Mystery, by contrast, reminds us to proceed carefully, to question our assumptions, to recognize the limits of our models. It keeps us honest. It also has ethical implications. The unknown is not just a scientific challenge, it is a moral one. It raises questions about responsibility and restraint. How should we act in a world we do not fully understand? How much should we alter systems whose workings we only partially grasp? What obligations do we have to the species, processes, and possibilities that we have not yet discovered? These questions are not abstract. They lie at the heart of debates about deep-sea mining, climate intervention, and biodiversity conservation. They remind us that ignorance is not a license to act recklessly. It is a reason to act with care. This is why some scientists and policymakers argue for a precautionary approach to the deep ocean, one that prioritizes protection over exploitation until we know more. The unknown, in this view, is not a barrier to progress, but a reason to slow down, to learn, to build safeguards. It is not an excuse for inaction, but a guide to wise action. It calls for humility, patience, and respect, qualities that are too often missing from our interactions with the natural world. Mystery also has a cultural dimension. It shapes our myths, our art, our language. For centuries, the deep ocean has been a canvas for our imaginations, a realm of monsters and marvels, of lost cities and hidden worlds. These stories were not just flights of fancy, they were ways of grappling with the unknown, of giving shape to our ignorance and expressing our curiosity. Even today, the deep continues to inspire creativity, from literature and film to music and design. It remains a symbol of the unexplored, the unconquered, the beyond. And in a world where so much feels mapped and measured, that symbol matters. It reminds us that mystery still exists, and that our relationship with it is part of what makes us human. The value of the unknown is also practical in ways that are easy to overlook. In science, uncertainty drives funding, collaboration, and innovation. It justifies exploration, motivates invention, and sustains inquiry. It fosters interdisciplinary thinking, as solving complex problems often requires integrating insights from multiple fields. It also encourages diversity of thought, as different perspectives yield different hypotheses and approaches. The unknown is not just a challenge to be overcome, it is a resource to be cultivated, and yet as our technologies improve and our knowledge expands, there is a risk that we will forget this. There is a temptation to see the unknown as a flaw, a sign of failure, something to be eliminated as quickly as possible. That temptation is dangerous. It leads to hubris, to overreach, to a narrowing of vision. It blinds us to the richness of the world and the possibilities that lie beyond our current understanding. It turns exploration into exploitation, curiosity into control. The deep ocean resists that temptation. It remains stubbornly, gloriously unknown. Even with the most advanced submersibles and sensors, we have explored only a tiny fraction of its volume. We have mapped less than a quarter of its seafloor in detail. We have identified only a small fraction of the species that live there. We do not know how many undiscovered chemical compounds, geological structures, or biological interactions await us. This ignorance is not a weakness. It is an invitation. It is a reminder that the world is larger and stranger than we imagine, and that our journey toward understanding is far from over. It is also a reminder that the unknown is not static. It changes as we learn, shifting shape and scope. Some mysteries deepen as we approach them, revealing layers we did not anticipate. Others dissolve into new questions as soon as they are answered. This dynamic quality is part of what makes science and exploration endlessly compelling. It means that there will always be more to discover, more to understand, more to wonder at. It means that mystery is not a problem to be solved, but a companion on the journey. In the context of the deep ocean, this perspective is especially important. The scale of what we do not know is so vast, and the stakes of our actions are so high, that humility and curiosity must go hand in hand. We cannot afford to treat the unknown as irrelevant or incidental. It is central to how we think about the deep and how we act within it. It is the reason we must explore carefully, protect proactively, and learn continuously. It is the reason we must resist the urge to rush headlong into exploitation and instead embrace a slower, more thoughtful engagement with this hidden world. The unknown is not just out there, waiting to be discovered. It is within us, shaping how we think, feel, and act. It is part of what makes us explorers, scientists, storytellers, and caretakers. It challenges us to expand our understanding and our empathy. It reminds us that knowledge is not an endpoint but a process, and it connects us to the planet, to each other, and to the vast, intricate web of life and matter of which we are a part. In the end, the value of the unknown is inseparable from the value of the deep ocean itself. The deep is not just a repository of resources or a regulator of climate. It is a realm of possibility, a place where life has evolved in ways we are only beginning to grasp, where processes unfold on timescales that dwarf our own, where forces beyond our comprehension shape the fate of the planet. It is a place that humbles us, challenges us, and enriches us. And its mystery is not a flaw to be fixed, but a gift to be cherished. And if we accept that, if we see the unknown not as an obstacle, but as a vital part of the deep's value, then our relationship with this hidden world changes. We stop seeing it merely as a frontier to conquer or a storehouse to plunder. We begin to see it as a partner in the story of life on Earth, a source of wisdom as well as wonder, a teacher as well as a treasure. And from that perspective, the question is not just how much we can extract from the deep, but how much we can learn from it and how much we are willing to give in return. And perhaps that is the deeper lesson of the unknown, that it is not just something to be explored, but something to be honoured. It demands not just curiosity, but responsibility, not just knowledge, but care. It calls us to act not as owners, but as stewards, not as conquerors, but as participants. And it invites us to imagine a future in which exploration and protection are not opposites, but allies. A future in which the deep remains mysterious, not because we have ignored it, but because it is inexhaustibly rich. If we can embrace that future, then the unknown will continue to guide us, not just into the depths of the ocean, but into deeper understandings of ourselves, our planet, and our place in the universe. And in doing so, it will prepare us for what comes next, for the unfinished map of a world we are still learning to see. For all the progress we've made in exploring the deep sea, the truth is that our map of this realm is still mostly blank. It is not blank because nothing is there, but because almost everything is. It is blank because we have barely touched it, because the vastness of its landscapes and the intricacy of its life are beyond the reach of our current tools and imaginations. It is blank not as an absence, but as an invitation, a space waiting for attention, care, and curiosity. The deep ocean is the last great frontier on Earth, and our future, scientific, environmental, even philosophical, will be shaped by how we choose to explore it, how we choose to understand it, and how we choose to live with it. Today, more than 80% of the ocean floor remains unmapped in high resolution. We have better maps of the surface of Mars and the Moon than of our own planet's seabed. Most of the deep species remain undiscovered, its ecosystems undescribed, its processes unexplained. We do not know the full diversity of microbial life beneath the seafloor, nor the dynamics of many deep currents, nor the role of countless chemical reactions in global cycles. We have glimpsed only fragments of its geology. The vast ridges where new crust forms, the towering seamounts that rise from the abyssal plains, the trenches that plunge deeper than Mount Everest is tall. We have observed only a small portion of its behaviours. The seasonal migrations that span thousands of kilometres, the slow shifts in circulation that shape climate over centuries, the tectonic forces that reshape the seafloor over millennia. The deep is not just unknown. It is unknowable in its entirety, too vast and complex for any single generation to fully comprehend. This incompleteness is not a flaw, but a feature. It means that exploration is not a finished project, but an ongoing endeavour, one that will outlast us. It means that the future of deep-sea science is not about reaching an endpoint, but about deepening our understanding, refining our questions, and expanding our perspective. It means that each new expedition, each new discovery, is not a conclusion, but a beginning. The tools we use to explore the deep are evolving rapidly. Autonomous underwater vehicles, AUVs, and remotely operated vehicles, ROVs, can now dive deeper, stay longer, and collect more detailed data than ever before. Advances in sensors and imaging allow us to measure temperature, chemistry, and biology at fine scales. New mapping techniques such as multi-beam sonar and satellite altimetry are revealing the contours of the seafloor in unprecedented detail. Genetic sequencing and environmental DNA, eDNA analysis, are uncovering the diversity of life from mere traces in the water. These technologies are not just extending our reach, they are transforming how we explore, allowing us to see patterns and processes that were once invisible. Yet even with these advances, the challenge remains immense. The deep ocean covers more than 360 million square kilometres, an area larger than all the continents combined, and reaches depths of over 11,000 metres. It is a dynamic, three-dimensional space, shaped by currents, pressure, temperature and time. Exploring it is not like surveying a landscape. It is like mapping a living, shifting, multi-dimensional organism. It requires patience, persistence and creativity. It requires collaboration across disciplines, nations and generations. And it requires humility, an acknowledgement that our maps will always be incomplete, that our understanding will always be provisional, that humility is especially important as human activity expands into the deep. The choices we make now will shape the deep's future and, by extension, our own. Deep-sea mining, for example, could provide resources essential for renewable energy technologies, but it could also cause irreversible damage to ecosystems and disrupt planetary cycles. Deep-sea fisheries could help feed a growing population, but overexploitation could collapse populations and destabilize food webs. Climate change could alter circulation, chemistry, and biology in ways that cascade through the Earth system, but our actions today will determine how severe those changes are. The deep is not a distant, isolated realm. It is part of the same planet we inhabit, and what happens there will affect what happens here. The unfinished map is not just a scientific challenge, it is a political and ethical one. The deep ocean lies beyond national jurisdictions, governed by international law under the principle of the common heritage of humankind. This principle holds that its resources and benefits should be shared equitably, and that its protection is a shared responsibility. In practice, however, governance is fragmented and contested. The International Seabed Authority regulates mining in international waters, but its mandate and capacity are limited. Regional fisheries management organisations oversee some fisheries, but enforcement is uneven. Marine protected areas exist, but they cover only a small fraction of the deep and often lack effective management. As interest in the deep grows, so too will tensions over access, ownership, and stewardship. Addressing these challenges will require new forms of governance, frameworks that are inclusive, transparent, adaptive, and informed by science. It will require cooperation among nations, industries, scientists, and civil society. It will require balancing competing interests: economic development, environmental protection, scientific discovery, in ways that are fair and sustainable. And it will require recognizing that the deep is not just a resource to be managed, but a system to be respected, a partner in the Earth system whose health is tied to our own. Education and public engagement will play a crucial role in shaping that future. For many people, the deep ocean is out of sight and out of mind, a distant abstraction with little relevance to their daily lives. Changing that perception is essential. The more people understand the deep's role in regulating climate, sustaining biodiversity, and shaping the planet's future, the more likely they are to support its protection. Storytelling, art, film, and education can bring the deep to life, transforming it from an unfamiliar void into a living, vital part of the planet. Citizen science initiatives, open data platforms, and virtual expeditions can involve people directly in exploration and discovery, creating a sense of connection and shared responsibility. The unfinished map also offers an opportunity to rethink how we explore. Historically, exploration has often been driven by conquest, extraction, and competition. It has been about claiming territory, extracting resources, and asserting control. The deep invites a different approach, one based on collaboration, curiosity, and care. It invites us to see exploration not as domination, but as dialogue, not as exploitation, but as partnership. It invites us to ask not just what we can take from the deep, but what we can learn from it, and how we can protect it for generations to come. Such a shift would not only benefit the deep, It would benefit us. It would help us develop technologies that are less destructive and more sustainable. It would encourage policies that prioritize long-term stability over short-term gain. It would foster a culture of science and exploration that values knowledge and stewardship as much as profit and power. And it would align our actions with the realities of a planet whose systems are interconnected and interdependent. The unfinished map is also a reminder of our shared future. The deep ocean will continue to shape Earth's climate, chemistry and biology long after our lifetimes. It will continue to evolve and change in ways we cannot predict. It will continue to hold secrets we have not yet imagined. Whether we choose to see it as a partner or a resource, a frontier or a foundation, it will remain a fundamental part of the planet's story. Our task is to decide what role we will play in that story, whether we will be careless intruders, reckless exploiters, cautious observers, or thoughtful stewards. That choice is not abstract. It is being made now, in boardrooms and laboratories, in international negotiations and local communities. It is being shaped by policies on climate, energy, fisheries and pollution, and it is being influenced by public awareness, political will and cultural values. It is being determined by the investments we make in science, the priorities we set in governance, and the ethics we bring to exploration. The future of the deep is not something that will happen to us. It is something we are creating day by day. The scale of the challenge can feel overwhelming, but it is also an opportunity. The unfinished map means there is still much to discover, much to learn, much to protect. It means that our actions matter, that they can shape outcomes for centuries to come. It means that we have a chance to write a new chapter in the story of exploration, one that is defined not by conquest but by care, not by ignorance but by understanding. And it means that mystery will endure. Even if we map every seafloor ridge and trench, sequence every genome, and model every current, there will still be questions we cannot answer. There will still be processes we do not understand, interactions we have not imagined, connections we have not traced. The unknown will remain, shifting and expanding as our knowledge grows, and that is not a limitation, but a gift. A reminder that the world is larger than us, richer than our understanding, and full of possibilities beyond our imagination. In this sense, the unfinished map is not just a description of the deep ocean. It is a metaphor for science, for exploration, for humanity itself. We too are works in progress, constantly learning, adapting and growing. Our maps of the ocean, of the universe, of ourselves are always provisional, always incomplete. And that incompleteness is what makes them worth pursuing. It is what drives us to keep asking questions, to keep venturing into the unknown, to keep imagining what might lie beyond the edge. The deep ocean will remain the least known place on Earth for a long time to come. Its vastness, its complexity, and its remoteness ensure that. But that is not a reason to turn away. It is a reason to look closer, to listen harder, to dive deeper. It is a reason to protect what we do not yet understand, to value what we cannot yet measure, to cherish what we cannot yet name. It is a reason to embrace the unfinished map not as a sign of ignorance, but as a symbol of potential. And if we do, if we accept that the unknown is not a void to be conquered but a partner to be engaged, then the deep ocean will continue to teach us, surprise us and sustain us. It will continue to challenge our assumptions and expand our horizons. It will continue to remind us that we are part of something larger than ourselves, a planet, a biosphere, a universe still unfolding. The map will never be finished. That is its beauty. That is its promise. And that is why the deep sea, with all its darkness and depth, remains the least known place on Earth, and perhaps the most important. Because in its mystery lies not just the story of our planet's past, but the key to its future. And in that unfinished map lies the story of us, of what we know, what we seek, and what we choose to become.